with long and deep experience, speak on climate change, and through the panel discussion later, we hope recommendations will emerge on the way ahead. The distinguished list of speakers today includes top scientists and practitioners from IISc, IIT Gandhinagar, IITM Pune, NIAS, WRI, IIHS Bangalore, and ISRO, apart from others. And we are honored that the symposium will be inaugurated by the chairman of ISRO, Dr. S. Somanath. Following the Indian tradition of lighting a lamp to mark an auspicious beginning, I request the Vice Chancellor to escort the Chancellor, Sundar Raju, our chief guest, Dr. Somanath, and our distinguished guests, Professor J. Srinivasan, Professor Keshav Murthy, and Dr. Harini Nagendra, to light the lamp and mark the beginning of the symposium. The invocation will be rendered by Vibhavati.
Shubham kurutvam kalyanam arogyam dhanasampadah shatru buddhi vinashaya deepa jyote namostute deepa jyote namostute deepa jyote parabrahma deepa jyote janardana deepa jyote parabrahma deepa jyote janardana deepo haratu me papam pratadipa namostute deepo haratu me papam pratadipa namostute.
I invite the Vice Chancellor, the Chancellor, and the Chief Guest to be seated on the dais. I invite the Vice Chancellor, the Chancellor, and the Chief Guest to be seated on the dais. I request the Chancellor and the Vice Chancellor to extend a traditional Karnataka welcome to our Chief Guest.
Side, sir.
Yeah.
Yeah, that's good enough.
I request the Vice Chancellor to welcome the gathering.
So good morning to all of you. I extend warm welcome on behalf of AU to all participants and chief guests. Dr. Somanath, Chairman of ISRO. There is no introduction required for Dr. Somanath. Is known person. He's he's the chairman of an important organization in the country, and he's well known for his Chandrayaan mission. So it's not successful for not only for the ISRO, but it's for the whole country. By doing Chandrayaan 3 launch, successful launch, he lifted our aspiration of the 140 people in this country. So we should thank Dr. Somanath. Congratulate him. And 2 days back there was an announcement of national awards we called Vigyan Puraskar. It's a newly introduced awards. And there was an item for team award. You can guess who will get the team award. He got it, and he and his team got the award, so we should congratulate him. So when I went and invited him, he was really agreed to come here in spite of his busy schedule. He has a launch on 15th. Accepting our invitation and coming. And we have a galaxy of speakers, the most important subject experts in this country. So when we wanted to have this climate change, as you know, that climate change is important in this present context. Delhi was flooding this year, Bombay was flooding this year, Nagpur was flooding this year, everywhere. Climate change is very important to all of us. So we thought we'll call the best experts, and we have at AU, we have started a small group on climate change. It's called Center for Climate Change, CQ. And with the CQ, we thought that we will have a discussion with all the best subject experts in this country to know what is the latest issues relevant for climate change in this country and what we can do from university perspective. So we have Professor Srinivasan, who will be talking from IIT Bangalore. He'll be talking about why we should worry about climate change. My good friend Ravi Narjundaya from IIT Bangalore, he'll talk about how we do the climate modeling and climate projections. Dr. Krishnan from IITM, he'll talk about his monsoon rainfall is changing. We have Haridi from Assembly University. She will talk about climate change impacts on cities and urban landscapes. And we had recently, while also like disaster, so I thought we will include somebody who can authoritatively speak about Wayanad disaster, what really caused. So I have a good friend, CP Rajendran. We warmly call him CP. So thank you, Dr. Rajendran, for coming. He's working at IIHS Bangalore. And we have Dr. Vimal Misra from IIT Gandhinagar. He's an expert in hydrometeorology. We have Dr. Ramana from ISRO, Hyderabad. We have Ulka Kelkar. Ulka is here. Ulka, she's from World Resource Institute, Bangalore. She will talk about how much India is going to mitigate climate change. It's a very important topic. And we have Chandri Singh. She's from IIHS Bangalore. She will talk about climate change, vulnerability and adaptation. And finally, we will have a panel discussion will be moderated by Dr. Rup Kumar, who has international exposure. He was with the UN WMO for almost 13-14 years. So we'll have a good discussion today. So I should welcome all of you. I should thank all the speakers. Also, I should welcome all of you. And also, a good number of people, students have come from IISc and other institutions from Bangalore. I welcome all of you. Before I conclude, I should really happy to welcome my guru and teacher, my PhD candidate, Professor Keshav Murthy. He was when I invited, he was really very quick enough to say yes, I will come and join. He was in IMD initially, and then he later moved to physical research laboratory as a professor in theoretical physics group, and he was the director of the IITM. So thank you, sir, for coming. So hope we will have very good discussions and better discussion. Thank you, all of you. Thank you.
Thank you, sir. I request the Chancellor to welcome the gathering.
Good morning, everyone. The challenge for me is there's a galaxy of people here that I'm not qualified to be part of. And the fact that all of you have come here and hopefully set the direction for the institute, because the Professor Dr. Rajivan here, we kind of coalesced to a point where we're saying sustainability will be the center focus for this university. And it's interesting that the first thing that we're doing is talking about climate change and how to advance the negation of climate change, if you will. So it's a real wonderful kickstart. I'm hoping that Atria University will continue to attract engagements with people like you, and hopefully there'll be an elevation in the understanding and the ability of people like us, the general citizen, if you will. But sir, really thank you so much for starting this process off. I think it's, they say it's a start is, how you start is very critical, and Dr. Somanath coming here, I think is an amazing kickstart to the whole process of the journey that I think we will travel out of Atria University, and more importantly, we as a society, citizens of India, I think it's very critical over the next few decades that all of us communicate, disseminate to a point where every single individual that is part and a citizen of this country understand the issues and challenges, understand that we are at this point where we're likely to be, threatening the existence of humanity, more importantly the next generation. So there's a phenomenal obligation all of us carry, and I hope we will with seriousness carry that obligation. Certainly I can promise on behalf of the Atria University institution, education institutions, and all that we are. As a matter of fact, one of the mandates after Professor Rajivan came in was to say, how do I convert all the commercial institutions that we have under our into sustainability as the goal. So I think it's really lovely to see all of you here, and I certainly hope to learn a lot more. I certainly hope I will, with some amount of knowledge as we go by, be able to communicate to the people that I engage with and kind of transfer this urgency, if you will, of why we need to address climate change and address it aggressively. Thank you very much for being here. I hope you have a wonderful set of interactions through the day, and I hope that this will become the core community in some ways that is driving climate change in your environments and your communities. Thank you very much.
Thank you, sir. It is an honor to share a brief profile of the extensive accomplishments of our chief guest. Dr. S. Somanath is the chairman for the Space Commission and the Indian Space Research Organization, or ISRO, and also the secretary, Department of Space, and a distinguished scientist. Under his leadership, there have been numerous accomplishments, including Chandrayaan-3 landing on the moon, the Aditya L1, XPO-SAT, INSAT 3D5, NBS-01, OceanSat, GSAT-24, and commercial PSLV and LVM-3 OneWeb missions are some of the other recent successes. Currently, he is focused on the Space Vision 2047 missions, including Gaganyaan, Chandrayaan-C, and other exploration missions, Bharatiya Antariksha Station development, and the human mission to the moon. As director of the Vikram Sarabhai Space Center, Dr. Somanath was responsible for launch vehicle technology development, where LVM-3 M1 Chandrayaan-2 mission was a major accomplishment. He spearheaded the development of critical systems for the Gaganyaan program, development of small satellite launch vehicle, reusable launch vehicle, and air-breathing technology programs. He was the director of the Liquid Propulsion Systems Center And in his tenure, the development and qualification of C-25 stage was completed and successfully flown in LVM-3 D1 flight. He was the project director when the experimental flight of LVM-3X care mission was successfully accomplished on 18th December 2014. Dr. Somanath has been bestowed with many honorary doctorates from universities including Centurion, Karunya, Satyabhama, SRM, Uttarakhand, Sharda Birla Bangalore, JNTU, KUHS, MIT and DY Patil Vidyapeeth. He is a fellow of the Indian National Academy of Engineering, Indian National Academy of Science, Aeronautical Society of India, Astronautical Society of India, and a member of the International Academy of Astronautics. He is the President-elect of AESI and President of the Society of Aerospace Quality and Reliability. Our chief guest's presence here today adds immense value to the Symposium on Climate Change, the deliberations in which will propose recommendations and solutions for a cleaner and greener world. Everyone gathered here is in eager anticipation of the inaugural address by Dr. Somanath. Sir, requesting you to take the podium to deliver the inaugural address.
Thank you. Good morning, all of you. Respected dignitaries on the dais, off the dais, and the experts that you are assembled here for this workshop on the climate change and its impact, modeling our interventions. I think all of this will be discussed and debated today. Unfortunately, I am not an expert at all in this domain. My profile is only in designing and developing rockets. That will help you to put satellites up there that you can actually see what is changing on the ground in a synoptic manner. That's all I can do. But then when you have such a galaxy of experts here speaking, discussing about climate change and modeling its interventions, I just thought that of my travel yesterday. I was traveling from Chennai to Tirupati, from Tirupati to Bangalore by road. Beautiful landscapes. On both sides you can see hillocks, small mountains, which is rocks protruding out somewhere, being blasted, quarries on either side. And also I can see the erosion that is happening on those hillocks. My thought came to a point that how all this got created and how high these hills would have been, say, 1 million years back. And how all this sand that you see on the land, the terrain that you see, how those could have been created, whether these valleys would have been this flat as like say sea, whether they have been hills and shallows, much different than this terrain would have been much different 1 million years back. This was the thought that was going on those clays and sands that you see there, how those got created. And this was also fascinated by one of my scientists speaking to me about moon. He said that when you take images of the moon surface where there are boulders, immediately you can say they are new areas. That means the surface is actually recently created, not the one which has been there for a long time, because boulders don't remain as boulders over, say, 10,000s of years. Every boulder crumbles to become dust over a period of time because of weathering or other radiation. That there is no rain, there is no air, but still on moon, boulders become dust over a period of time. And that's how you see all the sands and clay and dust is getting created. And this is a natural process because of the forces that are acting all over us changes everything that you see in front of us. Unfortunately, our lifespans are so short that you are not able to recognize these changes. In fact, when I was thinking, who causes this climate change? Is it only human beings? The answer is that no. Every living creature has an ability to make a change. Even you think about the change for the good. The human came here after the earth became a living planet later, but it was not a living planet once. Even the change from a non-livable planet to a livable planet was done by a bacteria. Even that caused the change of climate that made all of us to come into existence. And today we are human here talking about it, understanding it, and try to mitigate it. Are we really fools or really intelligent creatures that you think that you can make a change? This was a thought that came to my mind. But knowing about it is one part, and ability to change is another. And your ability to change comes out of your greater ego, that you are very powerful enough to make all these changes. I really don't know. But then, at least it's very important as a scientist to be aware of what is happening, and to measure it, to quantify it, and to predict about the changes over a period of time is really an exciting science. But beyond that, how you really play a role in making it better for us in the future? This is the second question. Of course, climate change has always been happening. I think all of you know, the scientists already know. But the speed at which it is making change is what is worrying us, because we have to get adapted to the change. And the adaptation is the major issue. And it becomes an issue to all of us only when it affects your neighborhood or you. Until then, it is not an issue at all for anyone. The rising sea is an issue that all of us know, but doesn't become an issue until your cost is eroded. And temperature rise is not an issue for you until you find it uncomfortable in walking outside. And the rain becomes an issue when your traffic getting blocked. Until then, it is not an issue for anyone. So this is the type of society that we live. So this is again a social issue, because it creates problem for societies which are having voice to change, having no voice to change. So it becomes a technical issue, a social issue, a political issue, and in many ways a global issue that all of us can discuss and debate over periods of time. But what action is being done is the second question. And whether there are any methods by which we can actually change the climate change towards better situation. It's, as we know today, we are discussing it because it is changing to a worse situation. Climate change can always be towards a better situation. Temperature go down, your weather patterns become benign. Is it ever possible? I don't know. Really, I don't see after my reading and understanding, it is not going to happen. It is only going towards difficult situation. The glaciers are going to melt, the ice caps are only going to vanish, and sea levels are going to rise, and the water levels in land is going to go down at thrice the speed as that you have been in the past. Temperature rise is going to be at least 1.5 to 2 degrees per I don't know how many years, in 10 years or so. So these type of changes are bound to happen. So what we can do today is to understand it, model it, predict it, and talk about some levels of mitigation measures. I think that's all that we can do as society. Our technological interventions on changing it, I don't know really how best it's going to be. Of course, we talk about many certain amount of mitigation measures to reduce carbon footprint. You talk about greener energy, and you put all the blame on the energy as the primary reason that drives you towards climate change. This also I really don't know whether it is the truth behind it. And if you simply change over to the so-called greener energy, whether we are really going towards the right route, because the real green is never known which is real green and the fake green, or rather some other colors you associate with those energies. But one part is very, very clear. If you go back to your roots, try to live like cavemen, possibly it could be reversed. But is it really going to happen? It's absolutely not going to happen. The comfort levels and technological progress that we are making as societies is really going to increase day by day. And this will make us to consume more from the resources that are available. So naturally, the rate at which these changes are going to happen is only going to increase and never going to come down. So it's a question of adaptation. So this is the second point, and how technologically, as human beings, we can better adapt to these changes is the question. As a scientist, as an engineer, I always consider how do you live even under extreme situations. Even when the temperature goes to 50s, 60s, whether a human being will still be able to live on Earth? This is a question which we should discuss. Whether we will still have water enough to do agriculture and drinking, whether we will be still able to create cities as we look now, or it will be a city which is underground. So what type of societies that will emerge in the next hundreds of years? This is something which you should discuss. It's a different topic, not of the climate change, climate scientist, but it is a different topic of planners, long-term visionaries, etc. And there are associated issues which population, the natural resources dwindling, agriculture produce coming down, and the use of the extensive use of earth for the food and others aspects that we live on, because it's just by high-speed internet alone you cannot live. You need everything else that we used to have for us human beings, us living creatures to survive. So this being the topic, today I understand that you are going to speak about measurements. You are also trying to quantify these changes in a scientific manner, that you won't speak just over the head, but you are actually putting facts in front of people, policymakers, to understand the impact and make policy decisions in governments, in societies, that will be towards at least making at least few generations live better than they will not ever be. That much is what we are trying to do today. I believe that society in India who are working in this area is really very well educated. Our interventions in global fora has always been really good. Possibly we need to do more as a nation, being one of the very populous country. Our population 1.4 billion going to become 1.67 billion in another few years and stabilize. I hope it will stabilize. I don't know, this is the type of numbers that are coming. I am not very sure about those calculations. But at least if it stabilizes, at least that much good. So we have a way in which we can work on, at least from the resources. Whether it will actually show a downward trend over the period of time, whether society will change in such a way that we can actually reduce population over say 100 to 200 years of time. All this becomes questions that we need to address. From space, we have been doing quite a bit. We have been working on measurements. For example, in climate modeling on the essential climate variables, as we know that we have at least 12 to 14 of them being provided on a continuous basis from our satellites. You have almost 18 satellites up there who is doing remote sensing and related measurements. Our the latest satellite, the INSAT 3 series satellites are one of the best in this series, looking at weather, climate in very good manner. We are also looking at imaging in various spectral bands to see Earth and atmospheres, oceans, coastal areas in much ice caps and glaciers in much better manner than we ever have never seen before. For example, the satellite which we are yet to launch, the NISA, is a classical example of that, looking at Earth in two radar bands, L and S band, to make very good measurements of Earth and take every 15 days one image of entire Earth at very high resolution and very high swath, so as to get information about the tectonic movements, the water, the greener areas as well as the arid areas. So it's going to give you huge information. We are also working with France on a thermal imager of Earth called satellite called Krishna, which is going to be an excellent payload that will help you. The INSAT next series of satellites are being designed now. We call it INSAT 4 series, which will give you much better understanding of the climate, weather patterns in much better spectral bands. So these works we continue and support the community who is working on it. And I will be eager to know what more we need to do, especially in developing sensors, deploying them not only through space but also with the terrestrial networks that we have, some of them through the NISES program that all of you are familiar. So I look forward to your accommodation and wish all the very best for this seminar, and let good recommendations, suggestions come out of it. To work along with you will be a pleasure. Thank you so much. And with this, let me declare this seminar inaugurated.
Thank you, sir. We will now have a networking break. Tea and coffee is also being served in the room next door. And we will start the speaker sessions at 10:30. Thank you. We begin the speaker sessions for today. Our first speaker is Professor J. Srinivasan, who established the Dinecha Center for Climate Change at the Indian Institute of Science in 2009. A fellow of the Indian Academy of Sciences and the Indian National Science Academy, Professor Srinivasan is the lead author of the second and fourth reports from the Intergovernmental Panel on Climate Change and the review editor of its third report. With more than 150 research publications in climate and thermal sciences, Professor Srinivasan will be delivering a talk on why should India be worried about climate change.
Good morning. So my talk will be somewhat pessimistic tone. You should forgive me for that, because I think the problems we're going to face in India due to climate change, some of them are something you cannot adapt to. The chairman talked about adaptation. Adaptation possible up to some extent. Beyond a certain point, you cannot adapt. Now I've been talking about this topic for 37 years, and majority of the audience, both at IISc and elsewhere, are climate skeptics. They can't believe that human beings can control the global climate. The local climate, yes, we all know that. Okay? And the best example is a famous documentary filmmaker, David Attenborough. I was surprised. He was a skeptic. Although he knows all about nature and how human beings destroyed nature, but still he couldn't believe that human being can affect the global climate. Now, many people feel that 1 degree rise in global temperature is so small, it's much smaller than a seasonal cycle in any place we live. Why should it cause any problem? Okay? And the person who really understood this well long time back is the Nobel laureate Klaus Hasselmann. He said it is changes in the statistical extreme events rather than the mean that will have the strongest impact. And we're already seeing it. Okay? We're already seeing the impact of extreme events all over the world. And so this is going to get worse and worse. And this example is, in 2001, IPCC made a prediction that part of North America will have severe heat waves and extra deaths because they are not used to hot weather. In a place like Canada, there is no air conditioner. And houses are built to prevent circulation because of the cold weather. And many people died because they are not used to that climate. Okay? So this is already happening. Okay? Now, the reason why this is happening is easy to predict. You don't need a climate model. The distribution has shifted sufficiently that in places like England, most of the extreme events occurring never occurred in the previous 100 years. And now, we are among the countries which is going to have the highest amount of heat waves, okay? And McKinsey has put a statement, will India get too hot to work? Now this is a serious issue because those of us living in cities and have accrediting capability, we may not worry about it, but remember a large part of India is working in agriculture and construction. They cannot use air conditioning. There is no hope there. Okay? And so when heat waves are occurring, there's a nice program called Ahmedabad Heat Action Plan, which was first done in Ahmedabad after many deaths. And so they have managed to control what I call dry heat waves, that is 40, 45 in May, June, and so on. But that is only one part of the problem. There's another problem which is much more serious, which is not being addressed, that is humid heat wave. Okay? And humid heat wave is peculiar to tropics. This is not a problem for Russia or America or Europe. And India has a large coastline going from Calcutta to Gujarat. And these coastlines have high humidity already. And as the temperature goes up, there will come a time when you will not be able to manage that heat. And this is a prediction that WHO makes. But this is nothing because this estimate they have made is, I would say, too conservative. Already in the European heat wave, 60,000 people died, 2003, not 20 years back. Okay? So this is going to be much worse than what predictors are saying. And the reason is because in most of the Middle East and India, we have a problem with moist heat waves in which both dry bulb and wet bulb have to look for. And there was a place in Middle East, in Iran, which reached a wet bulb of 34, okay, which is almost unlivable. Okay? And I don't know how many of you have lived in North India in summer. May heat is tolerable. One can drink a lot of water, put cold on your head. But come August, during a monsoon break, Delhi and Kanpur, where I have lived, is almost unlivable. Fan won't help you. Fan will not increase your operation because you're already having too much moisture in the air. So that is a challenge we have. And above a certain threshold, human body cannot dissipate its own metabolic heat of 100 watts. When that happens, there is no solution except air conditioning. So I would like to know how India is going to tackle that problem. Not today, but in 20, 30 years. And we have only 5% of the household with air conditioners, the richest 5%. 95% will not have access to it. Factories cannot be air conditioned on a large scale. People working in the field and in the construction industry, they won't have it. So unless we fundamentally alter the way of working, for example, agriculture may have done at night, work not in the day. When construction labor may have to work at night. So these things we have to start thinking about right now, because this is going to happen. It's not something which will not happen, it will happen, even if we manage to control the CO2 emissions. As a matter of fact, one remark which has not been sufficiently appreciated is there a textbook published by a professor in Caltech, Seinfeld. He said, even if you stop CO2 emission tomorrow, Earth's CO2 content will not reach pre-industrial value for 1,000 years. Okay, remember that. So we altered fundamentally Earth's climate. We have to live with it. We have to see how to manage. So this is a point I want you to realize. Already many industries on the coastal region, Calcutta, Bombay and Chennai, are right at the border of what is called critical zone. That is, when the humidity is high, 50%, temperature starts going to 37, 38, you reach a zone where it's difficult to sustain your body temperature. Okay? And this is there's some work going on in America with young volunteers to find out how long you can survive on a high humid condition. They have a room in which you do exercise and so on. So that shows is around HIF 40. But this depends on your genetic background. So I would like to see in India people do experiments with young people. Old people you can forget about, maybe our life is over. Young people, you should see how far they can sustain temperature of that magnitude, and maybe you are more adaptable than other countries. The accommodates better. Now this is data we generated from the ERFI data that a place like Delhi, the number of hours in which heat index exceeds 40, was around 100 hours in 1967 and got to 300 now, 3 times in about 50 years. So this is going up exponentially, not linearly. So after 50 years, they'll go around 6 times. So when you have 600 hours per year of very high conditions, you have to make a plan for it. Okay? So either people should not work in those periods, or there should be some provision. For example, an innovative way of thinking about this is that many years ago, not now, when we didn't have a heat wave, in Delhi in winter, poor people used to die in the streets because they were exposed. So the Delhi government made a plan. They had a shelter. So every night you go to the shelter and stay, and next morning come out. I think that was a good plan. We need a similar shelter for heat waves. We have to create shelters where poor people will go and stay. As a matter of fact, it's already happening. I found a very interesting story about one theatre in Bombay which is showing the same movie for 25 years. All of you know about it. Very popular movie. And you know why? Because that theatre has air conditioner. So people who are old and they give 20 rupees a ticket, that's all. Stay in the theatre for 2 hours, enjoy cool weather. So this has to be now made part of every day. This one, that there will be 600 hours per year of unbearable heat. The society has to make conditions for people to survive those times, and the working hours of people have changed. So all these things have to be talked about. As a matter of fact, ILO International Labour Organization has talked about it, but somehow they have not got enough mileage from the government. So the other thing I want to talk about is, fine, human beings, we can manage, we have our voting rights, we can make sure that the government does something. How about animals? All mammals have the same problem. Elephant, tiger, rhino, all of them will not survive. Okay? 50 years from now, because if the temperature becomes unbearable, where will they go? Tigers will not be able to hunt. And I hear already that many elephants are showing high mortality rate in the last few years, because as the temperature goes up, elephant cannot get to the heat. So this problem, I don't know what is the answer to that. They will, I think, have survival issues. Now already evidence came this year in May, in Mexico, monkeys just dropped dead from the trees because temperature went very high along with humidity. So this is already happening. This is going to get worse and worse in the coming years. Now the next thing is about agriculture, which we have to worry about. We are a country of 1.4 billion people. And this was a prediction made 30 years ago by Professor Parry, that because of climate change, developed countries will lose and developed countries will gain in terms of yield of crops. Okay? This was not something that really liked the news. And many of my friends who are agricultural scientists, they said we'll overcome that. We have genetic engineering, we have various clever ways to overcome this problem. I hope they do. But recent paper, this is an old one, there are two papers published. One talks about how India, Zambia, Myanmar, Egypt, Botswana will be the little countries facing adverse food insecurity due to climate change. Okay? And then there's another, this is a review by Jin Wong in 2018. But in 2017, French author said, our model predicts that continuing technology trends would counterbalance most of our climate change. Now, I'm not sure who's going to win. I'm sure a lot of work is going on in our IIRI to come up with strains which can handle. But this is a challenge we have to live with, because in tropical countries, we've already gone beyond the optimal point where yield is maximum. The crops you have developed for the last 10,000 years were based on temperatures which existed 5,000 years ago. Okay, we have passed that point already. We are already on the downward trend. Okay, so this issue is going to be tough. I hope genetic engineering will solve this problem. Now, the other thing is brought out by heat wave, which doesn't affect human beings, affects plants. So this is a work which published by Professor Vimal Mishra, who is here, that in the month of March, April, normally we don't think of heat waves in March, slightly high temperature, 3 degrees above normal, had a huge impact on agriculture yield in 2022. Okay, and I was not aware of it until I read this paper. And so, because it has such a big impact, ICAR published a very important report about the decrease in wheat yield in 2022 because of that heat wave, and they have to figure out how to handle much worse situation will occur in the future. Okay, now the next important issue which we have to face in India, because we are in a coastal region, is sea level rise. The sea level rise is rising 5 times faster than it did 1,000 years ago. Okay? The 1,000-year period you take and take the last 100 years is 5 times faster and rising very rapidly as Greenland melts and Antarctica melts and Arctic melts. Okay, so that worry you may not think much about, because the rate of sea level rise right now is about 3 millimeters per year. It doesn't look very large. Okay, but you must remember that it is occurring in a background of sinking land. Okay, and the sinking is much more than this. So I don't know why this issue is not being highlighted in India. Our problem is not global warming. Even if CO2 emissions stop completely and wonderful things happen, this will not stop. This is a local problem. This is one thing I find which is a very serious problem today. We blame everything on climate change. And we know that the majority cause is not us, but outsiders. It's very easy to blame an outsider, right? But there are many things which we are doing wrong in urban areas as well as in the coastal region. And this is one example. And for example, Bangladesh is sinking much faster because they are extracting gas from the ground as well as groundwater.
So they are sinking very rapidly.
So this only adds to that. This is already there. This problem is already there. Okay, and this is another threat increasing. So this issue is not being addressed by anyone, and especially Bangladesh should worry about it. If they sink at that rate, they will not exist as a nation. Now, same thing about Mumbai. Mumbai also, as most of you know, this whole city of Mumbai didn't exist. It was a few islands 100 years back. So many of these will start having problems with high rainfall and sea level rise. And Mumbai has another threat which is looking more and more possible. Normally, there's no history of a cyclone hitting Mumbai. Rajan, I'm sure there's no data. But there is clear evidence in the last few years, because of the warming of Arabian Sea, more and more cyclones are surviving and coming north, but normally they go northwest, okay? They don't hit Mumbai. But last few occasions, it came quite close. If a cyclone hits Mumbai, it will be disaster, okay? Now, one thing I must say that because of the advances made by IMD, the cyclone forecast is very good, okay? There is some warning. But, and for example, places like Orissa as well as Andhra Pradesh, the cyclone forecasting has helped us in preventing deaths. But the challenge in Mumbai is the cyclone forecast 2-3 days in advance. How do you shift 10 million people? You cannot, okay? That is not a solution to the problem. So I think people should think about how are they going to manage an area where you know cyclone is going to hit, but you cannot shift people, okay? And we had a similar situation 4 years back during COVID, okay? When COVID happened, the government closed down the whole country overnight and didn't allow people to go back. And there was a lot of criticism of it, but you must remember that if they had not done that, it would be much worse. There would be a huge rush and you could not have. So to me, how to evacuate people or not evacuate people in urban areas like Mumbai must be addressed in a more serious way. There must be some way to figure out how will you... See, in rural area, they have had a good solution all along the coast from Andhra to Bangladesh. They have shelters, okay, every 10 kilometers. That's a good solution. You shouldn't move people, you should move them to higher level. But how do you do that in Mumbai? I don't see a simple answer, but I'm sure people should examine this issue more seriously. Now, so this is a part about that's the west coast, this is part of the east coast, where the sea level rises 20 millimeters per year. It's relative. Remember that if land is sinking, you'll see in Hooghly a much higher sea level rise than in Mumbai. Now, of course, the other threat we already seen is GLOF, glacial lug outburst floods, and more of them will happen. And this one, Professor Kulkarni is here. He made a prediction 10 years ago that that particular lake will burst, okay? Warning had been given. But the challenge there was that in order to decant that lake, which is in a very remote area in Sikkim, it would cost 100 crores, okay? So the government was hesitant. I don't blame them. 100 crores suddenly you find to do that. They delayed it, and this is what happened. One whole dam was gone. Okay, and dam is worth, the cost 20,000 crores dam. So we have to think of new way to address these events. That you should spend 100 crores to decant the lake so that you save your investment 20,000 crores. That thinking has to go into our policy making. Now, this is something which has not happened in India yet. But when this happened in Canada, it really bothered me. In Canada, a glacier feeding two rivers retreated and one river was cut off. So one river overnight had no water. Now, none of you would have heard about it because this is a remote place in Yukon. Hardly anybody lives there. So it didn't pose any threat to human beings. Okay? Imagine this happening in India. One of the major rivers loses a source of water. There'll be millions living along that line. I don't know what you're going to do about that. But I asked Anil, but I don't know whether there are any real possibilities that some of the rivers will get cut off from their source and they'll stop flowing. Okay? So this is the example that happened in Canada. There are two rivers, one going into Pacific and one going all the way to Arctic Ocean, and when this glacier retreated, one of the rivers got cut off. Now we come to the last point about climate change, which is very frightening, which is tipping point. Okay, people have many discuss about tipping point, but all the discussion 10 years ago was on what in IPCC called high impact, low probability events. Okay, may or may not happen, but we have to think about it. Slowly, things are becoming more and more clear that it may happen more often. Okay, this is one of them. There's melting parts of the ice sheet affecting the Atlantic Mediterranean circulation. And these two are ones talked about, of which the first one is really the most worrying part. So this was a prediction made 40 years ago almost by a value broker. It's amazing that he made a prediction that the impact of CO2 on this circulation will happen earlier than our understanding of that. Okay, so that is the point he made, and he's right. Now there are papers coming out in the last few years saying that there is already evidence that this circulation is slowing down. Okay, but unfortunately, we live in a very strange world. Both Europe and America have spent a couple of $1 billion putting up wonderful telescopes in the space to understand the origin of the universe. I'm excited by it, very nice work, but we don't know our own ocean. Okay, we know a lot about what's going to happen 15 billion years ago, but we don't know what's going to happen in our ocean in the next 100 years. That is an act of stupidity. All of us are part of it, that we are more excited about the origin of the universe than our own survival. Okay, so this point is that people are now having some observation, but it is not good enough to predict whether that circulation which has slightly declined, is it a part of interannual variability or is it a long-term change? This is a life and death issue. It is not some academic problem. Okay, and the recent paper which appeared in PNAS said from a model which may have problems, we show that collapse of AMOC can indeed be induced by small amplitude changes in forcing if the rate of change is fast enough. This is an important clause which many people forget. All the studies we have seen of past climate, whatever work has been done, those changes are very slow. Okay, we are talking 1 degree in 1,000 years, 1 degree in 10,000 years. We are in a domain of 1 degree in 100 years. Okay, and nobody has looked at it. So these people showed that if you let the water melt fast enough, the trigger occurs earlier. But again, remember, this was a model. These models are not fully tested. They may be wrong. We hope they are wrong, because the consequence of this is so serious that it is not even worth talking about. Okay. Now, this is a comparison I want to make with what's happening today with our 1 to 100 years with what we know from the past. The Paleocene, Eocene temperature maximum, which occurred 50 million years ago, is very, very slow. Okay, it took 20,000 years for a 1 degree rise. Now we are doing 100 years. So we have to worry about these fast changes which we are inducing. What will it do? Now, I just saw before coming here a paper published by IITM on the impact of this circulation stopping on monsoon. And the result is so frightening, the monsoon won't come to India. It will stay over the ocean. Am I right? I saw the figure. If AMOC stops, essentially the whole of Europe will start freezing, interestingly, and India will start becoming warmer, but the IT season or the monsoon system will stay to south of India. That is end of the game. We cannot survive. The monsoon doesn't come to India. We hope models made a mistake, but models have problems. They're not perfect. But this is a warning to for India to convince, because remember that in this problem we are helpless. 94% of the emission is coming from outside India. We cannot do anything about it unless we can convince them. So we are stuck in a very difficult situation, but it's important we keep reminding people that the threat of AMOC stopping is not hypothetical. It is getting more and more real. Okay, and I hope more funds are given to make more measurements in that region. Okay. Now I want to end on this note. We just had a COVID virus 4 years back. Okay, and it was a threat to our lives. But this is a much more serious threat to our existence, all mammals. Okay, we had a vaccine to deal with COVID. There's no vaccine for climate change. Nothing is there. We don't know any simple solution. Okay, so this is a problem which must convince all our policymakers, politicians, and everyone to realize that we have already done irreversible change to Earth's climate, and if we continue to get distracted by wars in Gaza and Ukraine, we will all go together down. Okay. On that very unfortunate note, I will stop my. Thank you.
We have 5 minutes for audience questions. Anisha and Surabhi will be coming with the mic if you have any questions. Please raise your hand.
I'll take a question.
Yeah.
Is EMA collapse?
Yeah.
IPCC assessment is it's very unlikely by 2100.
Yes, but after that, many papers will come. After IPCC published, there are 4 papers. Yeah.
After IPCC maybe after 20.
And as you know, Krishnan, IPCC is always conservative. It is an organization which cannot take an extreme position by its construction,
Also,
right?
They were up to 2019, the papers that were.
Yeah, but I can tell you, you and I know, we have been part of it. In IPCC, this one, you always have to moderate your prediction because, yeah. So what I'm saying is, although this is a very rare event, the consequence is so serious
It's very
that we must tell that we have to do everything to stop it, right?
correct.
That is what I'm saying.
So the uncertainties are large. That is the
Yeah, because modeling assumptions are large, observations are weak, but what I'm saying is when you're spending $2 billion to put up telescopes in space, why can't you spend $1 billion on ocean research? Okay, you must convince the government on that. Okay, when he was there, they started an ocean program, but that is for exploiting ocean resources. I'm talking about research, understanding the ocean.
So one more thing regarding the monsoon and EMA. EMA definitely is going to weaken.
Yeah.
But also this carbon dioxide is increased.
Yeah,
Because
monsoon will become.
But the water vapor is increasing.
Yeah.
So that is kind of going to compensate the.
Yeah, but not if ITC doesn't cover India. You're right. If ITC comes over India, we'll get more rain, and that's already happening. Okay, but suppose it doesn't come over India, it's bistable system. It stands back. Then we're in trouble. So this is a rare event, but I think it's important for the young people to be made aware of it.
Sure.
You and I won't see it. I can tell you that. Okay, the young people they have to be made aware of that.
The EMOC can impact Atlantic multi-degree variability, can influence monsoon variability in an indirect way.
Sure. That's what we also said.
Yeah, so variability can be affected. It may not stop the rains, but it can change the variability of monsoon. I think somebody else also question.
There's also someone to the left here after them.
You are talking about the increased incidence of heat waves.
Yeah.
So at least the urban population, the use of air conditioners will increase enormously.
Yeah.
And impact our power.
Right.
Even our power. And even our buildings, many of the buildings that our architects are building
It's terrible.
are modeled after New York and. So why you should teach? I mean, the teaching institutions should teach our civil engineers or architects how to build buildings in India. And also, maybe we have to change our food habits to adapt to the.
Maybe. Yeah. But I can tell you, 20 years back, some of the people who built the IT buildings in Bangalore East, they came to me because I'm a heat transfer engineer, okay, at that time. So they said, how do you prevent this building getting too hot? Because they have huge glass. The manager has a beautiful glass facade, okay? I told him, you have made a greenhouse effect in your building, you cannot escape. And until it was interesting.
They are built in Ahmedabad.
Yeah.
They have air conditioning even at night.
Yeah.
They have to use air conditioners.
Yeah, so I can tell you this interesting example. This manager sitting in that glass facade, air conditioner maintains 20 degrees, you still feel hot because radiation is still trapped. So it's a very stupid thing to do, but he said, we are IT people, we have to be like Americans and Europeans, otherwise you won't get business.
For example, I talked to.
I have another question. Our even South Indians have started eating wheat.
Yeah.
How is wheat production affected by the warming?
What do you mean?
Is it a serious problem?
Which one?
That the warming in North India
Ah.
will affect wheat production. Wheat
Yes,
production.
Vimal Mishra will look at it. He will talk about it. You can ask him at that time. I'm not an expert on that. Yeah, it will affect definitely.
We have a question from this side, from Professor Mishra, I think. Mike?
Some years back, I was in St. George Fort,
Ah.
Chennai. All the historical sketches and photographs shows that the sea waves hitting the rampart. Now the sea is almost half a kilometer away from this St. George Fort.
Yeah.
What is the reason then? It is the sea is depleting there. Nowhere it comes to rampart now.
Yeah.
St. George rampart.
Yeah.
And 1850s photograph shows that it is almost inundated. And it has affected the rampart also, St. George rampart. But now it is almost half a kilometer away from St. George Fort in Chennai.
Yeah, that I don't know, because you must tell me when the photo was taken.
1850s.
No, remember, suppose there was around the time there was a tsunami. You don't know.
It is a regular sketches, artist drawings and also available.
Okay. I don't know. I have to ask. Anyway, CB Rajan, you can ask him.
I can share the historical book also.
Okay.
Where it is almost hitting, like just our western coast forts, where Calicut Fort,
Yeah.
it is continuously under the action of sea waves.
Okay.
But whereas on the Chennai, it is very surprising, half a kilometer away from the fort.
Okay. I don't know the answer. Okay.
Can I add a point to that?
Sure.
Yeah.
It reminds me that, I used to live in Trivandrum, and when we were younger, we used to go to the beach. The beach, Shangumugam beach, very famous. It was very, very large, very wide. And today there is no beach. The beach is all, actually the waves are coming all the way to the road. So my friends there tell me that it is because of the construction in other part of the ocean that there is no sediment deposition. There's only scouring. So the sediment is not being deposited. So what you might see locally might be the product of something else that we are doing somewhere else. That's just
But what is that? That he's asking what is, I don't know.
The sediment is not being deposited.
No, here in that case,
So
far
there
away.
could be sediment is being taken away. No, here the sediment is being taken away. So the beach building process. Yeah, the beach building process is affected by the wave action.
Yeah.
That's what I'm saying. Over the years, some things must have happened which either deposit or take away the sand. So in Shangumugam, the Vizhinjam construction has taken away the sand because of the barges and all that. So there is no beach. Yeah, so that happened. Over time,
It's acceptable. But here, I don't know, because just I went there as a civil engineer for fort renovation. But I observed that all the historical photographs.
It will not happen next year. It's not going to happen next year. We should move on.
Yeah.
We will stop with the questions. I request the Vice Chancellor to felicitate our speaker, Professor Srinivasan.
It's a book on climate change by Matt.
Thank you.
Thank you.
Thank you, sir. Our next speaker is Professor Ravi Nanjundaya, who is currently a professor at the Center for Atmospheric Sciences and the Devecha Center for Climate Change at the Indian Institute of Science, a fellow of the Indian Academy of Sciences and the India Meteorological Society, and recipient of the NVIDIA Innovation Award and the Sir C.V. Raman Young Scientist Award. Professor Ravi is specialized in the study of monsoon and its variability using climate models, application of high-performance computing for climate and weather-related studies, and the use of machine learning techniques for monsoon prediction. Professor Ravi will be speaking on studying climate with numerical and data-driven models. So.
Is it audible?
Yeah, go ahead.
A very good morning, and thanks, madam, for your nice introduction. And I would also like to thank Dr. Rajivan and Atria for inviting me for this for giving this lecture. It's a pleasure and an honor. What I'm going to talk about is a little more drier than the kind of action which you saw in JS's lecture. It was vibrant and it made you feel what's happening. But I am a modeler. A modeler is like a messenger. He can only tell you what's likely to happen or what's happening. But it's unlikely that he can change it in a very big way. So my only request is don't shoot the messenger. Okay, so I'm going to study about numerical and data-driven models. These days, the data-driven is like a buzzword. Everybody wants to talk about it. And more papers are coming out at such a rate that you can't keep up with it. So I'll talk about the more conventional method, the more sturdier and the most, you could say, understandable method of numerical models, and then follow it up with data-driven models. So this is the outline. I'll first give a very brief kind of a bird's eye view of climate system. I'm sure all of you are experts, but just for the younger kids, just kind of give a view of the climate system. Then we'll talk about dynamical models, which is like numerical models. Then I'll kind of say how we study climate change using dynamical models. Then, of course, right now we are not yet reached a stage in data-driven models to talk in a big way about climate change, but how these data-driven models are kind of evolving and what we could think of them, with especially their accuracy. And there's a new buzzword. Again, in data-driven models, the new buzzword is again digital twins. So I try to talk a little about it. And I must tell you that there's a lot of hype in it. When I searched the web, I could see only one good real paper from ECMWF by Peter Bauer. Rest everything is a lot of hype from various places. So I'll basically talk from that. And the latest is neural GCMs, which was kind of only last week. There was a paper in Nature about neural GCMs. So I'll briefly talk about it. So let's get on to it. So let's ask ourselves, how do we model climate and weather? If you look at climate, it's a multi-component system, which is where they are kind of co-evolving. You have the atmosphere. Sorry. So this is the pointer.
This one.
Yeah, this is the pointer. Yeah, okay. Thank you. So what we are looking at is a multi-component system which co-evolve together. So what we mean by that is you have the atmosphere, you have the ocean, you have what we call as a cryosphere, which includes sea ice, and you have land, and they're all interacting with each other. So if you look at the climate system, all the energy that we are talking of today in one form or the other is coming from the sun. And when these components are there, they co-evolve, as I said, they influence each other and are influenced by others. For example, when we talk of AMOC, we are talking of monsoons, which could be essentially an atmospheric system and its impact. But it's basically happening in the ocean, but it's affecting our atmosphere. So that's what we mean by co-evolving system. And you have other components also. Like over land, we could have flat land or mountains, so which also have an effect on climate here. For example, when we look at the climate of India, Himalayas or the Western Ghats, they play a very major role. So that's also, we have to look at that. And when we look at land and sea, and if you are looking at it in a fluid, mechanical or a fashion, then atmosphere and ocean can be considered as fluids, while land and sea ice, not exactly, but yeah, you could consider them as solids when you're trying to model them. And to study climate and its variability and change, we use what we call as Earth system model, which kind of has all these effects built into it. If you look at all the processes that are coming in when we are looking at an Earth system model, you have atmosphere, which is like a fluid, And then you have, sorry. So you have all the components. You have clouds, which impact atmosphere and also could impact ocean with through rainfall and all the linkages that happen. And ocean currents and salinity, they affect atmosphere. So all of them have to be put into effect. And we may also have to put in the ecological factors or the kind of mischief we are doing to the climate. That also needs to be put in a particular fashion. So that's what we call as a Earth system model. So finally, if you look at it from a physics or a mathematical point of view, what we finally get are a set of nonlinear partial differential equations. These are fairly complex because there are so many of these processes which have to be put together, and they all have to evolve with each other. For example, if there is atmosphere, you would have clouds, then you have to put in a kind of a model for cloud, which would tell you that, okay, this much of rain is going to happen. And as an aside, the biggest uncertainty we have in today's climate change is clouds and how we model them. That's still one of the major problems that we are facing today. Okay, and when we put such a complex model, we can't solve with pen and paper, unfortunately. So we need huge supercomputers. Today, in today's world, usually the biggest supercomputers that are there are being used for weather and climate. And especially when we look at IPCC, a large part of the world's biggest computers, including those at the Department of Energy labs in US and elsewhere, they were used to conduct these experiments. So you need huge supercomputers, and usually there is a kind of a smirking remark that the energy used by these huge supercomputers themselves could be causing a bit of climate change and global warming. So that's only as an aside, but the important information that we get from these supercomputers is massive, and that's the only device we have to kind of peer into the future and say, okay, this is the likely effect that's going to happen to the climate. So when we look at models, which mentioned models, you don't have to use the entire hierarchy. If you are looking at a very complex system, you could use what we call as fully coupled Earth system models, where atmosphere, ocean, sea ice, rivers, everything is put into it. If you are looking at a particular feature, you could have only an atmospheric GCM or an ocean GCM that you could be using. Then even, let's say you want to do some processes, you would come to something called as a aquaplanet. That is, you simplify it and say that the entire globe is covered with water. It's quite often used for testing ideas in a model. For example, if I have to look at how clouds happen in an atmospheric model, I kind of assume that beneath it is the ocean, and I do some experiments with that. Below that would be what we call as a radiative convective model, and simpler to that would be the energy balance models. And finally, at the bottom, this is not the least, I mean, it might look at the bottom, but this is one of the most important things that happened was the Lorentz model, which kind of introduced us to the theory of chaos. Using such a simple model, they could say that atmosphere is chaotic and there's a limit to predictability, etc. Using such a very simple model, certainly not with a complex model, but something very simple, they could come up with that idea. If you go on the other leg, then you have the reanalysis products. That is, you take data from various sources, from satellites, ground data and all, and create what we call as a reanalysis. Today, it's one of the most important inputs or tools that we use to build models. And if you look at data-driven models, most of them are built on these reanalysis products. Whichever you look at, GraphCast or ForecastNet, etc., they all use data-driven models from reanalysis. Then you have a machine learning emulator of a GCM. It's still kind of, you could say in some sense, an infancy. And then you have data-driven models, which could be catastrophe models. Let's say for high impact events, you would have data-driven for that. And also for regular weather forecasting, you could have a weather model. So this is the kind, you could say, a hierarchy of models that you could use. And some of them could be for, let's say when you're looking at climate change, you would be looking at the most complex model that we would be interested, which could be a fully coupled Earth system model. So these are the components of a climate model, which is in a very, very kind of an abstract sense. You have atmosphere, ocean, ice, and land, and they all have co-evolving together. And in a model context, we kind of link them to each other. That is, they talk to each other through what we call as a coupler. So, and if you look at interactions a little more, you know that ocean forms an important part. And for climate, it's like a flywheel. It kind of modulates the temperature changes. If it was just let's say a land-covered Earth, the temperatures would have been much larger with all the CO2 we are putting in. But this acts like a flywheel and kind of modulates the temperature. And it's also a major source of moisture. If we are looking at rainfall, all the rainfall, in some sense, moisture is coming from the ocean. And also circulation in the ocean can play a role. I'll not go into the details of it. But if you're looking at it from a climate point of view, ocean also acts as a major carbon sink. That is, all the CO2 that we are putting in is also a substantial quantity of it is being absorbed by the ocean. Land-atmosphere interaction. There is also interaction between land and ocean. Land, unlike ocean, has a low thermal inertia and can heat up more rapidly than ocean. And friction from the land can also be important. These all need to be put into when we talk of a model. I'll not go into the details of it. Again, for the lack of time, I'll just skip it. And the presentation would be there. Those who are interested can look at it a little more. So now we come to Earth system models. So in a very gross sense, this is what we are looking at. You have the atmospheric circulation and the radiation, which is kind of forcing it. Then there is chemistry happening. Supposing you want to know how CO2 is going to change dynamically, you would need to put that particular chemistry. Let's say the NOxes, which are also pollutants, or this one, surface sulfur dioxides, aerosol, and all. So you have to put in chemistry into the model in a very simplified sense. So these are called as atmospheric chemistry models. They are extremely time consuming as far as computation is the requirement, but it is important. Even today, we don't have very good atmospheric chemistry model built inline atmospheric chemistry models. They are still very simplified, and maybe in the next IPCC, you may find much more online chemistry models which are coming into the picture. And then you have sea ice, which interacts with the atmosphere, and also ocean and ecology and biogeochemistry. These are becoming more and more important because human impact is going to be felt both on the ecological sense and the biogeochemistry, and they themselves can have kind of feedbacks into the atmosphere, into ocean as well as atmosphere. So all these things need to be put into your Earth system model. Then if you come to land, you have the plant ecology and land use, which is very important, and land physics and hydrology. So today's model, when we talk of the IPCC kind of scenarios, these are all the processes that need to go into your Earth system model. So having had a very, very gross view of what an Earth system model, we ask ourselves, how do we study climate change using Earth system models? So the biggest uncertainty is how do we peer into the future when we don't know what's likely to happen? So IPCC came up with some scenarios which are called as the SSPs. This is the SSP 5, which is fossil fuel development, lots of what is like business as usual scenario, which I think some of the politicians in US would love to see. Then is like a SSP 3, which is like a rocky road. There is regional rivalry. It almost looks like what's happening today. You have rivalries all over, and if you look at it, whether you like it or not, in some sense, it's oil that is driving all these rivalries. And middle of the road, where you take some mitigation, which we may more likely to follow, is the middle of the road SSP2. SSP1 is where you are a saint and you go for a highly sustainable one. Personally, I don't believe that it will ever happen. And then there is a lot of inequality, which is there in the SSP4. So there are various scenarios. So when we talk of here, if you look at it here, you have this SSP 5, 8.5. 8.5 means the amount of energy that would be, or radiative forcing that would be there in 2100. So this is the worst scenario, where if you are putting in something like 120 gigatons of CO2 per year, you are likely to reach the SSP 8.5. A little more better scenario is SSP 3. And finally, we come to SSP 1.9, which is very unlikely that we'll ever achieve it. I think we've already overshot what we would have done in the SSP 1. So, and these are the various contributors which IPCC uses to say, okay, these are the scenarios that we are going to use to kind of predict climate change. And now, up till now, we have had models which really didn't take into account how human behavior could change. Supposing you have an Earth system model, if you could say that, okay, I'm going to change the way I use energy or something in a dynamic fashion, in a kind of interactive fashion, then we'll come to where you have a regular Earth system model here, and what they call as a GCAM or a human system model. And the two would be linked. This is what they call as the E3SM of Department of Energy. And it's still kind of being worked out. I don't think quite a bit of this right-hand side is being done. Maybe some components of it is done. That is fairly stabilized. And when I talk of digital twins, I'll again come back to that and say how the interaction can occur in that. So these are some of the details of the E3SM, which I'll right now skip. One of the major uncertainties when we talk of climate change, we say that, okay, there's going to be climate change, but what are these uncertainties, even if you're looking at from a modeling point of view? In actual reality point of view, we really don't know. But if you look at within our Earth system model, there are various uncertainties which we need to look at. Some part we call as the internal variability. We know the climate model itself, the climate itself has an internal variability. For example, you're looking at PDO or other kind of variability. We know that even if you're looking at something as simple as the Indian summer monsoon, there are periods when there are very few droughts, and there are periods where there are a much larger number of droughts. So that is the kind of internal variability which already exists in the climate system and which the models need to reproduce. Then, of course, we know that our models are not perfect, which is the scientific uncertainty. For example, we know that clouds, as I mentioned previously, these are the biggest source of uncertainty. The way I put clouds, I can flip the result that can come from an Earth system model. I can make it go from one scenario to the other just by using some parameters within the clouds. And it's one of the weakest things, and a lot of work is being done to improve this cloud parameterization, but that's one of the uncertainty. But as you go along in time, you find that the scientific, could you make it full screen, please? Yeah, next, okay. Oh, sorry. Okay, so you have the scientific uncertainty. As you go forward in time, this uncertainty would always be there, but its impact becomes less and less as we go into the future. The biggest uncertainty would be the scenario uncertainty. We really don't know what's going to happen. And as you go further and further in time, the scenario uncertainty becomes more and more important. In the immediate future, let's say if you're looking at the next 20 years or 10 years or 20 years, the scenario uncertainty, that is the changes which we are looking at scenario, the way CO2 or other greenhouse gases are increasing, that may not play a very major role. But as you go further and further, the way we behave and the way the scenario kind of unveils, that could have a very major impact on our climate projections. And I would say that in future, that's the major uncertainty. And that's where I think the human GCM, which E3SM or the Department of Energy is talking of, you could easily kind of, when you do a scenario on the fly, you can change the scenarios and see how let's say if you are looking at a very bad path and then you say that, okay, I'm going to make it important, then on the fly, I can change it and get better scenarios for that. So that's one of the ways you could look at it. And let's look at climate change. I'm sure quite a few are already familiar with it. These are the various pathways. And I'm more used to clicking my own laptop rather than. Huh? Yeah, this is the right one. So there's a lot of talk about 1.5 degree change. And if you look at various scenarios, they will happen earlier and earlier if you go towards the right-hand side. And if I look at today's world, it's very unlikely that we will have already overshot, if you look at last year's temperatures, that we have already overshot the 1.5. Though, of course, officially, I'm sure the data is much more robust. But if you look at last year, what happened last year, which could be a kind of a blip on the overall trends, you do find that it was about 1.8 degrees. That means, in a sense, at least for the present last year, you have overshot by about 0.3 degrees. And these are the other scenarios where you would reach 2 degrees centigrade, which in 2.6 may not occur. But if you're looking at some other scenarios like SSP2 4.5 and all, these are the timelines over which they will occur. And if you look at the worst scenario, that is 4 degrees, that's likely to happen by 2075. That means compared to the pre-industrial world, it would have heated by about 4 degrees. That's the most frightening scenario. And we don't know whether we are kind of heading towards it if we are not doing any sustainable actions. So this is how the global temperature would change under the various scenarios. I'm sure all of you are familiar with it, so I will not spend too much. And if any of you are interested, you can play around with different scenarios in this link that is provided. You may find it interesting to play with it and see how the temperatures change. And this is the current status. And this is how the temperatures since 1940 as compared to the pre-industrial level. And if you look at today's values, we are at 1.78. Of course, it could be an outlier. Maybe next year, because of a lack of an El Nino, since El Nino will not be there, temperatures might be cooler. It may not hit the temperature that we are looking at, but the warning is already there that either we have hit 1.5 or we are close to hitting it in a long-term trend. This is, of course, a year, only year-wise we have seen. If you look at a long-term trend, the warning is that it could hit 1.5 soon. And as I said, 2023 shattered all previous records of temperature. And if you look at even this year's data, I think it's still kind of, records are still being shattered, not just in Olympics, but even in climate. So now we have talked about how we study climate using numerical models. Now, we know that there is a lot of data coming in. So data-driven techniques are also being used to study climate. So if you look at the amount of data that is coming in, it's huge. For example, if you look at ECMWF, it has archived about 450 petabytes of data. And every day, about 300 terabytes of data is being added to its repository. And if you look at data availability in all sectors, not necessarily in climate, but a lot from other domains, you have, for example, Ola here kind of mines a lot of data. It includes climate data also, like, for example, weather data in its own, let's say, its AI engine, Krutrim as they call it, because now they are kind of employing climate people with climate background who could kind of help them with immediate weather and its impact. So that means a huge amount of data is available, and these are kind of forcing people to look at newer and newer algorithms which are more efficient to kind of do better techniques when it comes to climate. That is, just as we used the increase in supercomputing to get better models, now the increase in data and the techniques which are coming out from commerce, we can use it to get better and better data-driven models. So, and of course, as the change in HPC, the high performance computing happened, today the GPUs are kind of accelerating how we can use data-driven techniques. And it's a major, you could say, game changer when it comes to data-driven techniques. So this is a slightly fancy, you could say, slide. Of course, it's, I think, from NVIDIA. And it shows how the data model size has changed with GPUs and how the data growth has happened and growth in scientific data. Unfortunately, they have not put a y-axis, but from 2010, go to the next. Okay, I'll go to the next slide. Not a problem. So it's basically the GPUs which are kind of driving the revolution in some sense. And this is a jazzy slide from NVIDIA, which I will skip for the present. So if we ask ourselves, how could we use data-driven techniques? One could be for predicting weather and climate from past data. This is what presently being done. All the hype that we are talking about, GraphCast, Pangu Weather, ForecastNet, these are like where you use data from the previous ones, either to predict climate and or weather. We could use these data-driven techniques because we have a lot of past forecasts also which are available, and use it as a data-driven technique with algorithms which can improve the present-day numerical forecast. That is, you get a numerical forecast. You have past data of the errors that the model has done. Now you use it and do what we call as a bias correction. That could be one. Third area, which is a much tougher area to use, is what we call as a hybrid model. For example, if you're looking at clouds, right now if you're looking at a cloud parameterization, it is based on some experiments which were done, let's say in Atlantic, like GATE experiment, and they have developed cloud models based on that. Obviously, we know that the clouds in Atlantic may not be the same as in over India, but now you have data from various sources, satellites, etc., which you can use. Being a data-rich problem, you can use an AI/ML module. Based on AI/ML, you have a module which kind of fits into your conventional model. Let's say a numerical model. So you're kind of marrying both a numerical model with an AI/ML model, which we call as a hybrid parameterization. And of course, the buzzword these days, which is developing a digital twin for weather and climate processes. So this is about predicting weather using data-driven models. I'm just giving an example of GraphCast, which is from Google. There are others like Pangu Weather, which is by the Chinese. They have one of the best AI-driven models, and ForecastNet, which comes from NVIDIA, and actually is being now used as a forecast tool by Taiwan for their forecast of cyclones, typhoons, etc. And since it's a data-driven model, it essentially goes on the European reanalysis data from 1979 to 2014 at 25-kilometer resolution. And it uses a encoder and a decoder. If you look at it, this is the encoder, this is the actual processor, and this is a decoder. So in simple terms, you have data coming from various sources, which you kind of encode as the model requires. The processor kind of looks at all the relationships and develops a output in some sense, which is kind of used by decoder to give you a result in the form that we would be interested in. Let's say we look at a forecast at a particular place. This data would be taken from, let's say, IRAF or any other source. Then all the relationships are built within the processor, where you have all these GNN and all other techniques that every day they come, new ones come, which I should say that I don't know. I've heard of things like GAN, but all I can do is Ghana. I can't do GAN. Okay, so every day a new technique comes out, but that's what they do. I mean, if you're looking at in abstraction, this is what is happening. That is, you have data coming in, which you convert in the way the model looks at it, or the data-driven model looks at it. It bends up the relationship and then converts it into a data form, which we can understand. So these are the other details. The interesting thing is, you need a lot of energy and time. Energy in the sense of actual energy. People say that if you use a data-driven model, you'll get a forecast within a minute, even with a PC. Let's say comparable to the kind of skill that ECMWF gives. But what is behind that, we rarely talk about. The amount of energy being used by all these AI/ML data centers is huge. And again, as the joke goes, to study climate change using AI/ML, you're kind of contributing a lot to climate change. So, but we have to keep in mind that these are tools which are very good. And as far as any general person, if I sit and look at it, I can kind of look at a forecast, a particular variable that I want to look at the click of a PC. I don't have to go to a huge supercomputer. The data is already there, or in some sense, the models are already available. I just use it the way I want it. That's the advantage that we have, which we may not have when we look at a conventional forecast coming out from numerical models. It doesn't mean that numerical models are obsolete. As we just will see, numerical models still have their own role to play. But these data-driven models kind of help you to kind of create things. Let's say I want to do a hyperlocal data-driven model. I take forecast from, let's say, ECMWF, then add some other data that I have and build another data-driven model just for temperature in Bangalore, or, I mean, which I cannot do is, which I cannot do is traffic in Bangalore. I cannot predict it. Even God may not be able to predict it. So this is about that. But what it means that we can use it as a viable alternative at a very low cost if we neglect the amount of energy that's used. Okay, so these are the skills. What I would like to say is that, okay, the skills are comparable for the GraphCast model, and the HRS is the ECMWF. So these are the various parameters. I'll just skip through it. And even for cyclone tracking, you can see that the errors are comparable with the ECMWF. This is a more striking one. This is about the Hurricane Beryl, which hit last month, I think, in early July. ECMWF on July 1st gave this particular track. GraphCast with 1st July data gave this, and NCEP was somewhere here, and this was the actual path. So ECMWF could not get the track correct as early as 1st of July, which GraphCast could do. I mean, this is just only one example. I'm sure there are counter examples which can be kind of produced and say that, okay, this did better and that did better. But what I would like to show is, okay, this could easily be done with a data-driven model, which is already being trained. So anybody could use the data at that particular resolution and create your own forecast. So that's the power of data-driven models. And these are some forecasts which one of my students, Karan, looked at it and see how actually good the forecasts are. I mean, for us, the interest is rainfall. And when it does very well for the global parameters they talk of, here is an example of rainfall where we compared just for 5 days between GPM and the forecast net. At the end of 3 or 4 days, it was nowhere near what GPM was giving. So, I mean, this is only a very small example. I wouldn't say that we have done an exhaustive analysis, but we propose to do it in later time. It shows that there are serious problems when we are looking at, especially if you're looking for Indian forecast where rainfall is important, this could be a major problem. And I think it might need to be addressed in a better fashion with data-driven models. This is another example of the work that he has done. And we did some our own forecasts with a very simple model just on a PC. And we could get a very good forecast with what we called as stacked encoders using just 3 or 4 predictors, which was atmospheric temperature, SSTs, and sea level pressure. And the skill that we got, or the accuracies that we got, were extremely good and kind of comparable, or let's say better than the numerical models which is being used. I'll not go into too much of details of that. This is a digital twin. And this is an overview of digital twin. Basically, it combines physical model with data and uses data assimilation for that purpose. It combines simulations and observations at a much greater scale. That is, if you need hyperlocal for forecast, you can do that. That is, on a global scale, you have kilometers, you have hectometers on a regional scale. And now one of the things you can do is to monitor and predict up to decadal scale, both natural, for example, you are looking at volcanoes, or anthropogenic perturbations. So this is what you can do with a digital twin. These are other details you have, and it could be used by various sources, which could include reinsurance companies looking at a future scenario, and that means they can do better risk assessment for that, and forecasters and farmers and etc. etc. They can use data from these digital twins. So now I'll come back to what the EEC 3C is. If you look at a conventional model, this is what you have. Sorry. This is what you have. I mean, you're fixing all the inputs and you're getting a model. Now, if you include the human GCM, in a sense, we are kind of interacting, which is what the digital twin does, is to interact with the, let's say, with data or with a data-driven model or a numerical model. A digital twin has a numerical model built into it. So this is what is, in some sense, is nothing but a digital twin for the climate change models. So this is, I think there are other details which I'll skip for neural GCMs. I think I'll skip up for the present, and I'm sorry, running late, so I'll come to the summary and I'll leave it to any other questions if there are any, or if it is possible. Sure. Okay.
Of late, we have been hearing something called as a cloudburst. So, can you explain clearly that what are the scientific reasons for the cloudburst, and why we are unable to predict these kind of cloudbursts in advance, or even forecast in advance? So we have a low Earth orbit satellites, right? They exclusively meant for the monitoring this kind of aspects. So IMD says that we are unable to get the data in time. That's why we are not announced in advance. So a lot of people are losing their lives.
Okay, I fully understand the importance of the question. But if you look at a cloudburst, strictly it is a very hyperlocal event that can happen. Or let's say it's like a tornado. Let's say it's not a tornado, but I'm giving an example. That is, it could be 1 kilometer in size. So most of our models are still running at about 2.5 kilometers, and you may not have the local information. Even if I run at a hyperlocal, I may not have enough information to give you a cloudburst. But depending on the conditions, we can always talk of a probability of a cloudburst. But to exactly say that whether the cloudburst is going to happen over Atria or is going to happen over IISc, we can say it can happen over Bangalore, but we cannot say that whether it's going to happen in this place or that place.
It's happened in Uttarakhand, it's happened in the Wayanad recently.
Yeah, but see, it's a very hyperlocal phenomenon. And there are still problems with models. They are not perfect. We are working towards it. You look at very high resolution models, and then you can say there is a high probability of intense rainfall happening. And the problem with most of the models is, if you look at numerical models, they do not give the kind of rainfall that you actually observe. There are problems with that. I mean, they can tell you, okay, there is a high probability of rainfall happening at a particular place. But I cannot say that whether rainfall will 10 millimeters or 100 millimeters of rainfall will happen. Let's say Wayanad, let's say it happened 1 meter of rain. It would be very improbable that we could capture and say that let's say 1,000 millimeters of rain happened in 24 hours. That a model will not be able to capture because it has a very coarser resolution, and there are processes which we are not able to include in it. People are working on it, but we are still some distance to go. I mean, I know it doesn't satisfy you, but that's the state of the art. Yeah.
I just had a small question. Thank you so much. I really enjoyed this because data-driven models weren't a thing when I was studying, so it's also new, very new for me. I had a question around, I think, issues of access. So there are the Googles and the NVIDIAs that are sort of driving some of this revolution. What happens in countries like India? Is there a push towards developing some of this expertise here? Because from what I understand, I think it also takes a lot of money and certain kinds of spaces that you have to create for chips and so on, which perhaps that capacity is not in India. So I'm wondering what is happening in this data-driven model space in India and our capacities.
Okay, there are two parts of the question. Hardware, yes. I mean, for the present, will not be able to reach that. India is making its own chips, etc. That's some distance away. But when it comes to algorithms, let's say AI-driven algorithms, for example, Ola has come up with Growthrin, which is like, again, a data-driven engine. So people are working towards it, looking at new algorithms, and even within Ministry of Earth Sciences, there is a drive to kind of encourage use of AI and ML for weather forecasts. I mean, there is a program for that also within MOEs. Okay. Yeah.
Hi, you talked about the environmental footprint of AI and ML data-driven models, the computing footprint and the heat footprint. You mentioned the same thing when you're talking about numerical methods.
Yes.
I'm wondering if there is a statistical difference between the two, or they all consume more or less the same energy, assuming that the problem statement is fixed.
Yeah, okay. I tried looking for that data, but I couldn't get it very easily within the time that I was looking for it. I'm sure there is data available. Let me say the major differences. If I have a forecast, I cannot generate a forecast with a numerical model. They just give you the forecast. But if let's say I use a data-driven model, let's say I use GovCast or ForecastNet, or let's say India comes up with its own model, I can do a hyperlocal kind of a thing sitting on my PC for the interstellar. For that it is very energy efficient. But when it comes to the training, the biggest thing is in the training. You need huge amount of not only data but energy. They are energy intensive, which people don't talk about it. But then energy intensive in every part of AI/ML, including Bitcoin mining. It's mind-boggling, and sometimes I don't think it is really required, but people use it, so I cannot say about that. Okay, thank you. Yeah, yes, Vaibhav. Oh, okay. Prosecution, Keshav. Sorry.
What about seasonal prediction of monsoon?
Yeah.
What is the status of this AML? And because we are still regarding numerical models, short range, up to 1 week, it is excellent. I mean, things have improved very much.
Actually, for seasonal forecast, yeah.
What about seasonal prediction?
Yeah.
Month and
sure.
These AML.
Actually, one of the results for lack of time.
Any skill, or what is the status?
Sure. I mean, actually, one of my slides had it. For lack of time, I rushed through it. For seasonal forecast, AI/ML techniques are kind of beating numerical models. But it's only if you look at all India or regional scales. Extreme events is a much tougher question. I have not yet looked at it. But when it comes to seasonal monsoon, yes, certainly. Yeah, all India summer monsoon, we are easily able to say that it's with the accuracy which is better than numerical models. Actually, one of my slides had it. We did it with ourselves with just a PC, and it showed very good results. Yeah. Thank you.
Thank you. Thank you. I request Dr. Nagesh Vangala to felicitate our speaker. Sir, Professor Ravi.
Oh, I thought I was done.
Atria University would like to share with some delightful news with everyone present here. A member of our academic board, Dr. Umesh Varshney, has been felicitated by the Government of India with the Vijnana Shri Award, and we would like to share this delightful news with us. As announced, I would request for a chair to be placed here on the dais, please. I request the Vice Chancellor to felicitate Dr. Varshney.
So, Vijnana Shri is almost like a Padma Shri for and besides. So, we are lucky that he's an advisory board member. Yeah, you be seated. I think it's that you should sit. You all have to stand. Within the front, this one. Yeah. So all the best. Thank you. Thank you.
Thank you, sir. Because of the slight delay that we are experiencing in the schedule, we've interchanged the next couple of speakers. We had Dr. Krishnan coming up because Dr. Harini would have to leave a little early. We are going ahead with Dr. Harini's talk, and later we will resume with Dr. Krishnan's. Let me introduce Dr. Harini. Dr. Harini Nagendra is the director of the Research Center at Azim Premji University and leads the university's Center for Climate Change and Sustainability. With over 30 years of research and seminal publications on forest conservation and urban sustainability, and several awards, with the most recent being the Clarivet Web of Science Award, Dr. Harini is an elected member of the World Academy of Sciences and the Indian National Science Academy. Her interdisciplinary work on forests combine remote sensing, biodiversity studies, and institutional analysis, and is recognized for elucidating the link between pattern and process in the human-dominated landscapes of South Asia. Dr. Harini is on Stanford University's list of the top 2% cited scientists in the world. She is speaking on climate change impacts on cities and urban landscapes and India.
Thank you, everyone. Specifically, thank you very much to Dr. Rajivan for this invitation. It's a pleasure to be here. And my slides up. My slides? They'll come? Okay, should I just... Yes. Oh, you need that. Yes, yes, of course. I think this mic should be fine for me.
For the recording.
Oh, for you.
Yeah.
I'll just hold it.
I think you can keep it.
Let's keep it here. Sure.
That's okay.
Okay. Another mic? Okay.
Is it clip?
Okay. Can you do this?
Yeah.
Yeah. Should work? I think so. Yeah, sure. This works.
We can
Clip it? No, I think it should be fine. I'm not going to move around. Well, I hope you can hear me in the back also. Yes, right. Thank you. So it's a great pleasure to be here. And once again, thank you for this invitation. I think the last few talks have been very interesting, and I wish I could attend the afternoon session, but I have to leave. So again, thank you for doing this change in the sessions. I'm going to talk about climate change impacts on cities and urban landscapes in India, specifically looking at the work at Azim Premji University for the Center for Climate Change and Sustainability, which we set up in May 2019, and which as of 1st September will become a School of Climate Change and Sustainability. So, and this is a work of a slightly different kind because this is a university with a philanthropic mission, and as I'll talk about it, a lot of this determines the focus that we have on climate change and sustainability. This is a slide that many of you might be familiar with. It's a nightlight satellite image of the world, and it gives you a sense of where the urban landscapes are, and you can see that India is especially very lit up. India, China, many parts of Africa are very fast urbanizing. And you see, if you look at this UN graph, that the growth of cities from 1990 to 2014, even to now, in fact, is dominated by the oranges and the reds, which are the cities in the global south. Right? And these are the cities that are growing fastest and also the largest. So India contains 3 of the world's 10 largest cities. India also contains 3 of the world's 10 fastest growing cities. It's not just India, of course. You have China that is urbanizing very rapidly. And surprisingly, or maybe not so surprisingly for some of you who would know it, is that can anyone guess the 3rd fastest urbanizing country in the world? India, China, of course, being the first 2. Nigeria. So one wouldn't think of Nigeria as urban, but it's very fast urbanizing. And the challenge now that we have, if you're trying to plan for an era of urbanization in India, in the era of climate change, in the era of the Anthropocene, is also the era of the urban in India. This is a very different India from what we thought of. All of us growing up, 90s, 80s, 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 learned in school textbooks that India was 27% urban, 30% urban. Now it's 33% urban. But very shortly, by 2050, estimates say, depending on your definition of urban, that India is going to become anywhere between 50 to 60% urban. That's a dramatic shift for a country that is always thought of itself as an agrarian, rural country to become an urban country. But what is this urbanization that India has? It's very different from countries in the West. Extremely densely populated, yet you have patches of nature surviving and very strong cultural, social connections to nature. Again, this is another nightlight satellite image, but this is a multi-date image where blue is lights on and pink is lights off. And this is just a comparison I just wanted to show you of areas of parts of India with parts of the US. And you have a lot of shrinking cities in the US. You have a lot of shrinking cities in Europe. And if you look at the papers on urbanization there, they're dealing with a very different set of issues, how to make cities sustainable when industrialization is coming down, when depopulation is happening, when crime rates are increasing, and cities are getting hollowed out. Whereas there's almost no part of India which is facing deurbanization. In fact, the only parts that are not facing urbanization as much is central India, because you have a lot of the protected area network, and parts of the Thar Desert. Even the Northeast is now very fast urbanizing, right? So we started looking in this paper, Nature Sustainability, looking at the urban South, the global South, and the predicament of global sustainability. And we found that the growth of cities in the global South has always been higher than the global North, even from the 1970s onwards. So it's not only now that these cities have been growing faster, they've always been growing very fast. And this is not just endogenous change, this is migrants coming in from across the country. And of course, they come to cities for two reasons. One is desperation, because the loss of climate change and other human factors are making their villages uninhabitable, but also the prospect of growth and prosperity, which cities do hold out. There is creativity, there are possibilities of economic growth, there are other possibilities of advancement. But at the same time that you have these global South cities facing very rapid growth, they're facing a very different, a very challenging social and economic and environmental context for governance. For instance, they have very high under 5 mortality rates, very low percentage of internet coverage, which you would need for certain kind of programs like smart cities, very high rates of crime, very low rates of education, very low rates of sanitation and sewerage, very high rates of air pollution. And you can see this is again UN data that we put together. Not just is it very different between the global North and the global South, but there's a lot of regional differentiation. Asia has its challenges, Latin America has its challenges, Africa has its completely different challenges, which means you need to study all of these places very differently. Especially for India, it means, I mean, these are some of the statistics. By 2050, India is supposed to have 60% urban population, slice it, dice it however you want to. It could be 50%, 60%, it's going to be very high. Some estimates again say we're going to have 415 million people added to our cities. 1,800 people even now move to a city. Writing the papers. Where are the lead authors coming from? 70% come from the US and Europe. Right? So 369 out of 1,000 from Europe, 343 from North America, that's 70% done. Another 20% come from China on China. What do we have left? India accounts for, or authors, lead authors from India account for 10 of the top 1,000 cited papers on global sustainability, on urban sustainability. Other India-like context, South Africa and other cities that we could draw from, another 50. So 0.5% is what we're accounting for. If you flip this around, I don't have the slide for this, but if you flip this around and say, what were these cities focusing on? This is just the lead author. And you can argue that maybe there's a lot of work done on Indian cities by people who are not from lead author, not from India, but originally from the country. About 50% of the top cited papers are global analyses. But again, when you leave the global analysis aside, there are very, very few papers that talk about Indian cities. So we almost have no data on Indian cities from the urban sustainability perspective. And yet, here we are trying to design these cities, adapt these cities, look at how to engage with these cities from a completely data deficient perspective. Which is why, for instance, when we look at smart city programs or other kinds of programs, how do you deal with these issues when you don't have internet penetration, when you have very low levels of education? You can't simply take data from a different context and apply it. So this is a very recent opinion piece of ours that came out 2 weeks ago from the Climate Center, where we talk about the issue that we need climate data democracy for urban action, for climate action, and I'll explain what I mean in a bit. But since this talk is specifically focused there's a lot of technical issues that underpin this. How does a regular citizen or a journalist or a parliamentarian understand, even if you make the data access open, how do you understand how to use it or interpret it and use it for action, for adaptation? So we argue then in the paper that academia needs to take the role on this. We have several advantages. Firstly, that we have the knowledge and the capacity to learn. Nobody is using this kind of data to tell policymakers very basic answers to the kinds of questions they need. So that's one kind of data. The second is, what kind of data do policymakers need for planning? We know that cities will grow, but what is going to grow in cities? Most of the city growth is going to come from informal settlements. And a lot of them will be tin shack roofs or plastic roof tents. We're going to have cases of heat island effects, water pollution, flooding and air pollution, and the worst affected will be these kinds of informal settlements which have no way to adapt. So we started with a few analyses. For instance, again, this is just work that is in review right now, looking at Bombay and flooding in Bombay, and which areas are most likely to be flooded under different climate change scenarios. And we find that the projected population atlas just for SSP 2.45 is going to be 3.4 million. And if you look at these models, between them, they have a range of $29 to $32 billion just from a single incident of flooding. So storms in Mumbai, because you have the financial district there. And this again, this kind of data could be very valuable for policy. There's a lot of health effects of the combination of heat and pollution. And again, these are being studied in somewhat in isolation. Environmental scientists are looking at pollution, health people are looking at heat. And no one's looking at the two. But if you look at the anomalies, what you see is that in this part, central India and the Indo-Gangetic plain, between 1998 and more recent years, you'll see a huge amount of increase in both PM 2.5 and heat. And this combined effect has unknown impacts on heat or unknown impacts on the human body. There are some indicators, especially from analysis of China. If you look at humidity, we all know that cities on the coast are more humid than cities in the interior. However, increase in humidity in cities cities in the interior are becoming more humid faster than cities on the coast. So the increase in humidity in cities in the interior is faster. And this is interesting because it's not just relatively, humidity. Heat stress is a problem, and you need to combine issues of heat and humidity for heat stress. But cities in the interior were never built to deal with humidity. High humidity is what people on the coast know how to live with. Their ventilation, their buildings, their architecture is built for that. When you start having interior cities with high humidity, this is not something we expected from our analysis, and it's giving us thought. So it's something we need to look at much more. So again, the kinds of things that we're thinking of from the perspective of how does a policy maker use this to adapt to cities. A third factor we're looking at is how do you increase data accessibility. So for instance, we're looking at land surface. This draws on the workshops we've been doing with senior journalists. And journalists often say that when they want to write a story, and the fourth and the final, we've been investing a lot of our time on environmental data communication, because communicating environmental data to the wider public, especially teachers and students, has been a hard challenge in India. So for instance, there's my book, Nature and the City, which talks about the ecological history of Bangalore, the deep ecological history over 1,500 years. But there are also two books that my colleague and Seema and I wrote on trees, issues of trees in Indian cities and issues of water in Indian cities, which we find now a lot of classrooms and colleges, whether architecture colleges or design colleges, are using in their classrooms. We did not anticipate this, but it's interesting. Games are now being created around trees. Our idea was that this is important for the English-speaking community in Bangalore, not for the Kannada-speaking community, because they would know already what to harvest. But it seems like these traditions are disappearing very fast. Right? So this is another very common question we get asked. What trees do I plant? And we simply can't answer these questions again and again with one real estate developer, one gated community, one apartment complex, one road planner. So we created this tree planting guide saying here are a set of species you could plant depending on the context. But sometimes these spill over and have benefits beyond what we thought. So we were doing a study on Gundutopes, which are these wooded groves across Karnataka, but across Bangalore also, and doing a study of their disappearance. And we created a bilingual Kannada on one page, English on one page, where have all our Gundutopes gone, illustrated by our students. We then found the Karnataka Panchayat wanted 6,400 printed copies for the Panchayat libraries across the country, across the state, which we printed as the Karnataka state government, who is very responsive. In previous cases, it's been BBMP Lakes, which has been responsive. In some cases, with road widening, nothing has worked and trees still get cut. But this, I think, I'll leave it with the last, close it with the last. Our most intensive work has been, and also most satisfying work has been our climate festivals of life. So we, as educators, have a problem when we teach the younger ones, undergraduate students especially, but also masters, that when you start talking about climate change, ecology, environment, planetary boundaries, sustainability, it's very dystopic. And the first semester, you can see energy is dim, 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 and by the end, you have a lot of students in depression. And these are realities. We must give our students the facts, but we're also depressing them, perhaps too much to act. And then we've been thinking about how do we take this forward to even younger people, to schools without depression. So let's go back to the Indian idea of the festival, the Mela, the Jatre, whatever you call it. And we said we're going to create climate festivals of life around the theme of nature. So in 2022, we started with rivers. Last year was forest. This year's mountains. We start with a very large festival in Azim Premji University Bangalore campus. November 11th to 22nd are the dates for this year. You're all most welcome. Where we brand it as a festival for the young by the young. So we train about 100 young interns, both on art and science, to go across the country and document rivers, forests, mountains. We then have art and theater and games and foraging walks in the campus and all kinds of other things. And we get 1,500 visitors, children a day. This is trilingual, Kannada, Hindi, English. It now goes to zoos. So Bannerghatta Biological Park, in 2 weeks, we're going to have an event there. In the Raipur Zoo, we have something. We're talking to other zoos across the country. In our Bhopal campus, in our Dhamtari campus, we have this in Hindi with tribal youth. So these are really large festivals where we get children coming across. I mean, just some glimpses, campus comes alive. And science, we are looking on
western disturbances that produce rainfall over parts of North India, which is important for the rabi crops. And so the question is what will happen, and they have opposite influence on the temperature. The question is how is it going to affect the precipitation and this large scale dynamics. I think this was the idea. And one is the meridional overturning circulations. The other one is the water circulation in the Pacific. And I will keep it very simple because I don't want to go very technically into the details. So basically the tropical Hadley circulation is driven by the equator to pole temperature gradient in the energy. Because in the tropics we get a net radiation, there's a gain in the energy compared to the outgoing long wave radiation. The extratropic is a net loss, and because of this, and it has an impact on the monsoon also, because due to La Nina we tend to get higher monsoon precipitation, and El Nino is usually less. So why I want to touch upon these problems is that the Professor Ravi was telling in the near term, it is the internal variability that's the source of uncertainty, and in the long run it's the scenario uncertainty. So if we are looking at what are the precipitation changes, these large scale circulation changes in the Hadley and the water circulation are going to be very, very important, whether it's the winter precipitation or the summer precipitation. And so the question is climate change affecting increase? They were substantial. But our precipitable water, because whatever water vapor is increasing, it is efficiently getting converted into precipitation. And so the rainfall, the heating is substantial in the atmosphere, so it's going to drive stronger circulation. The vertical velocities at the mid-troposphere are going to increase substantially in the future. So the monsoon is going to get stronger, heavy precipitation, and also stronger flow. This is the message. And winter time Hadley circulation as well as the water circulation are increasing in response to global warming. So that is going to produce more aridity in the subtropics. So it has implications for West Asia and also some of the western disturbances as well. So I'm not going into those details. Thank you. Thank you. Yeah. Professor Anil Kundar.
Now, do you have any better understanding about winter snow precipitation in Himalayas?
Yeah, so I didn't touch upon that. One thing, what we did from the LMDZ model, we have looked at the winter western disturbances, which is one of the important source of winter precipitation. So the strength of the amplitude of those western disturbances are getting stronger with global warming, and so the extreme precipitation is increasing. Although the mean has not changed much. When we look at the type series of mean winter precipitation, right now it has not changed over the Himalayas, but the extreme events are increasing.
One of the field observers suggests that over a period of last 30-40 years, the solid precipitation, even though total precipitation is almost the same, but solid precipitation is significantly reduced. Is it something captured in your models or your assessment?
Yeah, what we found was some of the higher elevations, Karakoram and those areas, the frozen precipitation has increased actually, because the amplitude of the western disturbance is getting stronger, and that's what we wrote in that paper. But this Hadley cell intensification is going to have a big impact on the winter precipitation.
Any other questions? If you have more questions.
The last part that when you showed that nested model, right?
Yeah.
So that you say that Q1, Q2, there is an increase in the substantial increase in Q1, right?
Yeah.
But that is just a consequence of the monsoon because of the latent heating. So I'm just worried about that. That cannot be a cause. This is a consistent with the increase in the rainfall and even the feedback to the circulation.
Yeah.
But it cannot be considered as a cause.
No, but when we put this, see, we are actually adding, of course, monsoon is getting stronger. It's a coupled thing. See, monsoon, when the winds are strengthening, it's going to increase the evaporation. If you are going to add to the fluxes, and it is going to increase the convective activity, rainfall is going to increase, and the heating is in turn going to feed back to the circulation. It's coupled, it's a feedback. It depends on both. Monsoon is affecting the precipitation is affecting the monsoon. And that gets into a feedback.
I just want to comment on the model dependency, because in 2012 your own work said the median overturning circulation will be stabilizing.
Correct.
with another AGC.
With another.
That was 20 kilometer model. And here it's a variable resolution. And you are not, I mean, we are getting the opposite.
Yeah, you're true. It could be model dependent. What I found in that model, doesn't precipitation is small. MRI model, despite it has a higher resolution compared to what I showed just now. This is 35 kilometers. That was 20 kilometers. But precipitation doesn't increase. It generally tries to make the stability more. It just makes the adjustment. So it depends on the convection scheme. So many of the convection schemes, when there is an instability, they relax the temperature profile to make the atmosphere stable. And that component is very strong in the model. But how efficiently you are converting the water vapor into precipitation, that is captured in this model. So you are right in a way that it is dependent on the model water convection scheme. So but the fact that it is the extreme events are increasing at a rate and the rainfall amounts are increasing. So I kind of now tend to incline towards this.
I request Dr. Nagesh Vandala to constitute the speaker. Our next speaker is Dr. C.P. Rajendran. Dr. C.P. Rajendran is an adjunct professor at the National Institute of Advanced Studies, Bangalore, a prominent geoscientist in India with an international reputation. Dr. C.P. Rajendran is recognized for his wide range across geological and environmental sciences. His work has led to insights into earthquakes, tsunami sources and their long-term behavior. Through his collaborative work and international cooperation on coastal hazards and local capacity building, he has established linkages with researchers from countries ranging from the USA, Australia, UK, Japan, Indonesia, Iran, Sri Lanka, Nepal and Chile, among others. A prolific communicator on science policies, environment, education and scientific temperament, Dr. C.P. Rajendran will speak on following the trail of the Wayanad landslide, implications for the future.
Okay, let us say that I'm not an expert, domain expert in landslide. When Dr. Rajivan wrote me asking me to give a talk on this, I said my first impulse was to say no. But then I thought it's also very important that someone should be talking about it because this has the Wayanad tragedy, the disaster has shaken the public conscience. So I thought I should be probably one person should be coming here and talking about it. So that is how I'm here, and I must say that whatever I have put together here is that whatever I'm able to get some public sources and other sources, and may not be. I must say that I saw a disclaimer saying that there will be some kind of inaccuracies in what I'm going to present, but the overall, I wanted to come up with a message. What has really gone wrong in Wayanad? So the first, I would say that here, when you look at it. The Wayanad landslide is a question always that comes up is whether it's a man-made or a natural hazard. So I must say that there's a mixture of all this, and as the previous speakers have already said and warned about the increased global temperature and the consequences of that is it will be heavy, short duration rainfall that is become a sort of a marker in our the climate, the changes that is part of all this. That's what we are seeing around. So that is one thing, and you see here, what I come up with is that just to show you, what kind of landslide susceptibility that we are looking at. And this is one of those recent maps which is published by the IIT group, Delhi, about with the use of machine learning techniques and also some other parameters into this, and they have come up with this, and they say that it's highly reasonably confident about the accuracy of the database. So this is what we see here. We have you can see that there is along the west coast. Where is the highlight here?
For the first one.
For the first one. Okay. So here, what you see here, the west coast is that you have the hazard is much more than what you see on the east coast. And if you look at the Himalayas, we all know that the landslide probability is very high, and including the eastern Himalayas. So this is the picture that we get. And then we have a picture from the Kerala Disaster Management Authority, and you can see that what you find here is this is here you find that the Palghat, except for the Palghat, Kasaragod, and to the southern Trivandrum area, rest of the places you find there is a high vulnerability for landslide. So this is a picture that is published, available publicly by, released by the Kerala Disaster Management Authority. But I'm not sure whether they have this high resolution maps that, on a local, specific certain localities is available or not. I'm not very clear about that. So, yeah, so when you look at so I've already mentioned about the landslide inventory. And then you also have to say that the landslide susceptibility, according to the IIT group, is they have actually classified 4.75% as a very highly susceptible to landslide. And outside the Himalaya region, Kerala is the most susceptible to landslide. So if you look at the database, you also see that over the last couple of years, the landslide incidence has about gone up in Kerala. So this is the area where the landslide on July 30th is reported from. It's called Mundakai, and you can find that there is a system, there is a river that is flowing through close by, and you have also seen what they say is that the first initial landslide happened around 1 o'clock. I'll come to that. And later there's a second incident that is actually more devastating, that has actually taken over the entire, and the next, the site was Suralpara, that also been devastated during that time. So what I wanted to tell you is that before we go to that Mundakai, I just wanted to tell you that there is a place called Kamalapara, which is in a Malappuram district. You can see that. This is where it is, where a landslide has occurred in 2019. So what you find here, is also very interesting. So if you look at I just wanted to compare what has happened in 2019 in two places, and then we'll go back to Mundakai. So this is a place where you have landslide in Kamalapara, and this is not working actually. Highlighted.
There is a lag.
It's really shaky. Shaky.
I just want to move it. It's not moving. Pointing this way. So this is where one landslide was reported in 2019, and you can see that they have two images, satellite images from this place, and you can see that 2019 and 2007 and 2019, and you see the differences in the occupation, of human occupation in this, and you can see that how different it looks after so many years. So there is certainly a question of human interferences in all this. So the point what people are trying to say is that in this area where you have landslide reported, there was an original drainage which was observable in the earlier image, and later on you see that it is kind of being filled up, either due to human activities or due to some earlier landslide, whatever, we don't know. But the point here we are trying to say is that because of the lack of that natural drainage, this has become a big disaster. That is what the point people are trying to drive from this. So now we go to another place called Puthumala, that is in 2019, you had a landslide there. It is not very far from Mundaka. So it is about 3 to 4 kilometers. And you can see that when you look at the earlier images, and later on, you have another image close to the event. So you see that image, you will find how different it look. So even from the look of it, you can see that there is a earlier
I think the teacher sticky is better.
Sticky is better. You have something next? Pointer or something?
Here the pointer does the laser print and pointer will not work because of this TV screen. Is that a better one?
Yeah, that is not your point. Angle point
this is what we're trying to say. Like when you look of it, you can see that you have a situation where a landslide occurred in a place where already there was a landslide. You can see that kind of nature of an earlier landslide there. So again, whether this has been taken into account to come up with a sort of a vulnerability map or not is a question that we need to ask. I know, but So that's what we have been telling. Already there's a landslide which has occurred in 2011 whether this point has been taken into account to come up with a vulnerability map of the region or not. So the August 30th, July 30th Mundakai landslide actually started from the hill very close by, and the whole thing started with the initial incident around 1 o'clock. And later on, you have another one at 4:30. So it actually wiped out the settlements on both sides. One is in Mundakai, another one is in Chulapara. So there are about 400 death toll, actually just close to 400, and we are missing now. Then the question again is that what is the kind of rainfall that we have been getting there? So the last 3 days before the incident, it's almost close to 572 millimeter, and also the region that is very close to the site received a rain in the range of 160 millimeters. So the whole the total land that has been moved down is close to 86,000 square kilometers. So there is a close by river that is tributary of Atria, which has been actually most of this material has got dumped into that river and is flowed throughout the river course and reached even to the main river that's called Atria. So again, we have a pre-event imagery from satellite, which is released through ISRO. We also have a post-event imagery which is captured by the RESAT satellite. And you can see the comparison. Again, see there is an indication of a old landslide there. And the question again is that whether this has been taken into account while this vulnerability is being compiled from that region or not. Next. So we have various cases of landslide in different places like Idiki sometime last year at Wellathu, and we had an opportunity to go and work, and we did some seismic profiling to see what is the thickness of soil profile. So the model that we got from there is that we have a natural forest there previous to the slide, and also close to valley side have plantations, and because of the excessive rain and infiltration to have some over precipitation, and the land started sliding down, the top soil started sliding down. So you will see that all the landslide. This is the kind of mechanism that you find in most of the landslides in Kerala. So what the effect of anthropogenic forcing? That's again being discussed in many by many people, including among the public. So the external forcing, what we can see is the characteristics of land utilization and the construction and also the agricultural activities. For Kerala, the main problem I think is that our forest has been acted upon by different human types of human activities, especially along the western part you have this plantation that is going on. The rubber plantations and tea plantations, which has started probably during the Britishers, and it's went on and continued even during those So this affected the landscape and soil structure and the natural drainage. So that's also contributed to the slope instability. So again, as the previous panelists have been talking about the climatic factors, we all know that there is an intensification of short duration rainfall. So this question also raised about the subsurface soil erosion which has been reported from different parts of Wayanad previously. And you can see that there's something called subsurface soil erosion piping, which happens when there's a subterranean erosion of material under the soil, underneath the soil profile. So here, what happens here is that many times the roots which has been destroyed, there's part of the deforestation. You can, what happened was they have removed many forests, and actually planted rubber plantations, even rubber plantations, and the roots are remaining there under the soil, and which is for a long period gets decayed, and it becomes interconnected pipes, passages through which the water flows down. So this also erodes the soil from the, from underneath the, if you go down the soil profile, you can, in many places you can see the soil piping in many parts of Wayanad. So there was a report by Center for Science Studies years back, when it was from the state government, which actually they reported there was a previous landslide in 1984, which actually made 17 landslides. So this area where you had the landslide is not the first time a landslide is actually reported. So this is not a virgin area where out of the blue event of this recent one occurred. Actually, there was a previous report of landslide that we reported in this market. Again, I was mentioning about Pudumala landslide, and you find we just know that was, as I mentioned earlier, in 2019 you had this landslide event, which actually again killed 20-25 people, and that is not very far from Mundaka. So what is interesting here is that this event also mimics the 2019 landslide, sort of mimic what has actually happened during the 2024. Because it started as a twin event. First as a small event, the second one was a major event. Then this is also, as I mentioned earlier, this actually started from the top of the hill inside the forest. The question again here is why such a thing happened in a virgin forest, and how could you attribute this to partly the anthropogenic activities? The answer to that is that as you come to the middle level of the hills, you find the plantations. And you see that many of this area has been disturbed by plantations, and the soil structure has actually changed a lot. So there is not much water carrying capacity for the soil in the present conditions. So these are the anthropogenic factors which I've already sort of mentioned. One is the removal of natural vegetation for farming that has started since British rule. And the activities have sort of changed the soil structure and also consequently the hydraulic conditions. So the large trees removed, as I said earlier, the root systems remain there, and it got buried, and it got decayed, and that becomes flowage channels for subterranean water. And that's what is called soil piping. Then the absence of stubble mulching. You know what? We don't have a habit. Our different practices don't actually follow. Sort of this kind of things. And we have actually doing the agriculture activities. We don't actually do much of stubble mulching. So that actually reduces the organic content of the soil. That actually facilitate the faster hydraulic conductivity and also the subterranean water. Then the construction, as you can see that if you look at the statistics from 1950 to 2015, you say that 65% of the forest is being destroyed in Wayanad. So it applies to many of the built-up areas which has gone up in very high proportions. So the changing, one of the major problem in Wayanad is that we have a changing hydrological properties. That is, it's actually the structure of the soil has been made so much. It's not able to, the hydraulic conductivity on the diffusivity has gone up, and the water started going down and started flowing in subterranean channels. So that's actually one reason why you have high incidences of landslides in Wayanad. So again, we have problems like a lot of disturbances in local drainage that is not able to channelize the surface flow. So it's a question of actually a land use policy or the land use, the planning that is required there has been completely ignored over several years. So again, there's a question of quarrying, but quarrying also adds to many issues here, many problems here like drain fractures and also widening the existing fractures. But the problem here is we are not even sure how, we don't have a database to suggest that what the direct relation of quarries to the landslide or the destabilization of the slope. So actually what we need is we need a database to convince ourselves that quarries are a direct bearing on the landslide. So here the question is we need to have more intense network of instruments to monitor rainfall and surface flow. That we need to monitor that, but how are we going to do it? And there are a couple of examples of success stories like the Atria, where they are able to predict landslide by networking of instruments looking at the surface flow and also taking other parameters into consideration, and they are able to predict one landslide in Munnar. Again, this needs a lot of investment, and we also need a lot of instruments to monitor this kind of parameters. Again, we have ourselves, IISc, we actually did some seismic noise imaging in one of the places in Dicky, and it's a very successful thing. We have found out that we are able to map the thickness of water bearing, the surface soil profile in various sites, and also the water bearing capacity of the underlying soil. So this kind of studies can be extended other places to understand the vulnerability of life. So again, there have been discussion on community participation. Important thing is to create the awareness how to reduce the risk. Secondly, we also need high-resolution maps of landslide vulnerability of this area to be shared with public. A good example actually comes from Mundakai itself, because there is a place, a Center for Ecology and Wildlife Biology at not far from Mundakai. They are running a sort of community-based research institute. And they actually issued successfully a warning to the district authorities regarding landslide about 16 hours before the event. And they found actually they have a rain gauge from not very far from Mundakai. That's a place called Putumalai. And from there they found that the rainfall is 572 millimeters for 3 days. And using that and comparing it with what they got it from 2019, they're able to come out with a threshold of rainfall there, and they issued this warning. Unfortunately, this was not taken very seriously by the authorities. That is what I understand. So this is again a example of community participation in monitoring landslide and also in in raising the public awareness. So this is one example that I would say that we learned from Wayanad. Next slide. Again, some of these sites are from Madigere, Chikmagaluru, where we did some, we did some sites inspection and came up with a report. Again, that's a coffee plantation there. And what they did is there are a lot of rain, harvesting pit on the top of the hill, and that actually collected water and allowed the water to percolate and trigger the landslide there. That is one explanation that we could come up with. Next slide. So this is one from the NASA, and you see this nowcast. So they use a sort of a model where they use the rainfall in real time and use the other parameters like tectonic faults or types of bedrocks, tree cover, steepness, etc., and come up with this kind of models that would actually help people to have a sort of assessment of, they call it a situational awareness, to decide about their the risk that they face in particular different areas. So this keeps changing all the time. So this is one model globally available for all these places. So I think next slide. Thank you.
Yeah, CP, there is very interesting discussion going on this topic in a landslide forum, which is constituted by Government of India. It is a forum on net. So if you, of this particular landslide, Geological Survey of India claims that, look, they have shown that since this landslide occurred earlier also, therefore they have done the detailed mapping of this landslide. What I'm not sure is whether they have done the hydrodynamic modeling, because that is what normally we do in our GLOF studies, where we say if it bursts, how much flash flood will come, which area will be inundated. And this is now possible to do the hydrodynamic modeling also, where the mud flow can be also simulated. I'm not sure whether this was done by Geological Survey of India.
I'm also not very sure about that.
But one thing I want to add more in that, Amruta University claims that they have developed the landslide forecasting system. And it is already installed in one of the places in Kerala. I don't know where.
Yeah, I know. I mentioned about that. That's from Munnar.
So I think if we really combine all these things, probably we have a potential to forecast and assess such events. So how do we go about it actually doing on the ground? Because we have a technical skills and knowledge to do it. But how we can now implement in such a fashion that communities are benefiting?
Yeah, it's an interesting question. One is you need a lot of investment in that because you need a lot of equipment. But what I would suggest is that, for to understand the hydrological parameters like the subsurface flow and all that need to be monitored very closely. So the point
I tell you, Central Water Commission is responsible for flooding, and GSA is responsible for landslides, and somebody is responsible. So there is no coordination. It's all silos. All local silos. Okay, we don't know where the water goes, and Central Water Commission doesn't know where from how much water is coming. So there are. So there's a flaw in our system which we need to correct. I am not a responsible person to correct it, so somebody else will correct it. Hopefully.
Sir, I have a basic question to ask you. As per the Gargil's report and the Dr. Kasturan's report, there are 32 ecologically sensitive areas in the landslide areas in the country they have identified. Out of which 10 to 12 are there in Kerala alone. So what is the local government has taken stand to at least to prevent the loss of human life?
Yeah, this again, the central government has asked for some response from the government recently about this, how it going to implement that. There is no question that it needs to be implemented, but the problem here is the local people are, political parties, they are depend on their votes and they don't want to move out of it. Some areas, ecologically sensitive areas. So I think what I understand is from even the Gargil committee report, they talk about grids. 30 by 30 kilometers or whatever. If you can actually adjust that, sort of make some accommodation in that kind of gridding, things will probably will be accepted by the local people. So there are ways of implementing that. It's not a lost cause. I think we need to talk to people, and also the experts should come and say where you can accommodate these things. So this is where the thing stands.
I think before the next landslide happens, we will disperse for lunch. Thank you very much. And he quickly agreed for giving a talk. And we will see. Thank you. So before we disperse, I want to make an announcement that at Atria we have started a new curriculum and masters by research, MS in research, as well as a PhD program which are approved by Karnataka state government. So please spread the news to your students. If somebody wants to join for MS in research as well as PhD program, you are welcome. Please give the news to your students as well as to your friends, etc. So thank you very much. So
which discipline?
So MS by research and PhD will be in energy sciences and digital transformation. Broadly covers AI applications for mostly what is sustainability today, energy sciences and digital transformation. You can share some information about that.
Thank you. So we will have
recipient of the Shanti Swarup Bhatnagar Prize and a fellow of the American Geophysical Union and the National Academy of Sciences, Professor Mishra will speak on the occurrence and implications of droughts in India, past, present and future.
All right. Good afternoon, everybody. So I'm going to talk about droughts, and as you might have seen in the previous talks, that Indian summer monsoon is going to strengthen in future as per the projections shown by Dr. Krishnan. So we may sort of get a sense that this might solve our water challenges. So we may not face frequent droughts and our water concerns may go away. But I will tell you something which is just opposite of that, right? Because of climate change, we are going to face more and more water challenges, despite there is a projected increase in Indian summer monsoon rainfall. So I'll be talking about occurrence and implications of droughts in India, past, present, and future. So past, I will discuss about the famine and drought during the British era. So how that affected our country. But some of the present droughts, what are the implications, and then the future. Will it not change? I don't think these two are synced. Anyways, so if we click up, maybe I can go back to the old business.
Want to speak over the slide? I'm
Chennai over. Okay, so I can talk until this is getting set up so that, I can compensate for the time. So I will show you, so my talk is going to have 3 sections. In first, I will show you how we tackle the past droughts, especially during the British era and famines. What were the implications of that? Then I'll talk about some of the recent droughts. And then I'll show you how climate change can basically intensify drought. And what does it mean for water availability in our country? Now, so the part of problem is this projections that show that we are going to see the strengthened monsoon rainfall. So this gives us a false sense that our water availability will increase. And that is a part of problem because, first of all, that the changes projected by these models, if you look at, these are very, very high, despite, if you look last 30, 40 years, there has been decline in rainfall over the Indo-Gangetic plain. So there is a mismatch between the model and observations. Now let's believe that models are right and there will be increase in rainfall, but that is totally during the monsoon season. So what about after monsoon season gets over? Okay, so I have to control this, not from here. Okay, so I can close it. Okay. So what about once monsoon season gets over? And the other problem is that this increased rainfall mostly comes in terms of extreme events, and we don't have infrastructure to store water. So there is an increase in rainfall, but how we can store that water on land? Because we don't have that much space or bandwidth to store more and more water. So, I mean, this, you might have seen this sort of gives us an impression that how and why the summer monsoon is a lifeline in our country in terms for both food and water security. So once monsoon sets in, you will see pictures like these across country. Rice plantation happens, water bodies receive water, groundwater level comes up, and all good news, right? Of course, we see extremes during the monsoon season like floods, landslides, and those create problems. But if we leave them, we will see that monsoon is essential and it is true lifeline for our country, and it ensures food and water security for the people more than 140 crores, right? 1.4 billion. What is more interesting is the spatial variability that we see during the monsoon season. You take any monsoon season, what you will see that there are regions that received a lot of rainfall, and there are parts of countries that did not receive sufficient rainfall. So droughts and floods will happen every monsoon season. And across, some places like here you will get a lot of floods. On the other hand, places like these, they will be under drought. So there is a great deal of spatial variability. There is also temporal variability because rainfall is not evenly distributed during the 120 days of the summer monsoon season. So you will see some part, June is very wet, July is dry, and then September again becomes very wet. So space-time interaction, or how rainfall will occur, that basically sets the precondition for droughts. And drought can occur for very short period, and drought can occur for a long period also. Like we have seen 2002 drought, where entire monsoon season was very less rainfall. On the other hand, we now are seeing flash droughts where you have 15-20 days no rainfall with very high temperature, and soil moisture will very rapidly deplete, and crops will start wilting. So we call that flash drought. So, if you don't know, this is a simple figure that shows like how one type of drought translates to another type of drought. So, drought will start from the weekend monsoon or less rainfall, then that we call meteorological drought. Then meteorological drought, high temperature combination of precipitation deficiency, and that can reduce the soil moisture and runoff, increased evaporation, and then agricultural drought can occur. And if this persists for a long time, you will see less water in rivers, even groundwater going down, and that we call hydrological drought. So there is a propagation of meteorological drought to agricultural drought, hydrological drought, and the last type we call socioeconomic drought, when society starts facing the impact. So people will lose, there is a reduced purchasing power because of the crop loss or other types of socioeconomic impacts. So these are the different type of droughts and their propagation. So you can see here also that precipitation deficit can convert to soil moisture, then stream flow and groundwater, and then there is a lag. So it will take some time when meteorological drought will show up to river flow. It may take months, it may take weeks, depending on how are the conditions in terms of temperature and rainfall. So what I'm going to show you that, how deadly were the droughts in the past, and then what happened during those droughts. So you might have learned about, or you might know about famines in India. There have been a number of famines in India, and those caused millions of deaths in our country because we were not food secure that time, and we did not have irrigation, or we did not have infrastructure to supply or transfer food from one place to another. So what we did, basically, we sort of tried to understand that all these famines which are listed, whether those were caused by droughts in the past or there were other regions, especially the famines during the British era. Now the problem was, if you want to understand drought during the British period, you need data, observations. So I contacted to IMD, and they were generous enough to share the station data starting from 1870 that our country has. So what we did basically, so if you don't know famine, I think everybody understands famine, right? Famine says food shortage accompanied by significant number of deaths. And India has long history of famines, and during British era, 1765, 1947, if you look the history, there are 12 major famines. What we could do, we could study only these. Those are highlighted in red because for them we could create the data and create the agricultural drought kind of a situation. So we collected the data, we did some quality control, and we sort of developed a gridded half degree by half degree rainfall product. We got temperature data from other sources, and we did a sort of a long-term data, this gridded data product starting from 1870 until I think 2017 or so. And we compared like how pre-1900 our reconstructed climatology compares with the post-1900 climatology in terms of spatial pattern. We use our model, hydrology model, to sort of simulate soil moisture because we were interested in terms of agricultural drought during the famines or how agricultural droughts led famine. We also studied, I mean, this is a little bit complicated to understand, but the thing is that when the major drought occurred based on different durations, so those we identified, these are the periods of drought. And then what we did, we sort of, whenever famine occurred, we looked at whether there was agricultural drought, long-lasting agricultural drought, that sort of caused crop failures. Now, how to ensure that drought occurrence and famine is at the same location? So sort of we looked at this book where they have British provinces during that time. We digitize those provinces that you see here in color and overlay on our drought extent to ensure that drought extent and the provinces where famine occurred, they overlap with each other. And you will see that there is a close correspondence between these two, and which suggests that monsoon failures, agricultural droughts, crop failure, less of food availability led to major famines. Now, what British did, 1873-74 famine, you see no mortality was reported, and that is only because they imported food from Burma and other countries and supplied that somehow. So it was only one famine where mortality was not reported. But if you look other famines, like this is the Great Madras famine, 1876, roughly 5.5 million people died because Britishers, they did not pay much attention. And if you read all these famines, what we notice, only Bengal famine was not caused by drought. So we could not get any reconstruction of drought. And it appeared like Bengal famine was total policy failure because they exported food outside of the country and and you might have heard about this Churchill's role. And there is a lot of literature in history available on that if you are interested. So, I mean, most of these major droughts, famines were caused by El Nino, or El Nino was there when these major failures happened, which still is the case when we see long-term major drought. But there were also droughts where no famines occurred. Not always droughts caused famines. And you see the most recent, when we did this data, was 2015 drought in North India, and that had a lot of impacts, but not something like famine. So the question is, how did we tackle drought in the past? Of course, during British era, British had different interests, and they did not sort of they did not, I would say, they did not care all the time, depending on who was ruling in terms of governor. But limited irrigation, low crop yields, and drought, monsoon failures caused this. Most of these famine caused by droughts. And then after that, of course, about Green Revolution. We developed a very strong public distribution system. And so you see here the food grain production has gone up. Now the question, we have developed irrigation, we have improved the food production by improving the seed varieties. So what are the challenges for the future? Whether future we will face any food crisis or problem or not, or how climate change can affect that. So that is the next question I am going to discuss. And in this, we sort of looked at long-term simulations from something called LENS, more than 100 ensemble members, and how droughts will change during the warmer climate in India, and we call that hot and dry summer monsoon extremes. This is simply that how we did do that. We use the indicator called SPEI. Less than -1 means dry condition. Temperature in the same season more than 1 standard deviation is the hot season, and if they both are occurring during the same monsoon season, we'll call that hot and dry summer monsoon extremes. So what is interesting, if you look at our monsoon season, whenever drought happens, major drought, you will see roughly 1 or 2 degree temperature going up. And that is because you don't have rain, you have high solar radiation, less cloud cover. So temperature by itself, weaker monsoon will lead higher temperature. Now you pose climate change on top of that, when we are saying like 2 degree or 3 degree, more warming, and the monsoon failing under climate change, how those hot and dry conditions can be very, very challenging to sustain the food production. So we have made tremendous progress in terms of food production, that is shown by here. 1950 until 2015 or so, this data is food grains, cereals, rice, and wheat. But you see a lot of these dips in this time series, and those dips are primarily caused by monsoon failures. So whenever monsoon fails, still you see a significant reduction in food production, despite we are having very much improved irrigation infrastructure in our country, reservoir water storage, ability to pump groundwater. Also, we looked at how hot and dry monsoons will affect food grain, rice production, etc. So there is a significant relationship. So that suggests that if you have dry and hot extremes during the monsoon, your food production will go down certainly based on this data. Now, we also looked at how the historical or observational these hot and dry conditions co-occur with El Ninos, and we will find a large number of those occur during the El Nino years, and that is the same plot here. So these are all observed major hot and dry events, including the last one is 2015, 2009, 2014, 87, 79, 72, and 51. Most of them, if not all, occurred during El Nino years. Okay, now the question is that if there are projections of higher rainfall or increased rainfall, why we need to worry about that? So there are two aspects I would like to highlight here. One is something called atmospheric water demand, PET, potential evapotranspiration. That is going to increase with much faster rate than the rainfall projections. Projected rainfall is going to increase under climate change. If you believe in the models, those perform well against observations. So the problem with climate models is that models, those don't perform very well against observations. They are very sensitive to change in rainfall, increase in rainfall, and change in temperature, warming. So some of them I have seen project 40% or 30% increase in rainfall in future. On the other hand, if you look at the GCMs, those are good against observations, you will find changes are mostly limited to 7 to 8%. 7 to 8% increase in rainfall. But so this is increase in rainfall from the lens ensemble members, that is roughly around 8 to 9%. Change in temperature, change in PET going up to 10 to 12%. So the demand will also be high in terms of water availability, and we may see that can compensate this some part of that increase. So dry years, hot years, and how hot and dry summer monsoons are going to increase. So despite you have more rainfall, that will be combined with higher temperature, and that will again increase the irrigation water demand. Okay, I'll skip this. So now this is the last part of my talk, that how basically summer monsoon drying what does it mean for water availability in the future. So what we did, we sort of looked at, okay, even if we have increased climatological rainfall in future, you will have years when monsoon will not be that good, and those will be drier monsoon years. And what will happen to India's groundwater during those years, and combined with the winter warming, because dry monsoon and followed winter will be warmer because of the increased temperature. So in winter we will have more irrigation demands because of the warming, and if monsoon is dry, how these two can affect the groundwater system. So I mean, to give you just an idea, like this is 2015 drought in the northern India or Gangetic Plain. This was very severe drought in that region. And what people have figured out, or we figured out, that from the groundwater depletion followed winter after that drought, groundwater was quite significantly, depleted. And that gives us a question that to address that how this will frame in future. So we use a model called HO8 model, which considers groundwater pumping and all other hydrology, irrigation, pumping. So we can also simulate the pumping requirements, how much area is irrigated, and so on and so forth. And these are the GRACE and model comparisons. So this is GRACE satellite observation versus model. This is the ground well observations versus model, and these are the storage changes in North India, that how much water has been lost over last 2 decades or so. So first we looked at that dry summer monsoon and warm winter which happened in 2009. So how that affected the groundwater. These are the results from GRACE, and these are the well observations. You will see many wells showing the depletion in groundwater. And then we sort of looked at how irrigation water demand, groundwater recharge, and groundwater storage changes when a monsoon drought happens. So you see, during the drought year, irrigation demands can go very high, recharge will reduce, and that will have negative impact on groundwater storage, and that will continue in the winter season also. So you look at the dry monsoon and warm winter. Dry monsoon and warm winter, which is the typical case if in future we see during the summer monsoon drought, and the followed winter will be warmer. So you will see more irrigation demands, less recharge, and overall groundwater depletion. By the way, these results are based on observations. And then we also looked at the similar, using our models, we conducted simulations where we imposed 1 degree global warming scenario, 2 degree global warming scenario, and 3 degree global warming scenario, and estimated that how much precipitation will decline or demand will increase and recharge will go down, and what will be the net impact on groundwater system. So overall, what we found out, that even if there is a surplus precipitation, the groundwater recharge will be much lesser than when there is a drought. So drought will have higher negative impact than surplus monsoon season will have the positive impacts, and that is because of the nature of rainfall. So more rain will occur in the form of extreme rainfall. This is my last slide. So, these are the things like water availability under climate change and food production under climate change. These are the two sort of big questions. Despite there are, projections showing that more and more rainfall, but these two areas will be very much affected in future because of increased irrigation demands, increased atmospheric demands, and also changing rainfall characteristics, because heavy rainfall doesn't contribute that much to groundwater recharge. So rapid groundwater depletion is already happening. That may still continue in terms because of to compensate the warming, increased irrigation frequency, crop yields. So essentially, what the message I would like to give that, even if we have more rainfall projections, how the rainfall will be distributed in time and is in space, that will decide whether we are water surplus, water deficit, even during the monsoon season. Because even if there is a 15-20 days gap, could pose a lot of pressure on the irrigation demand. The second is that the dry season after monsoon season, water management will be very, very critical because we don't have sort of bandwidth to store all this increased water into our reservoirs, right? So our capacity is not increasing with the increase. So our capacity is static. So most of this increased rain will go away to oceans. And then after, monsoon season gets over, during the dry season, we will face the similar challenges that where is water. With this, I'll stop here. Thank you.
What are possible solutions for this?
Good question. Yeah, so solutions are like we have just done some work identifying the solution, because we cannot always talk about problems and give the negative picture. So the solutions are there, but those are complicated to get implemented. Okay, so first solution is improve groundwater recharge, because groundwater is going to be the most critical during the monsoon failure under climate change. Nothing will save us other than groundwater, not the surface water storage. The surface water storage will deplete even before we realize that there is going to be a long-term drought. So strengthen the recharge, reduce the dependence for food production on groundwater pumping by improving the efficiency, and also basically by thinking about the cropping pattern. To surprise all of you, Punjab is the only region in the entire globe that grows rice in a semi-arid climate. There is no other region. Semi-arid climate, so it consumes more water than the annual mean rainfall. Now, if you put entire rainfall to recharge groundwater system, likely is that you will remain in deficit, right? So improving, changing the cropping patterns, moving towards less water intensive crops where depletion is high. That can be done by changing the market and also MSPs, minimum support price, some incentives for farmers. And then what?
Subsidy, I mean.
Huh?
Stop subsidy.
No, that is not the option actually. When we write stop subsidy, that is not the option, because once you stop subsidy, nothing else will work. Because so I am proposing incentivize farmers more to grow not rice but rather millets, pulses, oil seeds, or something else. And so what people have figured out that improving irrigation efficiency did not work well in our country. So when they improved the irrigation efficiency, farmers increased the area and they started using irrigate more area, with improved irrigation. So the water consumption increased. Yeah. So, I mean, this is a very complicated problem that probably involves us. This is more political, social problem than technological.
Water has to be charged. The water is free for the farmers, right?
Yeah. They will not.
We have to win the elections.
Yeah. They'll not charge until it becomes a limiting resource.
See, we only told Punjab people to grow rice. Okay, then give subsidy to buy electricity, free electricity. So they pump the water. They pump the water and they grow. And by October, and October, they have to cut that gas. And because they will go for free. And they, instead of cutting gas and waiting, they will burn it. And then it becomes a pollution problem for Delhi. We only created all these problems. Then we try to find a solution. We should not blame people in Punjab.
So just one
system, so I can speak.
Oh, sir, I just had one comment over here.
Yeah, please. Yeah. Oh, yeah.
Running away from challenges.
From Gandhinagar. Thank you very much.
So just one comment, sir, if you don't mind. Yeah. So since this morning, I think this is the fourth speaker, maybe, who used the word problem is in implementation. So we have challenges, we have solutions, but what is the puzzle? What is the piece in the puzzle that's missing? It's implementation. So what is it we're doing, trying to connect to the people who are in charge of implementation? What's the problem? How long can we keep finding solutions to the problems and not able to implement? So that's where the elephant is, So we need to do something about that.
Good comment. Thank
Our next speaker is Dr. M.V. Ramana, who is a senior scientist in the Earth and Climate Science Division at National Remote Sensing Center, ISRO, Hyderabad, with seminal publications on aerosol radiative forcing, aerosol cloud interaction, land surface processes, greenhouse gases, extreme weather events, and renewable energy. He has also been contributing significantly to National Information System for Climate and Environment Studies, the program of ISRO Department of Space. Dr. Ramana is speaking on how satellites are used to monitor climate change.
Good afternoon to all of you. Actually, my director, Dr. Prakash Chauhan, is supposed to come because of the last minute some commitment. He had to go to Delhi related to the extreme weather event related meeting. So he suggested me to go and attend, give this talk. And on behalf of him, as well as from NRSC and ISRO, I thank the team for inviting us to give a talk on this. I'm going to talk about the current satellites that we have and how the data we are utilizing it, and then how we are disseminating to the scientific community. All those details I'm going to talk. The first of all, these are all the currently available satellites with us. One is ResourceSat, which we effectively use it for resource monitoring. Another one is RISat, which we use it for extreme weather, means especially disaster flood related studies. And also we have Cartosat, series of satellites. We use basically imaging at a multispectral level. And also we have series of OceanSat sensors. And also, as we all know that we have weather and atmosphere related InSat 3D. We all have series of sensors, but effectively the data is available from around 2000 onwards. And all these sensor details, the specifications and all are there at the end of this slide. Those who are interested, they can go through it and get it. But I will go through product by product. First of all, when climate change taking place, what happens to the cloud cover? That was the first question we thought. Let us look into the data we have processed in the last 10 years. The InSat 3D is available from 2013 onwards. Till now, we have processed the complete data set, and we have validated with Modi's data, which is at 10:30 p.m. and also at 13:30 local hours. We have validated this retrieved product with Modi's data, and which is within the 5 to 10% of uncertainty. And if you see this data for the last 10 years, this is actually 25 kilometer gridded average product. There is an increase in the cloud cover over the land mass, and it started decreasing over the Indian land mass. But it is within the variability. But if I take it at 4 kilometer level, you see it's kind of a bell curve kind of a thing. So when I do at 25 kilometers, it's getting smoothed out. So it is a question whether should I generate the data at 4 kilometers or should I generate the data at 25 kilometers. But for modeling community, most of the time they say we need at 25 kilometers to validate the product. That's the reason why we are making the data available at 25 kilometer level. But if anybody is interested, we can disseminate the data at 4 kilometers level, native resolution also. And then also, just to see whether this data can be utilized for any of these studies related to climate studies, what we have done is we have taken December and January data, and we examined over the Arabian Sea where we have intense aerosol transport takes place during the winter time, and there is a location where the influence of the aerosol landmass influence on the that part of the place is almost negligible. And also we have examined the vertical profiles of extinction coefficient using the Calypso LiDAR. If you plot aerosol index versus cloud fraction and also aerosol index versus cloud top temperature, as aerosol index means it is a multiplication of AOD times extinction coefficient, that is aerosol index. As aerosol index increases, the cloud cover over Arabian Sea is increasing by around 2 to 3%. And interesting, the cloud vertical tops is also going up. So if you see, we have also seen cloud fraction versus cloud top temperature for different aerosol indexes. You see, as aerosol index increases, as a cloud fraction is increasing, as well as cloud top temperatures are also increasing. And then to examine this, whether it is correct or wrong, we have taken an independent data set, that is series, which gives us the planetary albedo that is reflected to the incoming solar radiation. If you see over that part of the region where there is enhancement of albedo, so that also shows that there are cloud formations are taking place and they are reflecting more energy back to the top of the atmosphere. So the pollution over that part of the region is enhancing the cloud cover, as well as it is expanding the cloud depth also. So this, just I'm showing it to you to give you the confidence on the kind of data that we have and kind of rigorous retrieval procedures that we have gone to make sure that the community can use this data. And then coming to the another product, that is land use land cover data, which is available since 2003 onwards on continuous basis, and it is available in the public domain in Bhuvan as well as our NICES portal. If you see, there is a drastic change is seen from our northwestern part of India, and this data is available at 56 meter resolution. And if you see our northwestern part of India, there is enhancement of the crop land at the expense of barren land and grassland and shrublands. All those lands got converted it into cropland. And how many classifications? We have 18, sir. And then we examined that thing, and once again, planetary albedo over top of the atmosphere. This is for summer season, March, April, May. If you see, there is a significant reduction the top of the atmosphere over northwestern part of India, whether it is a clear sky, whether it is a cloudy sky. The arrows indicates where the signal is at 99% level, it is significant, and cross indicates it is not significant. And then if you see during the daytime, that is at 10:30, and the bottom one is top is Terra, and the other one is Aqua from the series data sets. And then if you see, there is a reduction over that place around 0.01 of planetary albedo. If it is in watts per meter square, which is close to 12 watts per meter square during the daytime, that is around 10:30 and 13:30. But if you take diurnal mean, it is coming close to around 5 watts per meter square. That part of the region, because of the land use land cover changes, that region is gaining around 5 watts per meter square over that part of the region. And if that energy, if you spread it over the entire planet, it comes to around 0.02. So the change, a small change at northwestern India, which is contributing around 0.02 watts per meter square at the land mass. So the reason why I'm once again trying to show you is to tell you that the data that we have is land use land cover data is very effective in understanding these changes. And then recently launched EOX OceanSat 3 data, which is able to give simultaneously for the first time wind speeds as well as the chlorophyll concentrations, and which is helping our team at ECSA or NRSC to understand these phytoplankton dynamics. And then and that data is also publicly available. The most important thing, another thing that I wanted to bring your kind notice is that this morning Dr. Krishnan was also talking about Hadley cell. There is a debate that Hadley cell itself is widening, and then that actually is mostly confined to models and proxies, but there was no data was available to really check it. But using QuickSat data, could see that there is the Hadley cell is widening. But the problem here is if we change from one sensor to another sensor, there is a discontinuity in the data. And also whether it is 1 degree or half degree, those kind of differences are coming. It is mainly, is it coming? We don't know yet. It is could be due to the retrieval problem, or it could be due to the diurnal cycle that may be happening for that Hadley cell. For that, we are part of a committee on Earth observation satellites. As part of CEOS, all these space agencies joined together and trying to come up with a merged wind speed product over the oceans. So that activity is going on. Very soon we will have a merged wind speed product to be available from the NICES portal. And then, as you all know, that this is taken a classical paper from sea level trends. All our Indian sensors data as well as foreign sensors data has gone into it, and we examined the increase in the sea level, but we are mostly interested on the Indian part of it. We took all the available data and we have seen what is the kind of sea level change that is taking place. And also, we have also examined who is contributing to that using all the available Argo and Grace data sets and everything, using the model things and all. It shows that the steric component is majorly contributing to the sea level rise over Indian coastal regions. All these data sets, once again, are available publicly, freely in the NICES web portal. Another thing is that we started upon our chairman's interest that he wanted to understand all the eddies that form over the Indian seas around Indian Ocean or Arabian Sea, and what is their energy and how they are propagating and all. Why the question started like an Arabian Sea, how come they are, the eddies are forming, and to understand that this work just started. We are trying to understand how the eddies are forming and how they are moving, and also that their amplitude, their eddy kinetic energies, their radius, their amplitude, and then all these things we are trying to examine to understand. We just started this work, but this data is once again is available freely in the NICES web portal. And then currents, we have retrieved the currents from all the scatterometers available data, and also we have retrieved all the three components, geostrophic and Ekman, all those things. And we are trying to, our team at ECSA is trying to understand all these regions and how these currents are changing, and when the Pacific Ocean through flow happens, what happens to the currents and all those things using the satellite data. So these data sets are once again is available in the NICES web portal. And another thing is these data sets trying to understand the Arctic sea ice. These data sets does not belongs to us. These are ISAT and Cryosat. We just started dived into this data set, got hold of the data sets and tried to examine, see whether we can get a kind of hold on the data. And we were not having expertise, but now we gained the expertise in processing these data sets, and we have shown that there is a decrease. Means it is known. It is not that we do not know, but we have kind of gained the expertise. So this data now we are trying to utilize it over other parts of the globe to examine, to see whether we can monitor the changes in the volume over Arctic. Similarly, is it possible to examine over Himalayas and all? And then our Indian own sensor, using that, we have seen that there is a place called Chamoli where they conduct the sports events, and that events they are forced to cancel because there are occasions The snow was itself was not available because of the global warming, the changes that are taking place, and to the extent they are bringing artificial snow to conduct those sports events. So all these data sets, it is kind of our validation is kind of that whatever we have retrieved, we could validate with those events. And then the coastal erosion, using our AVIFS data, we are able to examine the coastal erosion related. This is the map, photographic map is taken, and this is the satellite image. To the data is available to understand along the coast, to understand the coastal changes. And the another one is, with a lot of efforts, I think JS team at that point of time, the megatropics was the only climate sensor India had, and that sensor had a Saphir for water vapor. This thing we just started. We have examined all other. We created all the historical data sets, but we started looking into the humidity data set over India to see whether we can clean or bring other microwave sounders data, and to see whether we can examine this data. And currently we are working on creating climatology of humidity over Indian subcontinent. We have seen there is an increase in the water vapor content over ocean, but still there is not that much over Indian landmass. We are trying to examine what is the reason behind it. And it was there up to 2018. There was a big gap, and recently, ISRO has launched a continuity mission, which is data is available now. Earlier, we used to get around 6 to 7 readings per day, and now with this sensor, we are getting around 4 to 5 readings per day. And this data has been validated by EMD, and they give certificate that it is meeting their requirements. But still, once we process that Saphir data, and we are going to come back and see whether we can normalize the data set to generate the long-term database. And then another thing that we have taken up, it is a new product, is vegetation optical depth. In the optical domain, we get NDVI, but whenever we have clouds, we will not be able to generate the NDVI data. And there is a lot of demand from agricultural community that they want some kind of greenery related parameter. So we have went ahead and processed all the optical remote sensing microwave data, AMSR, AMSR, and then SMAS and SMAP, all the data sets we have processed at L band, C band, X band, and as well as at KU band. What we have seen is we are able to, this parameter is able to show the changes, the greenery over Indian subcontinent. But most importantly, at L band, when the crop is there, which is have a low biomass, the signal is able to penetrate very easily. But when it comes to X, it is able to detect significant amount of VOD. But when it comes to the forest, it is a thick mass, so L band is able to produce the real VOD data, but X band is getting saturated. In this context only, means apart from other reasons also, the sensor that is going to come up nicer, which is going to have one more band at S band, probably we may be able to, I'm sorry. This is another one which finally MOEFCC is also wants to know satellite-based above-ground biomass data. This data was generated by European community for the year 2016. 16 that was available. We processed it for that particular day. All these L-band CX VOD products, and we plotted as a function of forest and non-forest regions to see whether we can establish a relationship between VOD, because that is a signal loss due to the vegetation. So that parameter should be able to match up with the above ground biomass. So that work is currently is going on to see whether when the biomass is very less, we are able to get a nice curve. L band is low and X is high. But as the mass is increasing, L band starts picking up, and it is dominating over other bands, and other bands are getting saturated. It is because of the microwave, it's a passive sensors. They were not able to penetrate through the vegetation. But when we have this nicer data, when it is available, it is an active one, we will be able to get the required information. I guess we'll be able to establish a relationship between VOD and above ground biomass. And then finally, I'll come to the thing that what our chairman has said, our job is to retrieve the parameters and disseminate it through the nicest web portal. All these parameters, whatever we have done, and currently we are doing all this data, we are disseminating through the nicest portal. It was started in 2012, and with objectives of main objective is to generate historical database with the at the climate quality standards. And then these are all the in 2012 13 around they are defined committee and earth observation satellites as defined around 50 important climate variables, out of which 28 are amenable through satellites, but that number now 50 has gone up to 54. They brought in like lightning and all other parameters also they brought in, and now we have around 70 products, out of which all are not essential climate variables, out of which around 12 of them are meeting the standards, but the long-term data is what it is missing, and some parameters are not meeting the required repetitivity, like soil moisture we need an every day, but the sensors are not available to generate the such kind of database. And these are all the data sets that we have. And some products we have like 20 to 30 years, and some products we have 5 to 10 years. But this work is going on to populate and to validate more and more products. When we were working on this, all of a sudden in 2017 or 15 onwards, the focus is on how to address these extreme weather events, and we need the data sets on extreme weather events. And when we were even trying to generate climate data sets, but we were not even having data sets on these parameters. Now we have to switch over to answering or addressing these data sets. For that, we have now OceanSat 3 is able to give us good information combining InSat as well as OceanSat 3. We are able to kind of at least forecast pretty well when it comes to cyclones. But when it comes to heat waves, we do not even have data sets. That the data sets that we have is at poor 4-kilometer resolution, and it is whenever clouds are there, it is not possible. And we tried in OceanSat 3 to have a SSTM sensor, but unfortunately it did not work out. But now, right now, we are using SLSTR onboard Sentinel-3. But this is what today morning our chairman has mentioned, that very soon we are going to have a Trishna machine. We are going to have our own sensor for SST related things. And also there we have our SAR data is being very effectively utilized to whenever you have oil spill related detections and all those things. That activity is very seriously going on. And then there is a need from Niti Aayog and all. They wanted to have how much is the energy that they can extract using the solar based energy as well as wind based energy. So we have went ahead and processed all the last 1 year of OCM sensor, recently launched sensor data, and we have generated global wind energy forecast, or not forecast, potential, that how much we can extract. Similarly, it is done for solar energy also, that we are able to meet the mitigation related things of moving from fossil to renewable energy related things. And then this is my almost last slide, that to meet the future needs, continuity of RISAT mission is there, and also Cartosat mission. This is what NISAR, NASA, ISRO synthetic aperture radar data. And then there is a plan for high resolution satellite sensor, and this is same as RISAT. And this is what I was talking about, thermal SST sensor, where we need very badly sea surface temperature as well as land surface temperature. This is the commitment to G20 commitment, that we have to launch one environmental and climate change satellite. That is actually all the G20 countries also, they also contribute their own sensors, and it is going to be our sensor as well as the community level sensor. So this is what, and these are all the future needs. I know very well at one committee, by the time I joined in ISRO, Rajivan sir was heading one committee. In that he said we need very badly the wind profiler. We are still at the same level. We do not have the technology yet, but that is what, even if you want mass exchange or energy, we need to have the wind profiler. That is happening now. It is just started, sir. Apart from that, these are all the needy things for the climate society. LOs. But that is also under cloud-free conditions, and there are some limitations are there, but it was a test satellite. So That's all from my side, and thanks a lot. And all the satellite details and all I have given here. Anybody is interested, they can go through it.
I have a fundamental question. The work carried out by the reports agency is phenomenal, no doubt in that. And in fact, the kind of data sets what you have been giving to the various research organizations across the countries, again, exemplary. But in spite of all these things, why still our IMD is unable to predict the proper weather conditions? They say today they'll rain, they'll not be rain. Tomorrow, it's unable to predict the weather properly.
Sir,
what is the reason, sir?
We have to thank IMD certainly that their forecasting skills have increased almost by 50 to 60% over the period of time. I think we should really appreciate IMD. They have taken steps to improve. It is improved. But when it comes to precipitation, that is a challenging issue. That is something related to the physics involved in that.
But
it is
still,
not.
Our weather prediction is not as accurate as that of any of the European country if you take, or any other country if you consider.
That many
they say that the rain is at 1:30, 1:30 it will rain. Here the rain is people telling in TV.
The number of satellite products that go into their models and the number of data points or the satellites that are available over Indian subcontinents that can go into the model, there is some lacuna is there in that. That is, we have to accept that limitation.
Which of the sector doesn't have their own climate modeling and other things?
So they do that, but the prime thing is the task is given to IISc program, and SAC is part of this. I'm sorry I did not bring all the ISRO centers and also MOES centers. All those people, all those entities are part of IISc, sir.
Thank you, sir.
Thank you.
Good afternoon, sir. So in the last 10 years, we have more data than we have had in the past. But has there been an effort to actually go back in time and enrich the data which has been there in the past in order to, for example, the work that previous speaker was talking about famines in this would benefit a lot from modern techniques for this and kind of going back to enrich some of these data sets there. I'm not sure if there is an
No. It is certainly a good question. Like for example, I'll give you a small example. INSAT 3D, which is available from 2013, but Kalpana is available from 2008 onwards. We have started processing the data up to 2008, but the problem is inconsistency between the number of channels. Kalpana had only 3 channels. INSAT 3D has like 5 and 2 thermal channels. So when we go and when we have to normalize these channels and data sets, whether we may get inferior data set or we don't know yet. That is what we are trying to understand, how to map these 3 channels versus 5 channels database to generate historical database. There are some limitations, but we are trying our level best to see. First of all, we wanted to disseminate the quality data. As far as we are concerned, at least we should get convinced that the data is good enough. So that was our prime motto, but we are doing it, sir.
Thank you so much.
Thank you.
Thank you.
Our next speaker is Dr. Ulka Kelkar. She is the Executive Director of the Climate Economics and Finance Program at World Resources Institute, India. Dr. Ulka has been the co-chair of the Think 20 Task Force on Clean Energy and Green Transitions, an official engagement group of India's G20 presidency, and of the Fair Share, Equity and Justice Working Group of the UN-backed Race to Zero campaign. She has served on the Government of India's long-term low emissions development strategy task group on transport, the National Committee for Carbon Neutral Village Awards, and Science, Technology and Innovation Policy Thematic Group on Energy, Environment and Climate Change. She works on low carbon development pathways, sub-national climate action, and just transition in small industry, and will speak on how much India is doing to mitigate climate change? Thank you. Are you able to hear me on this mic?
No, I'll pump up the volume.
Sure.
Yeah, I'll do that. Yeah.
Yes, to raise the volume. It'll come up. Yeah. Well, good afternoon, everyone, and thank you so much to Dr. Rajivan for the kind invitation to be part of this symposium. And it's especially nice to be at Atria University, which has some very interesting courses. So really nice to be part of this. I'm an economist, so my subject of my talk will be a little different from what you've heard so far. Also, the topic that I'm speaking on is how much is India doing to mitigate climate change? And usually when we say mitigate, we mean mitigate emissions, greenhouse gas emissions. The talk is how much is India doing? It is not how much should India be doing? Is it doing enough? That is a question of choices, often political choices or industry choices or citizens' choices. So it's a technical talk rather than a political talk. What I've requested colleagues over here to do is to link me up to a live dashboard that we have on the internet. Any of you can just go look at it. So I won't have slides. And so I'm going to basically show you what are the implications of India's commitment to become net zero by 2070. So what does that mean? What do we have to do in 2030, 2040, 2050? And what are the economic impacts of that? What does it mean for the economy? So this is a presentation about the economy and not about the climate. This model that I'll be showing you is a systems dynamics model. So the economy is not as complicated as the climate, but it also has some feedback loops. And that's what this model tries to incorporate. So let's enter this simulator, which, as I said, you can go to india.energypolicy.solutions. It won't open on your phone, but it will open on your laptop, and it's designed for general audiences to use. Couple of limitations over here. So, for example, one of the things that this model tries to do is it tries to forecast the future. But just as with climate, these are scenarios. These are not forecasts. So these are what-if scenarios of if the GDP grows like this, if the population grows like that, if the industry grows like this, then what will be the emissions? Given a particular set of choices, it tries to look at the least cost way of providing energy to the economy. So you could provide the energy demand through burning coal and generating electricity from coal, or you could do it by setting up solar plants or wind power at any given point of time. Whichever is the cheapest will get picked up first. Same with transport, whichever is the cheaper. The model does have some inclusion of the fact that technology improves over time. Efficiency improves over time. Technology becomes cheaper over time. There is diffusion in learning. So some amount of that is built in. And I'll kind of show you that. So when we go into the simulator, I think it's a bit slow. You can ignore all of this for now. But if I go down to this technology costs, for example, it's saying that the costs of batteries will fall over time. So these are the assumptions. It's a fully open access model. You can see what the assumptions are. Similarly, if you have, say, hydrogen electrolyzers, we're assuming that the costs are falling over time. If you're a modeler, you can, of course, download this in Vensim and change the assumptions. You can upload your own data sets. But if you're not a modeler like me, then you can just go here and download all the data into an Excel spreadsheet and make your own graphs and do your own analysis. So that's the sort of joy of this particular model. Limitations, of course, it is only for the national level. We know India is a big country, different states have very different contexts. At the moment, this model is not for Indian states. There is a US model that is actually there for many states, so you can look at that as well. It does not have trade with the rest of the world. So that's a limitation as well. India is in this model not connected so if things are happening drastically in the US or in China, that's not drastically changing things here. There are imports and exports, I'll show you those. And it does not have a fundamental change in the economic structure of the Indian economy. So we are not saying, like today morning we heard 50% of India is going to become urban. That kind of change, yes. But there's no fundamental change that, we'll completely stop growing food and we'll import all our food. No, nothing like that. It's a gentle sort of model, so realistic kind of future scenarios. So with this, let's go from the assumptions to the emissions. What do you think will happen to India's total emissions in the next 30 years? This model goes only up to 2050, so I'll ask you only about that time horizon. So what do you think will happen? So right now, India's emissions are around 2-3 billion tons of CO2 a year. How much do you think that is going to happen by the middle of the century?
No,
this is not for experts. This is for people this is not your subject. So usually when I ask generally, people, they say, oh, it will increase exponentially, because people are quite pessimistic. It will not increase exponentially. How much do you think it will increase? You're very optimistic.
So the government is doing a lot of angling that, at least for now, okay.
So it is an increase. It's not a decrease. This is the reference scenario. It's about double. So you're right. There is a lot that the government is doing. There's a lot of renewable energy that is becoming cheaper. We have solar, we have wind. But even then, there is an increase. Emissions from the Indian country as a whole are projected to double over the next 30 years, roughly. I mean, don't take this too literally. It is a scenario. It's not a forecast. It's not a prediction. But yeah, roughly that's the trend. But if we break this down into sectors, like where are these emissions coming from? Right? The obvious ones. Energy, transport. So what do you think will happen to the energy sector emissions? If I break this not into total, but to electricity, what will happen? Now is a good time to be optimistic. Yeah? So we find that in the reference scenario, in the current trends continue scenario, emissions from the electricity sector are almost flat. But they're not going down. We are not seeing that 20% decrease that you're expecting. Why is that? So much the government is doing on solar and wind. Why is it that the emissions are not coming down?
expensive.
Yeah, so we are all of these. More electricity is needed as the Indian economy develops. This is we are trying to grow. We are trying to provide, and coal is not getting phased out in this model, right? So fossil fuel emissions continue. They're not increasing because all of the expansion is coming from renewable energy, but it continues. What happens, do you think, to transport sector emissions? Usually those of in cities, especially Bangalore, we get caught up in traffic jams. We always blame the traffic for everything. What do you think will happen to transport sector emissions? Go down? Optimistic? Huh? Let's see what happens to transportation. It's going up, actually. So it's actually, if you look at the breakup, transport is right now quite a small share. Not many people have their own cars or two-wheelers, but it's growing fast. Yeah. That's, you tell me? COVID. So that's the interesting thing, right? We shut down the whole economy, but it was not a sustained change, right? A moment the economy bounced back to normal, emissions continued increasing. Okay, what about industry? Industry sector. Any predictions? Up, flat, down? Exactly right. So industry is going up. But let's go a little bit deeper into it. So transport, for example, where do you think the transport emissions are coming from? Yeah, specifically road what? Okay.
Shipping and roads.
Yeah, so if we look at transport emissions by vehicle type, this biggest one is trucks. we tend to blame, cars, or sometimes we blame air travel, and all these are important. None of them is insignificant, and they're all growing, so it's all growing fast. But the big one is trucks, and in a way, there's a easy solution there. We used to transport all our freight by railways. Why not try to go back to that, right? So transport. Let's look at industry. Where do you think the industry emissions are coming from? Which industries? Yes, absolutely right. So if we look at industry, the green is cement, the blue is steel, the yellow is chemicals. But industry emissions come from two types of sources. One is when you're burning fuel, so it's the energy use, and the other is the process emissions. So when you're trying to convert clinker to cement, or you're trying to do whatever to iron to make it into steel. So if we look at it by, say, energy emissions, we find the blue, which is iron and steel, is the biggest. Yeah? And this is easy to decarbonize because you can try to electrify as much as possible, try to get that electricity from renewable sources. But if we look at process emissions by industry, we find the yellow becomes bigger. The blue is very small, green is important, which is cement, and yellow is chemicals. These are process emissions. This is why industry sector tends to be called the harder to abate sector. Because unless you find a new way of making cement, a new way of making steel, you can't actually get rid of these emissions simply by converting to renewable energy. And that's what a lot of innovation is actually happening on. So now what we'll do is we'll look at the total emissions, and we'll do an interactive exercise where, as you can see, emissions are going up, but India has a net zero target. So this curve has to come down. How will you bend the curve? What are the policy levers that you would apply if you were the Prime Minister or the Environment Minister or whatever? What would you do? So there are over here hidden a lot of policy levers. You could ban things, you could set mandates, targets for things, you could tax things, you could subsidize things. In all of those sectors, how would you bend the curve? What's the first thing that you would do? Sorry? Reduce coal. So how would you do it? What would you do? Would you stop coal power plants overnight? Would you?
Move to solar and
Yeah?
Adding the storage is both cost competitive and faster to commission.
Okay, so in electricity, these are the options. You could retire the power plants early. You could ban new power plants. You could, set a standard. So the way we do it over here is, sorry, I can't even see this very well, but you could set a kind of carbon-free electricity standard. So let's play with that before we ban all coal. Yeah. So carbon-free electricity standard. How much of electricity do you think needs to come from carbon-free sources? So solar, wind, nuclear, all of that, non-fossil sources by 2050. How much of, say, out of 100%, how much of electricity should come from? 50, 60. So let's try all of that, right? So let's try 50%. So nothing happened because we should actually go not to CO2e, but to, let's try to do it only for CO2. Yeah. Nothing much happened with 50%. Let's try 60%. Very little something happened, little tail. Why is this? Why 50% of electricity you have put as non-fossil or carbon-free? 50% of electricity generation in this case has to come from non-fossil. But nothing bent. Only at the end you bent a little bit with 60%. Why is that? Exactly. We already have. So when you were saying that so much is happening, you're on the right track. There is a lot that is happening, but so you need to go beyond that. So let's go beyond that. Let's try, say, 70%. Yeah, and just be careful, the axis will shift. Yeah, the y-axis will shift. Let's go to 80%. So now you see it bending. Maybe you have to go to as much as 90%. Good. Yeah, but 90% of variable intermittent electricity in the system means the entire system needs to change. Needs storage, need to strengthen the grid. You need to change the way you do power purchase agreements. And yeah, it's a massive shift. Huh? Grid stability, exactly. But if you want to bend the curve towards India's net zero 2070 target, that is what it will entail. Any other, we won't go endlessly, I won't keep you trapped. So any one or two other levers if you want to try out in any other industry or transport sector.
Fertilizer-related things in the agriculture sector. I'm very curious.
So this model is not very good at agriculture, but we can see what there is. So there is things like afforestation, then there is some rice, improvement, there's some livestock improvement. I think fertilizer might even go in the chemical sector. So let's look at any one of these. So right now I'm in CO2, so none of these are going to be very useful. Anything else anybody wants to try?
No, we talk about only CO2 emissions, but
you can do both. So I am in the CO2 curve, but you can do methane, for example. The target,
agriculture is one of the major contributors for the greenhouse gas.
Let's look at that. Yes, let's look at that.
Methane, the cattle and agriculture.
So let's look at that. This is CO2 equivalent terms, and the green is the agriculture, and the gray is actually industry. So even when you convert the methane into CO2 equivalent terms, we find it's quite interesting. So electricity is big, but easy to decarbonize, relatively easy to decarbonize. Transport, which is a red, is small, but growing fast. Industry, as I said, is hard to decarbonize. And agriculture is somewhere in the middle, right? It is important. And so it's interesting when you look at things from a long-term perspective. So anybody wants to try any favorite? Huh? EV. Okay, all right, let's do. So the good thing is you did it in the right order. You first decarbonized your electricity, and now you're saying let's look at EVs. Had you done it the other way around, there'd have been no effect on the curve. So where did our transport go? So EV sales mandate. So it's basically saying you're the prime minister, you want to say this many vehicles should be electric sold by such and such year. So what would you like to do? How many vehicles do you want to become electric by when? 60%. 60%. Okay, so we'll just put 60%. 2030. So what you can do is you can go in here and customize the implementation schedule, but I'll leave that as homework. And you can do it separately for each type of vehicle. So for example, you might be more optimistic about passenger transport than you are about freight transport. Let's make it 60% for now. And you see there is a little bit of a change. If you, for example, go exactly into, say, transport emissions, you will see a kind of a change happening. But even 60% will not be enough. It will have to be pretty much close to 100% by 2050. Remember, it's 2050. So 2030, 40 will be intermediate. So I think the message from here is really that it will take quite a lot. It will take much more than current trends continue. And what it means is that the entire system will have to change. Because just imagine if you're saying 60% EVs are not enough, you have to go to 90%. I mean, no more petrol pumps. EV charging is required, not just in cities, but even in long distance travel. So it's an entirely different economy, right?
Money for that.
Yeah. So most of it should come from the private sector.
No, that's not fair.
No?
That's slightly unfair because if you look at the projections, even in the US economy,
40%
is private, 20% is government, and 40% is tax. That's how the US is projecting it. So I think throwing everything at the private sector in India is absolutely not fair.
I think it's fair, but anyway, yeah.
Actually, if we are increasing that electric vehicle 60-70%, then will it account for the increase in the electricity demand?
Yes. Yeah. So you have to keep meeting the demand at every stage, and you have to keep meeting it through whichever fuel is cheaper. And you have to then add the cost of building that much renewable energy or that much coal. All of that is so that's why I said it's a systems dynamics model. It does do that. So on the good side, what it means is it might also create new jobs. Because if you're installing new things and you're manufacturing new things, so it adds up. So what is going on over here? Yes, discard the changes. So we tried to do this same experiment, this thought experiment, and said, okay, this is the business as usual type of scenario. And if we want to meet, we want a pathway to be aligned with India's net zero target, then this is something. And how did we get there? Of course, this is not the only case, right? It's just a thought experiment. You could come up with a different combination of factors. One of the reasons why we came up with this particular combination was because we wanted a positive effect on the economy. We don't want to lose jobs. We don't want electricity prices to soar and inflation to happen, right? So we were keeping an eye not just on the emissions, but also in the economy. And we came up with some. So we didn't ban all coal power plants right away. We said, let's keep them, let's do it slowly. But let's just look at, yeah. So what we get is a whole rainbow of actions. So everyone has maybe a favorite solution that they think this is the key. But actually there is no single silver bullet. There's no single key. These colors are showing the sectors. So blue is sort of industry, brown is kind of electricity, red is kind of transport. But all of these actions, and then there are some which are, like an economist's favorite action. So there's a little carbon tax there. It's not a big one, it's a small one, but you need it to have some shifts. Then there are some engineering type of solutions. So for example, there's what we call circular economy, material efficiency, not just energy efficiency, but recycling, steel scrap, cement, debris, all of that. There are standards, there's shifting of modes. There's everything, and you will need everything just to get from here to here, even with the 30-year period that we have. But if we, so my sort of favorite message to young people in particular is work on any of this. Whichever sector, whichever industry you want to work in, there is a contribution. But what if we were to take these and line them up by order of cost, from the cheapest to the most expensive? And we find that there's a lot of options that are actually negative cost, meaning they pay for themselves. The catch is that investment has to come up front. Over time, you will save energy, you will save money, but that you will also improve health. But that will take time. In the beginning, the investment has to be made by somebody, but it will pay for itself quite a lot. I don't know. It's hydrogen vehicles. So sales mandate, because that's the way the model does things, right? It gives you the power to be the minister and say, what policy would you apply? So here it's saying, let 30% of all trucks become hydrogen. There'll be electric also, but some hydrogen. That's too expensive at the moment, at least. Anyway, but this kind of tells you what to go for. We have mode shifting. Mode shifting is the cheapest. It's actually the cheapest. Oh, what is mode? So meaning, for example, you shift from cars to buses, from aircraft to railway, and you can kind of look at it. So for example, I can go into this transportation. I can go to mode shifting. And you can see what assumptions we've used. So we're assuming 30% of cars are shifting to buses, 10% of aircraft are shifting to trains. We've not done anything about taxis. We have said 25% of road freight will shift to railways. And you can change all of this in the web interface. If you want to go deeper, you can download it in Vensim and do that as well. So yeah, let's maybe just take another 2-3 minutes just to wrap up. Couple of things I wanted to tell you about the economy. One is, if you want to look at health, all of these things we're doing from a climate change perspective, right? But because when you reduce CO2 emissions, the things that you do to reduce CO2 emissions, you also reduce particulate matter and other types of gases. So there is avoided premature deaths. You can also put this in money terms. Then you can also look at water, for example. Just ignore this. So this is water used by coal power plants coming down as the coal gets phased down. Why is the water coming down? Water use? What is the connection between coal and water? It's actually used for cooling. So even nuclear power plants, thermal power plants, they generate so much heat that you need to send water just to cool them. And the water is extracted from the ground. Some places like Gujarat and Tamil Nadu use coastal seawater. But most places they use groundwater and then they again release it and farmers can use it or whatever. But so there's a huge water saving that you can do. In terms of the economic benefits, we find that actually there are some jobs that will be created. So these are electricity sector jobs in red. Blue is manufacturing jobs, like you're producing more electric vehicles. And yellow is other jobs. So these are more indirect jobs. I'm happy to go into this in more detail. There's a lot that is happening at the back of the model. But as I said, our assumptions are such that this line is not becoming negative. There are many things we could do, but it would have a negative effect on the economy. Maybe just one last thing over here. I was saying we have imports. So India currently imports a lot of its oil, right? So when you said let's have electric vehicles, we actually reduce the need to import that much of petrol and diesel. So this is actually, in money terms, this is lakh crores per year. This whole red thing is the savings on crude oil imports. So from a government perspective, this is a gain to the national economy. We don't have lithium yet. We are building that in. As of now, it looks like the lithium expenditure, import expenditure will be less than what we save over here, but we don't have that in the model right now. We are updating this. But there is another catch right now. So if we look at, and this is honestly the last one. Actually, let's skip that. It's fine. So
Anything regarding nuclear power scenario?
I don't have too much, but I can show you over here. We don't have small modular reactors, but you could have, like for example, I'll just show you what the. So this is where is nuclear in this? Green. So it is this much. It's a little bit. We don't have a huge, but that's also a choice. You could make a choice that you have much more nuclear. It might increase the costs. Another choice we have made is we have not put carbon capture, utilization, and storage. That lever is there. We have not included it in our assumptions in our package. You could include it, and you could say we'll deal with the cost of that.
It's a huge cost.
It is a huge cost, which is why we didn't use it. But it's there as an option. If you as a policymaker are much more aggressive, you can take in all of these things. So I'll just wrap up my presentation by just saying a few things. One is there's a whole of economy transformation. It is not an energy sector. It's not an environmental thing. It's really going to affect all of the economy. There's no single solution. You need everything. The problem, of course, is that even if the aggregate impacts are chosen very carefully, that the aggregate impacts for the economy are good, there will be regional differences. There will be gender disparities. There will be winners and losers. So what we will need is complementary policies, economic policies and social policies, to complement these climate policies so that the overall effect is good, not just for the economy, but also for society. So thank you very much for your attention.
Madam, after listening to your lecture, I had one basic doubt. It may not be appropriate, but I wanted to just check it out.
Yes.
See, to keep up the development and you are unable to avoid the CO2 emissions.
Yes.
Right? There is no single solution. It's better to allow this to happen and capture the carbon and try to do something. Did we work on that?
Yes.
Capture?
Yeah.
If CO2 to come out, let us use whatever it is. Is there any way of capturing the carbon and reducing it into the atmosphere?
Yeah, so we do have carbon capture equipment costs in the model. This is an assumption. You could have it as a lever over here. So I think it's somewhere in cross sector, I think. Or is it in district heat? Yeah, so you could have direct air capture, carbon capture storage. You could put that in the model and see.
Talking cost of carbon capture. But now the technology is still
Yes. Yeah. So whatever is the literature or the industry studies, and you can update this model or update the assumptions. But as of today, what we know, whatever is the best we know, that's the decision you have to make. So what you're saying is, yes, we could continue emitting and wait for the cost
Sorry, you talked about your favorite tool, carbon tax, right? I wanted to, maybe hear your comments about carbon credits.
Yes.
It's been an extremely controversial topic, both in India as well as in international circles. Seems the government is working on a carbon credit platform which is going to come out in the next year.
Yes.
Do you see that playing a big role? Should it be?
Yeah.
What are the things that we should be careful about?
So one of the nitty-gritties of this is that there are actually two interpretations of carbon credits. One is what are called carbon offsets. That is, you use these lights, but then you plant trees outside. So you offset your emissions. That is slightly risky because you could go on increasing and you may not actually. So they feel everything is greenwashing, everything is useless. It's not all useless. There are some things worth doing, provided the rules are robust.
Yeah. So how do we make the entire thing just?
Yeah.
Is there anything in your model also that,
No. The model currently has policies which the outputs give you some hints about the injustice. So, for example, is it good for the economy? Is it good for society? Is it good for nature? Because you could have plantations, for example, that sequester carbon, but are actually, you're not letting people use the non-timber forest products. You're not letting people, say, wash their clothes in a wetland. You're not allowing them to fish. So there are many, people, nature, climate, all of these have to go hand in hand.
Yes. Good afternoon. So I had a question. You've mentioned that there's something similar in the US also.
Yes.
And here. Has this actually had a direct link to any policies?
Yes. Yeah.
I think a lot of people have spoken about the problems, but are a little clueless about how this will get implemented going forward, right?
Yeah, so in the US and Europe, in Germany, they tend to have a little more of a tradition of using modeling results like this to inform their policies. They are also conservative. For example, the US, when it picked its NDC target, its long-term target of I think a 45 or 50% reduction, the modeling actually showed 55% was capable. So they also tend to leave a little buffer, conservative. India also tends to say if China is saying 2060, we'll say 2070. I think more and more there is a willingness to look at such modeling analysis, but there is a healthy skepticism also. For example, we work very closely with Niti Aayog, and the chief economic advisor says there's a trade-off. Should I invest in health and education, or should I invest in green hydrogen? There is a kind of choice to be made with scarce budgetary resources. These are valid questions. So all we can do is present information about the trade-offs, the choices, then it is up to the policymakers to.
Niti Aayog uses this model.
This model is actually linked from the Niti Aayog website, so they are looking at it. Yes, there are other models also they're looking at, and sometimes models say different things. Just like with climate, maybe you need an ensemble.
Yes. Normally they go out and US
No, they're quite suspicious about outside models. Yeah.
So it's very complicated. We scientists are far better to say climate is changing, easy to write papers, but
Good afternoon, ma'am. Good afternoon, ma'am. Good afternoon. Ma'am, my question is in relation with the flattening of the CO2 emission curve.
Yes.
And through an example, I want to give you the example that India as a country set its gigawatts of renewable power generation in 2025.
Yes.
But as a country, we achieved it way before, 4 years. So my question is, how do you see the impact of the policy, like transition? Can we accelerate the transition towards green energy and environmental regulations? How do you see this impact of policy making on the achieving this dip in the curve very early in the CO2 emissions?
So it is actually quite difficult. The government of India has two targets. To the international community, it says we will do 50% of our electricity capacity will come from non-fossil sources by 2030. This is what is called our NDC target under the Paris Agreement. But there is a target that it has, which is not in the NDC, which is 500 gigawatts of renewable energy by 2030. Now, if those lines that I was showing you for the reference scenario, the model doesn't give you 500 gigawatts. 500 gigawatts is not going to happen on market forces alone. Even with solar becoming cheaper, wind becoming cheaper, even with all of these policies, the models doesn't actually even show it as theoretically possible. So the government of India's domestic policies are actually very ambitious. Then there are specific components like rooftop solar. We had a 40 gigawatt target. We could not meet it. So I think the targets are good. A lot needs to be happen a lot needs to happen to achieve those, because you can set a target, then you could have a kind of way to get to that target. So you say 2025 will be here, 2030 will be here, but through what instruments? What subsidy will you give? Will you give it to the consumer or will you give it to the manufacturer? Will you set a sales target or will you set a tax? These are all choices that, there's a lot of actually learning by doing and a lot of feedback that we'll have to see.
So the final conclusion is by 2070 we will not meet the target.
No, that's not my conclusion at all. We'll maybe do even better. Maybe.
Okay. So thank you, Ulka, for your wonderful talk. Thank you for coming here and talking to us. So this book we must have seen already.
Yes, thank you so much.
Thank you.
Thank you.
I know her for last 25 years. Her father was my boss in IMD. Thank you, Ulka.
Our next speaker.
Oh, thank you so much.
Our next speaker is Dr. Chandni Singh. She works at the interface of climate change and development in rural and urban geographies within the Global South as the lead practice, School of Environment and Sustainability, Indian Institute of Human Settlements, Bangalore. She works on issues of climate change adaptation, differential vulnerability and well-being, disaster risk and recovery, livelihoods transitions, and rural-urban migration. Dr. Chandni serves on the editorial boards of Regional Environmental Change, Climate and Development, and IIHS's in-house journal Urbanization. She is the domain editor on vulnerability and adaptation at Wire's Climate Change and a contributing editor within Carbon Brief. Dr. Chandni will speak on climate change vulnerability and adaptation, current understanding, and research gap.
Thank you so much. I hope I'm audible. I would say congratulations to everyone for sticking around to so far for the last presentation. It's never easy to be between people's coffee and the last presentation, but I hope to keep it not too long and slightly interesting, and also continue what Ulka started on solutions. Is there something I have to do? Okay, good. Thanks so much. Yeah. So, I think one of the parts of the story that Ulka spoke about is mitigation, which is reducing emissions. And the other part, which I'll speak about, is adaptation, or actually managing some of these risks and horrors that we have been hearing about since morning. All right. So, I'll just start off. Climate change, and then what. So just quickly, I don't need to say this at the end of this long day, but the working group 2 meeting, the working group 2 report really says a couple of things. First, the scientific evidence is unequivocal. The fact that climate change is a threat both to planetary health, but also human well-being. And also very, very clear signals that Asia in particular is a region that is most at risk. And these are some of the figures that we show after assessing thousands of journal articles to sort of comprehensively say what are the, please can people stop talking? Yeah. It's a little distracting. So we assessed a large pool of papers to sort of find out what are the key impacts on water scarcity and food production, health and well-being, cities, settlements, and infrastructure. And what you'll see across the Asian region, of course, we were also assessing literature across 52 countries. That's how diverse and large the Asian region. What you see is, of course, most of these signs are minus, which show that there are negative impacts. Some of them are plus and minus, and that is exactly picking up from what Dr. Vimal Mishra was also saying on water scarcity. There are some places which will have extreme rain, some places having drought. It also changes depending on what crops you are growing. So there are uncertainties around, or rather in some literature you have a positive effect and in some literature you have a negative effect. But what is more interesting, which is the dark blue colors you see, which is high confidence statements around heat, malnutrition, mental health, and displacement. So Asia is going to see extreme impacts, negative impacts around these things. So we've got a story of increasing risk and increasing impact across Asian countries. But we also know that adaptation action has been increasing. Across the globe, all countries have reported adaptation action. That's what the IPCC says. But while this action is increasing, it's inadequate. So it's not reducing risk to the level that needs to be reduced given the kinds of climate projections and realities we're seeing. It's uneven. That means some places are adapting faster than others, often because of the kind of money they have, the kind of data they have to make decisions. Adaptation is very sector specific. So particular sectors are adapting faster than others. And then also, this is something that I've been talking a lot about. You've got particular adaptation strategies for particular hazards. What that means is you'll have a heat action plan in a particular city, you'll have a flood resilience plan in a particular area, but not having comprehensive climate risk reduction or climate adaptation plans, either in cities or rural areas. And so that's why there is this gap between what we are supposed to do versus what we are doing currently. And this is what we call the adaptation gap. Also, we have shown quite clearly, I mean, especially, I guess, for Asia, but also within that in India, this adaptation gap, so the gap between what we should do versus what we're doing, is largest for the poorest parts of our population. So there is also an inequality in who is able to adapt and where adaptation priorities and money is going. I then always use this slide and this quote from this book by Gendres and Amartya Sen, which really talks about, I'll read out the quote. India's growth story is making the country look more and more like islands of California in a sea of sub-Saharan Africa. Why I say this in a climate adaptation talk is because while we can be talking about climate change, we are a country that has poverty, inequality, deep development deficits. So we have to understand all the modeling that was shown in the morning, the satellite imagery, all of that is overlaid on a story of islands of California and a sea of sub-Saharan Africa. And so if we are thinking about reducing vulnerability and increasing adaptive capacity, adapting, we have to think about how we are going to first bring the people who are in the sea of sub-Saharan Africa to a level that they can then deal with the flood and a heat wave and so on. And I think the first presentation alluded to that in the morning about some people being able to use air conditioning, for example, in heat wave scenarios, while other people won't be able. So keeping this in mind, again, I'm not going to go into too much detail. Krishnan sir just left, but of course, led this work on climate impacts and risks across various climate impact drivers in the country. I think this still, to me, is at least the first IPCC Working Group 1-like assessment, but for India. What I do want to say is one more thing that we understand better now is that hazards don't come singly. So there's a compounding of hazards, heat waves and droughts, for example, heat and fire, for example. So there's a compounding of hazards and a cascading of risks. By cascading risks, I mean that what happens, so you might have drought-related famine and food production decreases in rural areas, that then cascades to food insecurity in urban areas as well, market prices going up. So this, if we are thinking about adaptation, we really need to think about the fact that the risk regime itself is changing. You can't be thinking of single hazards and you can't be thinking of single sectors. And this, as Ulka also showed, is more difficult. I mean, it's easier said than done because working across sectors and across geographies is often very, very difficult. I just want to sort of say something about what do we really mean when we say adaptation. So many people here must be familiar. This is the risk propeller from the IPCC, which says that risk is a composite of hazards, what kind of like heat waves and cold waves and droughts and so on, vulnerability, underlying structures in our society, and of course, exposure, which is the fact that there might be a heat wave, but if you are not outdoors or if you're not exposed to it, you will not face the risk of it. So what adaptation then is this reduction of risk. And if we are to look at reduction of risk, you would, and this is some examples of reducing vulnerability, reducing exposure, reducing hazards. And there are multiple ways you can do it. And I wanted to give some examples of different things. This is an example, of course, reducing risk and adapting due to coastal hazards and coastal risks. So you can reduce the hazard by growing mangroves and sort of stopping storm surge and flooding. You can reduce exposure by actually resettling people away from the coast, moving people inland. So you reduce the exposure. And you can reduce people's vulnerability by providing flood insurance, for example. So these are different types of strategies. And again, choices have to be made between, do you actually put in a lot more money on flood insurance? That's a whole different system. We know insurance has not worked very well even in crop insurance in our country. So how do you get very poor people to actually pay premiums? So there are trade-offs associated with all of these. But what I want to highlight is that you have to do all of these things simultaneously: hazard reduction, vulnerability reduction, and exposure reduction if you really want to adapt. I will not go through this, but so I've spoken a lot about adaptation. There are a lot of examples of adaptation really across the country. Primarily, adaptation had focused a lot on agriculture and things like, again, people spoke about it earlier, improving irrigation efficiency through drip and sprinkler irrigation. That was considered an adaptation strategy. Trying to think about changing crop timings and sowing, changing crop varieties, shifting crops, all of that, these are considered adaptation strategies in agriculture. And a lot of money, effort, policy attention has gone into that. More recently now, we are seeing adaptation interest in urban areas, things like heat action plans, trying to build advisories around heat or floods, especially before these extreme events come. So while on the one hand, a lot of adaptation is occurring, there is also, so things are progressing, there's also this increasing risk of maladaptation. And this is something I think even in the Indian policy circles is a sort of taboo subject, because we don't want to accept that some of these things that we're doing with good faith are actually not reaching the people we want to, or is not at least leading to the risk reduction that we want to have. So overall, globally, if you see, and this is from the Adaptation Gap report, we don't have very good numbers for India, so I couldn't show those. But over time, what we're seeing, this is basically showing that investment and number of projects on adaptation is increasing over time. So from 2006 to 2022, when this report was published, you're seeing a growth in adaptation action. And what you would imagine that if you are seeing this growth, you would see a decrease in risk. This is what we call the burning embers diagram. This basically shows that under limited adaptation, your risk is very high. The purple and red colors are showing exponential risk. And when you undertake proactive adaptation, your risk is much lower. And so basically you're saying that on the one hand, we had this figure which says adaptation action is going up. On the other hand, we know that if we adapt, risk will reduce. So ideally, what we should have seen is lesser people are exposed to risk currently, and yet we see more and more infrastructural damage, loss of life. Of course, the risk itself is increasing, but there's something going wrong with adaptation, which is not reducing risk. And this is what we call maladaptation. So maladaptation is basically unintended negative consequences of adaptation. Things that we wanted to put into place to reduce risk are actually increasing risk. And I've picked up two examples. There are several from across the country, and it's also very difficult to delineate adaptation and what is just good development. Similarly, what is maladaptation and what is just really bad planning and bad investments. But this example, and Chennai around this, looking at how post the tsunami and then post the 2015 floods, people have been evacuated from along the Adyar and Kuam rivers and then been brought often 30, 40 kilometers away from the city center and put into high-rise buildings, low-cost housing for these people on the base or to sort of reduce their risk. So the argument was these rivers regularly flood. Climate change is exacerbating some of this, although we knew that 2015 floods was a mix of environmental and man-made or human-made reasons. And then sort of moving people, I mean, in this case, people were moved into these G+7, ground +7 tenements. Now, what happened in this situation is the places they were being moved to were actually wetlands. And over time, so they moved from flood risk, but moved into another kind of flood risk. Now, they were also away from the city center, so jobs were lost. Many of them worked as domestic workers, cab drivers, and so on. So you've got a sort of increasing profile of risk, which was unintended, which was actually done on the pretext, or I think with the intention of risk reduction and adaptation, but led to further exacerbated risk. The other example is of the Karnataka coast. I think a lot of, and this is not only Karnataka, all across our coast, coastal hardening is one of the strategies that are being used, which is that you're building sea walls to sort of keep the water out and protect our coastal populations. While that, of course, is a good strategy and also protects people for quite some time, multi-decadal. But what's also happening is a lot of people have this false sense of security and then stay in areas that are risk-prone. And that is then leading to some of these people living in these areas that are actually uninhabitable just because of these artificial structures. There's a lot more to speak on this and various examples. The empirical literature on this is actually quite thin. And I purposely talk about this when I speak to students because I hope more people can actually challenge some of this. It may not be as simple as what I'm saying. And so, but we need more research on what are the mechanics of maladaptation and then how can we really avoid it. That's what we all want to do at the end of the day. So risk management, I mean, there are a range of strategies to manage risk. And this is actually from 14, 15 years ago, where I was looking at how farmers in rural Rajasthan are actually adapting to that. Basically, what you see is some people don't do anything at all. There is no response. Some people are adapting and coping positively. And then a lot of people, as I said, are maladapting. There's negative adaptation that's happening. And this is what we call the response continuum. I want to also highlight this because we often sort of just say adaptation and maladaptation, but there's a lot happening in between and different households and also different people within households are doing different things. So while we understand this idea of adaptation and risk reduction, there's also the twin challenge of meeting some of our development needs. And this work by Haley Eakin has sort of conceptualized all of this to say that on the one hand, we are doing a lot of things. We have, for example, the NREGA scheme, things around PDS, rations. We have the right to education. So there are a range of development policies that we have. And many people say that this is good. This is building our capacity to even deal with other kinds of things like climate. But in this framework, what she says, and then what we have applied in the Indian context is that these only build generic capacities. These are capacities to meet our basic needs for food, water, shelter, and so on. But what climate change adaptation really requires is building specific capacities. And to build specific capacities, you need to do much more. So if you are building only your generic capacities, you might, and not any of your specific capacities, when you have a drought or a heat wave, you might remain in a poverty trap. But if you are building both your generic capacities and your specific capacities, you might actually lead to what she calls the sustainable adaptation quadrant, really. And we then apply this kind of thinking, and there's this paper that we've written on how different people, we were looking at farmer communities in Maharashtra, Karnataka, and Tamil Nadu, to show that actually some of these, so the things that you see in green are actually some of the strategies that are called adaptation strategies. livelihood diversification, crop diversification. These are things farmers do every day in their lives to sort of deal with risk, taking loans, community-based groundwater management. These are various strategies that farmers employ. And then you've got things in blue, which are strategies that the government is employing. So watershed development programs, having better climate information services and sort of advisories, weather-based insurance schemes. And when you start plotting it against whether they are actually meeting some of them, and usually these kinds of things which people are doing on their own autonomously, these are just only building, they're not building generic capacities or specific capacities. So people are getting trapped in that kind of situation. Whereas things where you might have livelihood diversification, you might sort of be building natural resources, those are sort of things that are then helping you to move towards that sustainable adaptation quadrant, which is where we want to be. And this is not easy to do. This is also, so currently, I think a lot of our government policies tend to focus on the safe development paradox, lift the most people out of basic poverty, give them basic access to services, infrastructure, all of that. But we really have to start moving towards this quadrant is what we argue in this paper. And then finally, I just want to take you through a piece of work that we did in Karnataka around migration, looking at the fact that now rural livelihoods are increasingly becoming more difficult. You've got the story of, on the one side, you've got the story of increasing drought, groundwater depletion, changing cropping patterns, but you've also got the story of changing aspirations. A lot of farmers I speak to, their children don't want to remain in farming. There are various studies that have shown how I think there was a national study in 2017, only 5% of children of farmers want to remain farmers. So these are the story of rural India is changing, and climate change is only one part of it. And what that's the other part of the story is that people are coming to urban areas. Someone I think in the morning also spoke about this, that what do we do with all these people coming in? But we must understand that most of our cities are being built by these migrants. Recently, I can't remember what it was, but 2 months ago, there was some news that Bangalore's metro is not, the construction has stalled because all the migrants, I think, had gone for Chhath Puja, which happens in Bihar. So, these kinds of, not Chhath, it was another festival, but these kinds of ideas of what these people from rural areas who come to urban areas do in our cities is often very invisibilized. And what we were looking at really in this paper and in this work is what happens to people when they come here, and are they able to adapt or not? Because in 2016-17, when I was doing this research, I started it out, there was very little imagination of urban adaptation. All our adaptation was happening in agriculture systems, crops, water systems, but not as much in urban areas. So we know from the global work and studies in India that economists have done that climate change is impacting how people move. First, how people conduct rural livelihoods and agriculture, and then how people move. There are several large studies using the census data. I know it's outdated, but also other surveys to sort of show that drought, especially also rainfall variability, is leading to people's movement. And some studies show that increased movement, some studies show altered movement. But also what I want to highlight is that this movement of people from rural to urban areas is not equal. Everyone doesn't get to move. Actually, the ones who have the best networks, most education, also land, they are the ones who tend to migrate first. People belonging to oppressed classes and castes, they are actually the last to move. Only in distress migration situations where entire villages move, and we have stories of that from Uttarakhand, but also North Karnataka, Rayalaseema region, and so on. So migration happens because of climate risks, but also filtered through the local or household socio-economic context. And of course, migration leads to different outcomes for different people. So what we were doing is, and I'll go through this very quickly, what we were doing is looking at rural to urban migration from North Karnataka, in particular Kalaburgi district in North Karnataka, into Bangalore, and also looking at commuting or daily movement between Kolar and Bangalore to see how these different kinds of movements, first of all, are they climate driven or not? And then what happens to people when they come in. And these two districts in particular were chosen. They are vulnerable and exposed to climate risk. Both the trends, past trends and future projections show a story of increased rainfall variability and increased heat, land surface temperature. And then on socio-economic indicators, the government of Karnataka itself has identified both these districts as extremely vulnerable. And these are the kinds of responses we would get in the field. Ours is a cursed village. In bad years, dry years, even migrating is difficult. Migrants have to stay on roadsides. Manual labor work we do is exhausting and we don't get good food. And these are, I mean, this is just an example. We conducted around 1,800 household survey. We conducted around 50 focus group discussions with men and women, speaking to various creating timelines where we would bring climate data and then actually make people construct their timelines of climate risk. And basically what we show is that a lot of outcomes of migration are differentiated within the household. So these very simple graphs are men and women within the same household, and we said, how do you feel you're doing before you've migrated and after you've migrated? And some households show an upward trend where they report that their quality of life is increased and so on. And some, of course, show a downward trend. I'm not going to go through all these examples, but just to give you an idea that when there are non-climatic extreme shocks that happen in a household, no matter how much you have stayed in a city, earned, lived, accumulated, it leads to downward trajectories for households. And so given this, what we were basically arguing in this work is that the act of moving out from an agrarian livelihood is a way that people manage risk, and it's a way that people spread risk, climatic and non-climatic. And climate change is one driver out there that is sort of putting a deep burden on farming and pastoral livelihoods. So the space to sort of adapt and make a living in farm livelihoods is narrowing. But on the other side, when people are coming into cities, and these are field pictures, so these are sites where migrants are living to build the houses that are at the back, and these are typically migrants from Raichur, Gulbarga, Bidar, and so on, will be living in these blue tent settlements in our city, not too far from here. And so basically, you're moving out of a certain kind of risk, but you're moving into another kind of risk. Often people from Kolar and Gulbarga who are used to drought and water scarcity and have practices around conserving water now are living in a city that is flood prone. So you have no experience and sense of how do you deal with the issue of too much water and leaking roofs and vector-borne or waterborne diseases that come with issues of flooding. So it's a complete, this idea of risk changing for a household, and then so how do you imagine these households adapt? And that is why I keep on saying that the onus of adapting should not be put on the most vulnerable. You do have to, yes, we do need behavior change, we making our own shifts in how we manage risk, but the most poor and vulnerable will need state support. And also assuming that hybrid alliances of, say, private, public, NGO kind of things will somehow magically help this adaptation, I don't think that is going to happen. Mainly because everyone is coming with their own priorities. It has to be a state-led thing for the most vulnerable. All right, so this is the last slide. I think since morning, since I made these slides, I think the numbers have changed. So I think it's 1.38 now, global average warming since pre-industrial levels. That, of course, means different things in different parts of the world. And in India, it's not as much. But what this warming, unequivocal warming trend shows that the imperative to adaptation is clear. Yes, I would say, and many people again criticize me for this, but I will still say it, that mitigation is the best form of adaptation. The first thing we need to do is bend that curve that Ulka was showing us so clearly. Till we don't bend that curve, we are going to see more extreme events. And what do we do in this case of more extreme events? Either we cope, or we adapt, or we maladapt. So the act of adaptation is We just have to do it. There is no answer, and different people will have to do it differently. What I didn't talk about too much in the presentation, but just do want to highlight is, just like on the mitigation side, there are a range of adaptation options we have. Across sectors, across scales, there are different things we can do. I gave you a flavor. Some are things like hard options, like seawalls, increasing the plinth of buildings during flooding. Some are softer options, like behavior change, making sure that heat advisories go out to people and people actually use them. So there are a range of options that are there, but the feasibility or the possibility of them actually being useful are very context dependent. And also it's dynamic. Feasibility can change if we have a new subsidy, a new policy focus, and so on. There are a range of policy instruments that are currently present in the country, from national action plans on climate change, state action plans. There are sectoral policies. Then we have the whole disaster management infrastructure, like state disaster management plans and district disaster management plans. And so if you look at it in total, adaptation action has definitely increased, but it is uneven. Some parts, for example, our northeastern states, even urban areas as compared to rural areas, there is uneven adaptation that is taking place. And as I said, we might be building a lot of generic capacities because that is where the challenges, development deficits remain. But we need to build specific capacities to climate risks. And that is a whole different thing. And this idea of additionality, of adaptation beyond development, it's still something everyone is grappling with. I think it's not only an India problem because it's very difficult to track. We don't have good ways to track, say, like how Ulka was showing, CO2 equivalent and emission reduction and CH4 emission reduction. We just don't have those numbers for adaptation. You can say tens of thousands of people impacted by a particular policy, but to what level, which people? So there's much more lack of specificity, I would say, in tracking adaptation, which is why it's also very difficult to make a business or economic case for adaptation sometimes. And then, of course, my last point, which is that can we really preempt some of the bad things that we are doing in unintended ways and preempt maladaptation? And a lot of adaptation scholars globally and in India have sort of summarized is that we need to stop making some of the mistakes that the disaster management policies and implementation has made. So not only focusing on relief, but also long-term recovery, not being reactive, but also being proactive in our planning, and also being flexible in how we make decisions. So if we have a heat action plan, there has to be a way that we have some monitoring of it, learning of its efficacy, and then actually changing it. Just having a heat action plan and a tick mark is not enough because that's not reducing risk for the most vulnerable in any way. Okay, I'll stop there. Thank you so much for your attention. It's a very tough job, sir.
Yeah, thanks, no, but I will just brief you. I will please. Yeah. Just before that, let's see. We arranged the presentation in a sequence way. First in science.
Yes.
Yeah. So that's why Gulka and your presentation is not. That doesn't mean that your presentations are not important. For me, Gulka's presentation and your presentation is more important than us. Let me ask a question. In India, how many Gulkas and Chandris are working? For example, adaptation and mitigation subjects are more important than science. So there are plenty of achievements in this country. Question is how many Gulkas and Chandris? We have less. I'm very sure we are less. So we need people like you to work. And don't feel that your presentation was...
No, I'm not feeling any such thing. No, but I'd like to say something on this, that I think India has actually done a phenomenal job on having earth scientists the way it has come with a lot of investment, right, in the country. But the space of adaptation and mitigation has only evolved in the maybe past 30, 40 decades. And so it will take that much time now to build that capacity.
So thank you for a wonderful presentation. Yeah, you want to ask questions?
Yeah, you have time. So, see, I don't know whether I missed out. You talk about the traditional knowledge in harnessing this. In many places in Rajasthan, Kutch, I find, many of these things that are happening there. but I missed that.
Yes, absolutely. I agree completely. And there's a lot of work showing how actually traditional knowledge, or what many people are calling indigenous knowledge, because traditional sort of has sense of as if it's somehow backward in some way, which is not often true. But so there's a lot of work on this, showing that actually they are able to perceive risks better and therefore able to manage risks better. But my own feeling is a bit contrarian, which is that the kind of risks that we are talking of and all the science that was shown in the morning, I don't think traditional, this is way beyond the window that traditional knowledge had, the perceptions of change and the risk regime that I was talking of is changing too rapidly. So our Baolis and all of Rajasthan, they will not, I mean, they have a very crucial role, but they're necessary but not sufficient, is what I'm saying.
Thank you.
Thank you, Chandri, for coming here. You have to now join for panel discussion.
Yes. Yeah. We thank all the speakers for very informative and engaging sessions. As a culmination of all that has been shared and for recommendations to emerge, we will now have a panel discussion that will be moderated by Dr. Rupakumar Kohli. Dr. Kohli is currently an honorary scientist at the International Monsoons Project Office, located at the Indian Institute of Tropical Meteorology, Pune, India. Earlier, Dr. Kohli has served as the Chief of World Climate Applications and Services Division at World Meteorological Organization Secretariat, Geneva, where he supported the implementation of the World Climate Services Program, enhancing national capacities, coordinating regional and global networks of climate service providers, user liaison in climate-sensitive sectors, and research operation linkages. Also on the panel are Professor J. Srinivasan, Professor Ravi Nanjundaya, Dr. R. Krishnan, Dr. Ulka Kelkar, and Dr. Chandni Singh, and Dr. Gopal Iyengar. Huh? Okay, instead of Dr. Gopal Iyengar, we have Dr. Vimal Misra who will be joining in the discussion. I request the panelists to take their place.
Thank you for that introduction. And I know it has been a very long day and lots of information to actually to digest. With the excellent presentation we had always. So I hope actually we can complete this panel discussion in as short time as possible. In fact, I have a vested interest in that because I have flights to catch. So let's try in about half an hour. And in fact, since there was so much of information today that I don't want to complicate this further. So I want to simplify the whole thing by going back to the title of our symposium. And in fact, I compliment Atria University and Rajivan in particular for organizing this. So climate change, science, projections, and climate action. So let's try to kind of take a step back and see how we can actually address some of these things in and help us to have some high-level messages that can be actually worked out as recommendations for the symposium that can be worked out. So actually, I was expecting Professor Keshavamurthy also to be part of this panel discussion because of his long experience in modeling. So actually, I would like to put Rajivan on the spot and direct the kind of a high-level question that I wanted to actually put to
Professor Keshavamurthy. In fact, Rajivan is a good friend of mine. We had about more than 3 decades of association, and both of us were actually introduced to climate models almost at the same time with the same group in the US. So with that kind of background, I want Rajivan to actually tell us what he feels about the progress in climate modeling, particularly in representing the Indian climate dominated by the monsoons, and what are the expectations from the modeling community to actually to provide actionable future projections, and what advice you can provide to the younger generation to actually to take on the challenge.
It's a good question. As Professor Keshavamurthy is missing, I remember Keshavamurthy was when he was the director of IITM. He started the first climate modeling group in IITM. And I remember he bought the first silicon graphics machine at IITM, computer or supercomputer machine. And it was somewhere some late 1990s. It was. And since then, IITM and many academic institutions, for example, IIT Bangalore, they all started doing climate modeling. And our initial problem was the availability of computer. You need huge computing power. Computer power means money. So everything started coming after 2006 or so. More funding has come because we started a new Ministry of Air Sciences. More funding has come. 300 crore is to go to IITM, 200 crore for AMD. So a lot of funding has come. So our computing power has gone up exponentially. And also the efforts on climate modeling. I'm not talking about weather modeling. I'm talking about climate change modeling, and climate change modeling. And since then, as IITM, they have started a new center called Climate Change Center and Center for Climate Change Research, CCC. And now IITM, Dr. Krishnan was the director there. And they now started, now they developed the first version of a system model. We should be very proud. India has developed for the first time a climate system model. It's not very highly comprehensive, but still there are scope for improvement. And I'm very sure that they're already working on that. So we have, from late 1990s, we have really moved very substantially. We have improved a lot in progress. We made a lot of progress in climate modeling and climate change projections. And Chandni was showing the climate change assessment report where I was secretary. I asked Krishnan to prepare the report. It's the first time we prepared the National Climate Change Assessment Report. And I wanted the report should be free of cost. So we gave money to Springer, 45 lakh or something. 6 lakhs. Huh? 6. That's all. That's all. Very cheap. Okay, 6 lakh. And we told them that you put it on the website free of cost. So anybody, see, last week I was showing somewhere 411,000 downloads and 526 citations. It was published only in 2020. 4 years it has come. So we are moving, frankly speaking, in the right direction. We are doing a lot of good climate modeling work. And as Krishna was saying that there are a lot of things to be improved. We have still a lot of uncertainty. Professor Jay was saying that, and Ravi was saying that cloud relative forcing, for example, is not well known. So we need to do a lot of work, but we are on the right track. And we should be happy that we are a lot of good people to do this job in India. I remember earlier days when T.N. Krishnamurthy used to come from the US, we all get surrounding him. That because for him, for us, it is a data, his model. So that those days are gone. Now we are self-sufficient. We are good for ourselves. We can do our job ourselves.
Yeah, thank you very much, Rajivan. So that means we have the road made ready for the young generation to travel, to improve further the modeling. And talking about the modeling, actually, Ravi has raised an aspect of the uncertainties, but I will not put that question to Ravi. I would like to kind of request Professor Srinivasan. Ravi has actually spelled out different types of uncertainty that are part of the modeling work. But uncertainties are there everywhere, even in observations, even in satellite measurements that Ramna has shown. Everywhere uncertainties are there. So, Professor Srinivasan, can you share with us your thoughts on how we can minimize these uncertainties and where it is not possible to minimize the uncertainty, to communicate or characterize these uncertainties and convince the decision makers to confidently apply this information. Because we know that uncertainty, we cannot wait for these uncertainties to be zero. With the uncertain information, we should be able to take action because things are happening now and we have no time to wait.
Yeah, I'll tell you first the contradiction we have. I've spent a lot of time in the last 30 years convincing people that climate models are reliable for global mean temperature, okay? But the same models are totally unreliable for predicting what will happen in Bangalore, okay? But you'll be surprised, at that time people are skeptical that you can trust climate models. Today they've gone to the other extreme. There are NGOs producing documents of what will happen in Bangalore 10 years from now, which is ridiculous, okay? They don't understand that climate change in Bangalore is very different from climate change globally, right? I don't know how to, I wrote many emails to people, they were not happy with my criticism. See, politicians demand very nice reports, what will happen to various districts in Karnataka. We should have the honesty to tell them we cannot do it. We don't have the capacity, not for the next 10 years. It may take 10 years, as Ravi had talked about, as the resolution goes down, if AI and M will improve, maybe 10 years' time we'll be in a position to forecast what will happen. But right now we are not there. I think it is good to be very honest and tell them we cannot make predictions about climate change 10 years from now. So that's the first thing to be done, because to me otherwise, because so many models are there, so many outputs, they can turn out all of them, people can generate all kinds of fiction. To me, that's all. A lot of reports are there about what will happen to smaller regions, right? Yeah. So although IPCC made a clear statement a long time ago that anything below 1 million square kilometer, you cannot trust the result. Okay, it is there in black and white. Nobody reads it. So to me, that is the first communication gap between modelers and people who use models. Okay. Now the second problem is there. That's why I think our policymakers and politicians are a little frustrated, because you posed a problem. There is going to be terrible change in this country over the next 30, 40 years, but you're not going to give us specific forecast which we can act on. So the whole question of adaptation we have heard about is possible provided you know what you have to adapt to, right? So to me, this is where the comment lies. Modeling has improved a lot in the last 30 years, but it has not reached the stage that the users want. Users want clear answers for very short term that we cannot do. But I think we can tell them that on account of improvement that happened in this country, short-term forecasts are improved. Okay, so people can the exposure part we can reduce. As flooding or cyclone track prediction can help reduce the exposure, but we cannot really give kind of advice they want as to what they should do to change. For example, we talk about Mumbai's threat of flooding. Now, that's only hypothetical. We don't know how bad it will be. So, somebody is planning Mumbai's future. We cannot advise him how to change Mumbai so that it is more resilient, right? So, I think there is a gap between people who want data and what you can supply. And I'm hoping that in the next 10 years, there'll be sufficient improvement. But still, I don't see any time that climate change, climate models will become good enough to predict what will happen in Bangalore 10 years from now. That would be going to the limit. I don't see any chance. Maybe Krishnan and Ravi can differ from me, but I don't see any chance. Okay.
Yeah, in any case, actually, we also should realize that most decision makers are already familiar with working with uncertain information. The greatest example is share market. So there is so much uncertainty, but it doesn't bother. It doesn't prevent people from making huge investments. So in that sense, I think if we can present information in a transparent way with all the uncertainties associated with it, and let the user take the decision within that kind of range of uncertainty that we can provide. I think that is how we need to present climate information in that context. Well, thank you, Professor Srinivasan. Yeah.
Yeah, so this is the
The uncertainty is also as a problem for even short range to medium range seasonal forecast. So we try to improve the model so that that's a systematic work that will continuously go. We cannot wait for the model to be perfect. What users want is some information. So what we are told is that you give information along with the uncertainty. So that this is the user should take a decision based on our information plus uncertainty. Take a very informative decision he can take. So, but we cannot wait for the model to be perfect. So uncertainty will be never zero.
Yeah, this is exactly one of the first principles that was actually adopted for UNFCCC, United Nations Framework Convention on Climate Change. It's called principle of uncertainty. That is, we cannot wait for things to be perfect to actually take action. So that,
sometimes the forecast we make may not be actionable. I'll tell you what happened 10 days back. Whatever happened in Wayanad, there was a fight between the government, Kerala and federal government about the forecast.
Yeah.
Okay? To me, some government said, you made the forecast, you can, but I think was the forecast actionable? Remember, same thing happened 10 years ago in Kedarnath. IIT made the correct forecast, but it was not made in a way that the district magistrate or the people on the ground would say how to take action. And the same thing happened here, I think. They did not say there will be landslide, obviously, because they don't have enough knowledge, right? They only said there will be heavy rainfall. That is not enough. But the kind of qualitative forecast that's coming up, heavy rain possible at this place, to me, it's not actionable. So to me, some effort occurred after the Kedarnath, this one. I think the background forecasts are now more clear-cut. There are various colors and so on. Same thing can be done for landslides. The landslides are going to occur more often in Uttarakhand, Himachal, Western Ghats, everywhere. So we may have to come up with more things which, what do you call, person on the ground, the administrator, can, because he doesn't understand climate change, he has no time to design it. We have to give specific guidelines after giving the warning what you should do, right?
So we are moving to impact-based forecast. That means they give a forecast and say what could be the impact. Exactly by now, we gave a red alert. The collector, what red alert? Okay, fine, it will rain. But we never told him that it will lead to a landslide. IMD is not responsible for that, but simply giving a forecast will not suffice. So IMD is trying to do a lot of impact.
But it might be easier. What impact is, we had a discussion not here, pointed out that we still don't fully understand what causes landslide. So I told him, for example, the 200 millimeter rainfall in Western Ghats is very normal. Every year there are in Mumbai, everywhere 200 millimeter occurs. Every year don't have landslides, right? So we have not understood the details, and as you pointed out, we don't have enough ground data.
Yeah.
And until that is obtained, how can you do a forecast which is of value?
Okay, let's move on to another topic. Ravi, we know that there are multiple sources of information and multiple levels of scales of information. And it is important for any specific user or decision maker to derive the most appropriate information relevant to the decision context. So in that sense, how can we actually use the emerging AI, ML technologies to actually right scale the information? It's not even downscale or upscale, it's right scale, because it has to be directly applicable to the scale of the decision. How do we use these technologies to actually convert the available information into that context? And at the same time, many users, if you present them even with a small map or a chart, they feel it is highly technical. So we need to convert this very complex scientific information into easily understandable messages. So can we use the LLM technologies to actually convert this complex information into few messages, not only communicating to them, but also understanding or allowing them to ask questions in simple language? It can be English, Hindi, Telugu, Kannada, any language. So can we actually get into that arena with the technologies?
Okay, an interesting but tough question is what I would say. Well, let's see. For example, let's say you talk of
as simple as rainfall in a particular area, then you need to worry about the area around it. Let's say if you're looking at traffic conditions and all, then there has to be a translation of the rainfall forecast in a way to tell the person on the street, whether it's the policeman or the guy driving the car, that okay, this is the kind of condition that you are likely to get, and this is the probability of that kind of a rainfall and the flooding and being stuck. That's, I think, the kind of information that we need to translate. That will not come only from one particular domain. It has to come across domains. It could be hydrology, it could be even traffic management, it could be anything else that. So we have to kind of put them together, and the messages should not be too graphical or too complicated. It could be just say that okay, there is rain here. You don't do this or do that, or take this road, or don't take that road, or if water is being released, okay, what is being released and how much could be released, and those could, I mean, it should be like simple flash messages that we could convert it. And of course, I'm not an expert on LLMs. As I said, I don't understand too much of AI/ML. I'm interested in it, but yes, I think it could be done with LLMs, and appropriately we'll have to ask the questions that we want answers of them. That's more important. We have to think and say, okay, what is it that I want from the system? The system can give me any kind of answer, but what is the question I should be posing to it? And then then maybe you can use any of the AI/ML techniques to get an appropriate answer from it. And of course, additional data wherever you can get from. It should be a cross-domain set of data which you can use to kind of give appropriate forecasts or messages or warnings. I think that's what we have to do.
Yeah. Ultimately, I think climate information should be as easy as using a Google map to go somewhere. So I think we need to get there. I think for that, I think we can't do anything without AML and LLM technologies. I think it's an area that has tremendous potential, and it also actually helps us to actually cover the last mile, where the information actually leads to a particular decision. I think that part is still there is a tremendous potential for, particularly for the younger generation to look at.
Okay, on a lighter note, when IMD gives you a forecast, in Hindi they have a very common thing. They say, "Dur dur tak varsha hone ki sambhavna hai." Up till now, I have not understood what exactly IMD is saying about it. Sorry, it's just in a lighter note, but I think that's exactly what we should not be doing when we are kind of sending out things. Yeah, that's what I wanted to say.
They mean to say widespread.
Yes. Yes.
Thank you. Thank you.
Only people are good in saving their own skin. And historically, it's not by present IMD. Even if you see the old original reserve forecast issued by British people, they used to bird the reserve forecast so that at the end their forecast is correct. So we learned from them.
There's a deep issue more. Dr. P.V. Joseph mentioned, the old days there was no certain nothing when he had to advise the pilot about thunderstorm on the way. They have to be careful and say it will happen. Chances are very low. Because if an accident took place, Joseph will be jailed. So those issues you must also understand that if you get a very specific forecast and you go wrong and leads to some disaster, you will tomorrow face a court case. So he said, your life was very hard. And people laughed at them. He said, but what can I do? I cannot say everything is clear and something happens.
IMD is improving their impact forecast. Good thing is one small incident to tell you. When I was there, when heat wave something happened, they went one step further to give advice to the people not to do or not do. They said you should not take liquor. Many people does their job. They said don't take liquor.
Yeah. So let's move to another topic. Krishna, as Rajivan mentioned earlier, we have made rapid strides in modeling, and we have very sophisticated global and regional models. And give us an idea of what further future directions we are looking at. And also, the models put out tremendous amounts of data. So naturally, the users who are not familiar with that are intimidated by the volume and the scale of information. What are the best ways to actually package that information in a way that people can easily apply into their decision context?
Actually, this CMIP, participating in CMIP, it was a very important exercise, at least for IITM. Because CMIP, first time when the MOES and NOVA agreement for the monsoon mission happened in 2011, and the fifth assessment report came out in 2013. Already we were too late. So we realized that it is not going to happen for the fifth assessment report. But one thing we said that at least we should go for the sixth CMIP and also IPCC. So that was the plan. And the good thing is it happened with a seasonal forecast. The aim was you take CFS and do seasonal forecasting. And we said, okay, we will use this model for climate making Earth system model. And we said, okay, take out the ocean model and put POM4, P0. Then we wanted to put one P1. So which was a big, we didn't realize the magnitude of that. But then that exercise took us 3 years. And in 2014, I presented in India that Rajivan was about to join IITM. So our radiation imbalance was there, about 7 watts per meter squared. You said that you better address it, I remember. So that is the first target we set, to have a climate model, reduce the, and then we discovered that there were so many problems, especially in the polar. AMOC was collapsing. The Arctic ice was melting, and then the AMOC was totally collapsed. And that was affecting the sea surface temperature, the energy imbalance. And so that we fixed it. So we identified where are the big problems which can affect. So that was one important. Then we did so many other things and focused on the monsoon. We get global climate, but make sure that the monsoon is not lost. So these, and fortunately it was for seasonal prediction. So our teleconnections with the ENSO, IOD, they all came in our favor. So that was a very strategic move, transforming a seasonal forecasting model to a climate model. It helped us because from our own importance for the monsoon. And of course, the water cycle chapter was introduced in the IPCC first time. Both working group 1, working group 2, none of the previous IPCC report have a dedicated chapter on water cycle. And I was fortunate to be a coordinating lead author. We pushed all the monsoons, all the regional monsoons. I thought we should focus on the regional monsoon. Global monsoon is fine. So that's how that assessment came out. And so since then, of course, it was a course resolution because we had to complete so many years. First time we were doing it. But now, so the CMIP 6-7, we are going now. Already the preparation has started. So this is going to be at a much higher resolution.
When the output results start coming?
It will start making next year, sir. The projection, already the PA is frozen. We are frozen. Yes, it's very much. So it is at, now we have a TCO grid. And it will be at a 67-kilometer grid. Earlier it was 100 and it was almost close to 180 or something kilometer. Now 67, that's a big jump we have got. And we are going to put on the ice sheets, Greenland ice sheet. Already the Sandeep Narayan City has started working. We also want to go to the Himalayan cryosphere. So we want to get all these Earth system components, and it's already doing a good job. And we are using for land use, land cover, some of the NRSC data for the Indian region. That is one more thing we have done. And also we have to get told our group that you focus on the water availability for irrigation. That is, I think there's a group in Germany, they're doing that. I told you, we have to interface that. Water availability, focus on water, that is going to be an important topic. So anyway, that will happen in next few years. So, and there should be a strong representation in IPCC from India. So that is important. The Chinese, they come, they have in every chapter, they will put 1 or 2 people and all working groups. So I think it's very important that India participates. CMIP in IPCC, we should have our presence. And so I think I'm seeing big value additions compared to the previous. But still some big biases are there, like the ITCs that I was telling. Double ITCs, it's a big problem, not only here. GFDL Professor Ramaswamy tells it's the same problem. They have fixed it. So these are big problems, not only for us, even the world is facing. The winter time, if you see South America, you are not getting rainfall over Brazil, Amazonia, it shifted. So these, we have to really address these hotspots. And that is going to improve your general circulation, your ocean atmosphere, coupling, feedback, teleconnections. First, you have to get a handle on them. Otherwise, it's going to be difficult. And slowly increase the resolution, go step by step. And we have to go systematically. It will not happen. And because they have all built for last 30, 40 years, we are into the ball game now. Go systematically, go with a plan. Planning should be pakka. You do it and keep improving, and the improvement keeps on happening. It is not first time when you were running the COLA model and all making, I know how the forecast will. I think we have come a long way. So that is that there's a plus, but we have to also learn from the lessons and keep improving. And we have to improve the human resources in this climate science, climate modeling, build the expertise. I think that is going to be very important. Of course, other things, adaptation, mitigation, other things are also important. But that community we have to have. You need a sizable community. And for the short range, all these extreme rainfall prediction, heavy rainfall, which lead to flood, early warning system, data assimilation, that is also one area where we have to improve. So we have to do this very system, weather prediction and climate modeling. These two, and bring all these new technologies like AI, ML, which I don't know very much at the local scale. So I think we need to have a very comprehensive plan, go step by step. And we cannot tell, as Professor JS was telling, I'm going Bangalore, I'm going to give. I know what is really feasible, what is not possible. That we should be very clear. Claiming, so I think that we should really set this is the plan. And we should, workforce we should generate to be there in all the international platforms. India needs a very good representation.
And and also you should facilitate application of that.
Absolutely.
In fact, that's where you need hand holding. Because many times on the user side, they don't have the expertise and they need help, and that's where you actually.
So the protocols are, we have to make the ESGF and we have to CMARify the data. So the CMIP sets all the benchmarks, how to put it, and we followed that. We went for CMIP and 6, CMIP 7, we will do it. And last one more point I want to add. Rajivan told that you have to bring the climate change book for India. It was very hard, but it was a very important thing. So 2020 we have done. Now 4 years are gone. Hopefully somebody starts making the next.
In Atria we are trying to do it.
So we will collaborate with you. Yeah, so that will be an important thing. I think we should be there. So every periodically, every 5, 6, 7 years, we should have a national assessment report. That
US does it every 4 years.
But what US, somebody told US that is more like a brochure US report.
Very exhaustive, I said.
They cover adaptation also.
They cover both the adaptation and mitigation. We have done only science part. Next time we should add.
Maybe working group 1, 2, 3 type of thing we should have.
But you have done a wonderful work.
Okay, let's move on.
But that was a very hard time actually.
Ulka, so you have worked with lots of interdisciplinary teams to link climate model outputs with decision makers in many contexts. Based on that experience, now probably using your own kind of expertise in behavioral economics, can you tell us what motivates people to actually confidently use climate information in their decision context? And what is the current status in the country, and where we can go in the future?
I have no answer to this question. What motivates people to use climate information?
Yes.
Well, two things. I think one is fear and the other is a profit motive. Profit motive, I mean, I think you're getting requests from insurance companies, renewable energy companies for weather forecasts. For renewable energy companies, it is as important as knowing where to site a wind farm, how much generation and hence how much money to expect in a given time period. What are the long-term trends? For example, there was one study that was done by researchers from Oxford University, which found a 40% variation in monsoon winds in the last few years, and hence an impact on the wind power output. But it could also be things like, for example, the additional cost of making that energy infrastructure climate resilient, because these wind power, solar power projects are themselves being affected by, on the one hand, heavy winds, but on the other hand, even things like air pollution, which is reducing their output of solar panels. So it's very much a profit-motivated thing. For insurance companies, it's a little bit tricky because with climate change, that is with systematic, widespread climate risks, the fundamental logic of insurance breaks down. because that risk mitigation or risk spreading behavior is no longer applicable. Instead of saying that, Vimal's house will not get burgled the same night that my house will get burgled, and so we can have insurance. All of our houses will catch fire at the same time, right? So with insurance, it is actually being used in a negative way, which is it can be used to raise premiums, or it can be used to completely withdraw, as is happening on the east coast of the United States or in the wildfire area of California. The other is, of course, fear. I mean, people do want to be safe. I think every time there's a tragedy like this, people feel very helpless. And so that's why they look for local projections, because it is not enough to just scare them and say climate change is going to happen. Local MPs, MLAs, they do want to take district collectors. They have been given responsibilities. Tamil Nadu, for example, has a climate change mission now that every district official should be a climate change officer. So what are they supposed to do? What kind of precautionary measures should they be taking? So, for example, we are working in Bihar very extensively. And even if we can't make a climate projection for Bihar specifically, we do know something for that part of the country. And we do know the baseline conditions are very different for north of the Ganga and south of the Ganga. North of the Ganga, you have transboundary floods from the Himalayas. South of the Ganga, you have droughts. So there needs to be some science-based actions, some action plans that policymakers can make, communities can make, NGOs can make. And finance also wants to go for climate resilient action, but doesn't know what to fund. So there again, I think there is a lot that can be done, and a lot is happening. The more the science is robust, the better it can be used.
Thank you. So another fact, actually, I think benefiting from climate information is a key motivating factor. Another motivating factor is actually by seeing your neighborhood. If someone else is benefiting. In fact, Sulochana organized a project, Ulka's mother-in-law. So she organized a project on climate and agriculture in Rayalaseema. So there they actually identified a few champions who actually use climate information and advertise the profit that they get. So that actually provides the motivation for those who are actually looking into climate information with a skeptical mind. So that's another motivating factor. So we need to find ways to actually enhance confidence or credibility. And at the same time, as you mentioned, insurance example. In insurance, you have actually conflicting motivations because insurance company wants to earn profit by hiking premiums, and clients want claims to be settled. So this is a kind of motivation that play against each other. So those are all the various things that we have to actually see. Probably that is an area that is left to economists to figure out how best to handle. Dr. Jannis Singh, you have actually worked with human dimensions of climate change, both in urban and rural sectors. So in that context, we always have this issue of equitable access to climate information, and also the adaptation actions that are associated with it. So given the disparities that we have in the society today, and given that climate information that we are generating in the public institutions are for the public good, how do we ensure that there is an equitable access to climate information and also opportunities for adaptation among those communities?
Thank you so much. I think this issue of equity and mitigation, I think this is a very central issue in adaptation. Who gets to gain and who loses because of certain actions. When it comes to, actually, I have done some work on climate information services and advisory, especially these daily or weekly sort of forecasts that are given, and why do certain farmers take it up and why don't certain farmers take it up, and also then how do you improve uptake and then utilization of this information. And what we've seen, first of all, the ways that we give this information in, it has to be in a way that the user requires it. And I think it seems so commonsensical, but somehow we keep on forgetting it. We like to load more and more detail and information in a particular advisory rather than keep it more user-centric. Also, of course, that somebody I think was mentioning it, that it's not only the fact that there's going to be a heat wave or untimely rain, but what impact that's going to have on your crop. So that second level of information, which often does not actually sit with a meteorological department or a regional met station. It is actually your KVK, your agriculture scientist, who's going to give that thing, which means you need cross-sectoral, combinations of expertise. And then the final thing is, of course, from the user side. We have seen very clearly a lot of surveys we've done where women don't actually own the phone in the house. But if you're giving mobile-based advisories, it's going to the man, and the woman is the one who's in charge of planting the seeds, weeding, and very important parts in the, in the agricultural activities in a household. So what type of message you're giving, and then also in what form. So there are some NGOs, WOTR in Maharashtra, they've shown how you can have advisories that change every day on the Gram Panchayat, the Gram Sabha building, but just put up there so that it's democratizing who has access to that knowledge. So there are ways of doing it, I guess. In urban areas, it's a little more tough, and I always like to actually put the onus back on people like us who have education, skills, means also to adapt. We can buy houses in certain places. What are we doing? And are we also using some of these advisories to change our actions? Often not. So it's really, and this is why I always feel whenever I have conversations on climate change, we are still not engaging enough social behavioral scientists in the conversation. These issues have been addressed, tested with the same kind of rigor that we use in our modeling and all of this in the social sciences. So let's bring those people on board to design some of these IMD products, and then we can make them more effective. I have also spoken to folks in the NDMA to say, if you're giving heat advisories, let's do some pilots on designing different styles of heat advisories. Just one jingle on the radio or a newspaper thing, which are very important, but there needs to be much more testing, scientific testing of which ones are working, which ones are not. And then let's change them for the next year based on that science.
Thank you. I think in addition to that, I think we also need trusted communicators that can actually relate to the user. In fact, I came across a story in Eastern Africa where the communities, the small communities, they have someone known as a rainmaker. Rainmaker is a traditional, a kind of hereditary activity who actually predict rain based on flowering or whatever natural indicators that are available in the environment. And the climate center there actually trained these rainmakers to use modern climate information and use the rainmakers to actually to link to the actual users. So that's how, if you can develop a system of an army of communicators that can actually help us to reach the climate information to the
thing to add, I mean, we have a similar example, like in Kolar, all the fieldwork I used to do, Neerganti, the whole system of, there were these people with wisdom around water, Neerganti, there are songs around it. They used to go from village to village, they knew which tanks are going to be filled when, and accordingly you use these man-made tanks, in a certain way. So I think those practices which have somehow gone, I mean, we have that history and that culture in India as well. It's the merging of these two cultures, which are with very different values, right? These traditional knowledge systems and then the scientific system. It's not always easy, and that's what we have to figure out.
Thank you. And coming to the last panelist, I will ask you the toughest question. So, we have an excellent climate community in India that we have seen, and also a world-class hydrological community. But the bridge between these two, I find, is still not strong enough to actually to benefit from each other. So what do you think is the problem, and how we can actually address this by helping them to work with each other? In fact, this can actually save lives and property if there is perfect coordination between climate prediction and hydrological warnings.
Yes, I think that's a great question. And I think as everybody is optimistic, I would also say like in last 10 or so years, there has been a lot of progress on that front as well. So climate community and hydrology community has started working together, but eventually it all depends on need. You know, in India, hydrology community is very small, even smaller than climate community, I would say. And even in that small number, rarely if you do operational hydrology, where they translate meteorological forecast to hydrological forecast, and that can be used for decision making. So whosoever is doing that, they are very well connected, I would say, both with organizations like IMD, IITM, and they are getting help, data, everything. Like for instance, our group is very well connected with IITM and IMD both. Every day we receive forecast and observations that we use in our hydrology model to give the soil moisture, runoff, and other variables, the stream flow, etc., including floods. But I think given the size of our country, these two communities are extremely small, I would say. And the importance of water, the hydrology community and the climate community is very small, and even then we need to do a lot of capacity building. So for instance, there are many people who use climate data, but they don't understand it. And you might have heard like people will say there is a climate forecast until 2100. You know, out of 10 people, 7 will say like this. And they don't understand the difference between projections and forecast. So I would say, I mean, we need to strengthen the capacity. We need to sort of include more people. How, I don't know, probably these are not the top areas. Now AI ML is the hot cake. Everybody wants to do AI ML. So maybe from that route, more people will come to climate or hydrology. But hydrology, earth science, and climate, you know, these are at the bottom of the hierarchy. When you talk to students and IITs, they want to go do computer science, and you know. So I mean, that is one big gap. So the problem our country is facing, we have a very less trained, small community that is trained and they can deliver something. That community is very, very small. Solution, I mean, solution यही है कि see, also people, society, they don't have very high expectations. So now expectations are coming because we have every year disasters. So for instance, when you have a landslide, all the landslide experts will be in high demand. It's like that. When there are floods, major floods, hydrologists are in demand. When are heat waves, so this demand is increasing because these extremes are increasing. So now we have expectations, so probably more and more people will come forward and do the good work and deliver.
It's the basic problem. Say, we should have next meeting when after the next disaster. After next disaster to happen. So that's the problem here. See, we don't find a system and solution for any issue. We are waiting for a disaster to happen to meet all of us together and find a solution. But that does not have a permanent answer.
Because we always are very good in reacting. Proactive, you know, planning, we don't put much value. But
People always prefer crisis management rather than risk management. But risk management is always more effective and less costly.
The question is too good because our community even now climate scientists and heterologists don't work together very as it is required. Vimal is an exception.
Yeah, of course. But we need more Vimals. Yeah. So
Interdisciplinary, this interdisciplinary courses will be there.
Right.
Study hydrology and also climate.
No, courses are there. Problem is not of courses. Problem is communicating and working together.
Mutual trust also has to be there.
I can give you a small example here.
Yeah.
I remember 2013, the Uttarakhand floods. You know that so many devastating flood. Then principal 95% of the forecasts are correct. So I was sitting near the yesterday. He was asking, will you call this meeting? He said that 95% of the forecasts are correct. So they think that their forecasts are correct. So they don't want sorry, I mean to say that the meteorological forecasts are very useful to them. What the 95% is, they put a runoff machines over so the instrument where they can see the flow. And next 6 hours, how much water will go? Right? Anybody can do. So you know how much water is coming, and next 6 hours, what will be the flow?
It's the correlation based.
Correlation based. So you can the forecast, but that's not really the flood warning we really require. So people don't get to it. Basic problem. That's why morning also I told the basic problem.
I think we have a lot of insecurities. Every organization has their own insecurities, and that's why they don't, because they feel if we work together, it won't be clear that who did what, and credit will not be given. You know?
Anyway, thank you for this perspective. Yeah.
I think justice and the courts are an important part of the puzzle here, because that's when they will safeguard your most vulnerable community. Hopefully, I'm not sure if it happens, but a lot of modeling and then looking at the impacts, both pre and post, would actually help climate justice to happen. So, do you see that being viable anytime in the future, or is it already starting to happen? It's just a curious thing. So, for example, say you're doing some work which increases the chances of landslides. A private company has done some quarrying which increases the chances of landslides. There is a justice element to it, which is that you can technically sue them for the work they've done. Right? So the courts are an effective deterrent to future activities happening in that sense, because they are precedents also. But do you see that pipeline actually happening from the modeling and the impact assessment side to this, to the legal community?
I could give you a simpler example, which has already happened, which was in California, the electricity company PG&E, where it was determined that they are aware of climate change. They are aware that climate change is increasing the risk of wildfires, yet they did not take countermeasures to underground the wires or to cut off tree branches, that were increasing the spread of the wildfire. And so they were sued, and this was declared, this is called the first climate bankruptcy. Now, of course, with loss and damage, I think Chandni can speak more about that. I think there is a lot of emphasis now on attribution science. To what extent is a given disaster specifically due to climate change, or to what extent has its probability or frequency increased due to climate change rather than the baseline variability? So I think there's definitely room for all kinds of documentation as well as modeling. Jani, I don't know if you want to add.
Just, I think to add, of course, on the attribution science side, things are moving, but I am quite skeptical of it actually leading to climate litigation in the country right now. I think even if we are able to, and that's what Freddie Otto and others have been doing with teams from India also. I think IITM also giving inputs that, what was the what has been the increase in the likelihood and occurrence of a heat wave or a cloud burst and so on, with and without climate change. What's the difference? Anthropogenic climate change. So while that is moving along, to move from that information to building a case against certain polluters and then that leading to payouts, I think in India at least there's there's more time needed. The international argument, I think, is much stronger. I would say, actually, what India needs to focus on is a database on loss and damage, first of all. How much loss and damage is occurring because of anthropogenic climate change and how much is otherwise. This right now, when you talk to NDMA, they unfortunately still do not have a good database of, leave climate change for a second, damages due to existing disasters in the country in 2024. They will not be able to, because that is on states. Then the knowledge or the data coming to them is very uneven. So there are some fundamental issues we first need to solve. Then will it maybe filter to climate litigation?
Heat wave. Yeah, it is not even recorded.
But even like heat wave, okay, there are questions of, there are, I mean, from the medical science side, if for 1 minute, but even rapid onset events, infrastructural damages, sometimes we don't have clear estimates or like actual numbers on that also. So there's a lot of data stuff we need still, I feel, on this side.
It's not going to happen.
Okay. Let us.
Case was what I had in mind when I asked the question.
Okay, let us.
The case of the T-Star dam, the glacier burst. There is enough infrastructure issues which are caused.
There's a case going on that dam which completely went costing 50,000 crores. The insurance is an international company.
Yeah.
They don't want to pay. They want to blame the government. So it's going to drag on for many, many years.
Okay, let us thank all the panelists for the excellent. If there are any questions, particularly from the younger generation, if you have any question, maybe we can take one. All are tired. Yeah.
Long day.
Thank you very much for this excellent. I hope these are useful for recommendations. But one comment I wanted to make. I was waiting to hear one term throughout today's lectures, but I did not hear except maybe Dr. Chandni Singh mentioned climate information services.